Okay, so I think we can get started. Welcome all of you to the 8th AI City Challenge. I know it has been a long a challenge and you guys have performed really well in all the tracks. We just really appreciate all your participation in the challenge and making it a successful challenge for this year. So we're going to present to you some summary of our challenge. Okay, so my name is Zheng Tang, or you can call me Thomas. So I'm one of the organizers. So you can see this year we have a huge crowd for organizing this challenge. So Shaw and I, we are from NVIDIA. We have Professor David Anastasiou from Santa Clara University, Professor Ming-Ching Chang from the University of Albany in SUNY, and he is currently in Taiwan. We also have Professor Liang Zheng from Australian National University. I think he will be here in the afternoon. And Professor Anuj Sharma from Iowa State University. And Professor Pranamesh Chakraborty. He's from the Indian Institute of Technology, Kanpur. We also have Norimasa Kobori from Woven by Toyota. He's with us today. And also Professor Junwei Xie. He's from National Yangming Chiao-Tung University. And Professor Rama Chelapa from Johns Hopkins University. We also have some challenge committee, and they are also composed of a lot of different university and institutions. It shows how big this organization is to run a challenge like this. So this is the 8th year of the AI City Challenge. And you see the first year is the 2017, we started this initiative. And for the first year, we run this challenge at the Smart World 2017. And afterwards, we have been in conjunction with CVPR. You can see that this year, we also have 5 challenge tracks. So we have a new challenge track introduced by Toyota, which is on traffic safety description. We also have another new challenge track introduced by the Professor Go Chu's team and also the National Yangming Chiao-Tung University. So it's on object detection in fisheye cameras. So the existing 3 challenge tracks are the MTMC people tracking, which is multi-camera people tracking, and driving action recognition, and also helmet detection. So this year we have 5 tracks, and the winning teams will have the opportunities to get NVIDIA GPUs as the challenge awards, and we will announce the challenge awards in the afternoon. So this is the participation for each year. As you can see, we start at 2019 only for the first year, and then we started to grow. So in the 3rd year, when we introduced the multi-camera vehicle tracking dataset, which is a city-scale dataset NVIDIA Metropolis has introduced, we have seen a big boost in the number of participating teams. And then in 2023, we also have introduced several new challenge tracks. Especially, we have a new challenge track that have a data set created by the NVIDIA Omniverse. We have a major large-scale data set for multi-camera people tracking. And this year, we even increased the scale of that data set by 10 times. So you can see that we have another jump of participation. This year, we have seen a 43% increase in participating teams from which is 726 participating teams this year, and they are from 47 different countries and regions. So we are very proud of these statistics. Okay, and here is the statistics of the number of teams that submitted for evaluation. As you can see that the trend is also growing every year. So we introduced the evaluation server in 2018, and starting from then, it has been managed by Professor David Anastasiou, who is a major contributor for the challenge. And you can see that this year, we have also seen a major increase in the number of teams that have submitted for evaluation. So we thank everyone for your participation. And here are the statistics for the participation and also the teams that submitted to our evaluation server. We have 726 participating teams from 47 countries. We have received participation requests for 5 challenge tracks, excuse me, here. So for track 1, we have seen the most participation, which is 421 teams. Track 2, 359 teams. Track 3, 349 teams. And track 4, 403 teams. And track 5, 419 teams. So 209 teams that have signed up for evaluation system accounts. And here is the number of submissions for each track. As you can see, track 4 and track 5 have received the most participation and it's the most challenging among all of them. So we will introduce each of the 5 challenge tracks afterwards. But here is the public leaderboard on our challenge submission deadline, which is way back in March. But this is not the final, like winning teams or the final runner-ups. So we will announce that in the afternoon because we have done some validation of all the people's submission of their code. So this is not finalized. But you can see that we have a wide variety of participants from all over the world. So and it has been a challenging competition, but we see that everyone have been pushing the state-of-the-art accuracy on our data sets. And we have been preparing for this AICD challenge since June last year, which is when just right after we finished the AICD challenge, the 7th AICD challenge at CVPR 2023. So from June to December 2023, we have been preparing for the data set. We are preparing for the data sets. We also submit the proposal to the CVPR and got it accepted. And we started to plan for the challenge. So the challenge was open on January. So we released the training set and the validation set. And then in March, we ended the challenge submission. And then we move on to the stage that we receive the workshop papers from all the participants. And then we also do a validation of their code. And today is June 17th, which is the day for the workshop. And we are very happy to celebrate all this with you. And now I'm going to present all the 5 challenge tracks, and some of the people here are with us, and we will all present for you. So this is some statistics for track 1, which are multi-camera people tracking. So this is a challenge track contributed by NVIDIA, is mainly the Metropolis team. So you can see that we introduced the first benchmark last year in 2023. And this year we have a new benchmark and it is much larger. For example, you can see that the number of scenes has grown from 21 to 90, and the number of cameras has grown from 129 to nearly 1,000 cameras. And the number of people has grown even larger from 156 to 2,481. And the number of bounding boxes have also have a major increase. And also the total length of all the videos is around 212 hours. We also provided the 3D annotation and the camera matrix, and also the character assets are based on a more like a rich and more representative of character assets, which is the render people. And also we use a more advanced metric, which is HOTA for the evaluation. So at the bottom left, you can see some example of a scene of 16 cameras. And you can see there are around 30 people working in these hospital assets. So here is a table. Maybe it's not very clear, but this table lists all the major like a MTMC or multi-camera people tracking data sets that we have found. At the bottom, this is our AICD24 data set, and we can see that it is the largest scale in terms of the number of frames, the number of cameras. We also provide both overlapping and non-overlapping camera views. Also, the camera coverage is mainly simulated. We use the NVIDIA Omniverse platform to simulate all the data sets. And without Omniverse, we cannot create such a large scale data sets. Also, all the video frames, they are high resolution at 1080p at 30 FPS. And all the 6 scenes, their examples, you can find it at the bottom right-hand side. Okay, so now we can move on to track 2. I think Kwan is online. Kwan, can you hear us? Let me see. Chan is not, we may not be able to hear you. Okay, maybe your teammates can help you. Thanks.
Hi all. Thank you for participating track 2. So this year we have released a large scale dataset for large language model for video captioning, which covers the very challenging traffic scenes. And we highlight our dataset on large scale, which is over 6K videos plus more than 130 traffic scenarios, which is very comprehensive to cover many and also important challenging scenes. And also not only about the numbers, we also provide multi-view videos for covering vehicle and also pedestrians. And also we provide fine-grained captions and also fine-grained segments of the behavior phases. And yeah, so we provide a very large scale dataset. Yeah, thank you very much for the participation.
Okay, for track 3 is Anuj or Shaker are here. So yeah, we have some issue like playing audio in the lab computer. Okay, if Shaker or Anuj are not here, I can present for the track 3 for them. So regarding the track 3, we have 16 distracted driver activities. This is a challenge track for naturalistic driving action recognition. We have approximately 90 hours of videos from 99 diverse drivers, and this year we have a major increase in the scale of this data set. We also have 3 synchronized camera views and manually annotated labels of approximately 60 hours of videos for training. And we have recorded at 30 frames per second, and all of the videos are 1080p. And we have like a footage with and without appearance block, and there's a random order and duration of activity. So it's a more challenging case. And on the left-hand side, you can see the setup of the 3 camera views. And on the right-hand side, you can also see we have 16 different action activities for the driving action recognition. And this is a setup of this large-scale data set for this year. Okay, for track 4, with Professor Gochu.
Good morning, everyone. So the track 4 is based on the existing open data set called Fisheye 8K. And the data set task is for road object detection in fisheye cameras. These fisheye camera videos were captured in Taiwan, Hsinchu City by police department. And we were so lucky to get access to these because of the collaboration. I should mention Professor Xie and Min Chen for this big collaboration. And then we have manually labeled 8,000 images. First it was 10,000 images, then there was some issue and we had to get rid of like 2,000 of them. And then this data set has 5 classes: pedestrian, bike, car, truck, and bus. And we have selected 22 videos from 18 cameras. And we labeled 157,000 bounding boxes. And it took us like forever to finish all of this work. And we are so proud that we made it for this track. And we are also very thankful for all the attendance for this track. Thank you.
Thank you. Pranamash, I think you're online, so maybe can you try to present
Yes.
track 5?
Yeah.
Good.
Can you hear me?
Yeah. Can is it loud enough? Yeah, we can hear you.
I can hear you. Okay. Okay. So the track 5 is basically for helmet violation detection. This is typically for like Indian cities or Southeast Asian countries where we have like a lot of motorcycle riders. We wanted to specifically check whether they are wearing the helmets or not, because as you can understand that when you are riding a motorcycle, uh, like it's very essential that you wear a helmet for safety purposes. So this data was taken from CCTV videos of an Indian city. For different lighting conditions, we have daytime, nighttime, we have fog data to understand the challenging like visual conditions, how do we get. So we had a training and test data set of 100 videos each. Each were something like 20 seconds duration each video. This time we had some more challenging videos where we have like a lot of congested conditions and unstructured driving, overlapping conditions what we have. So still in those conditions, how can we basically detect like whether the person is wearing a helmet or not? The classes that were to detect was along with the motorbike, also to separate out drivers or passenger who are sitting at the back, or passenger zero is something who is sitting at the front, because those also sometimes like kids we have seen that who are basically in front of the driver. So the challenge was to detect all this like 9 classes that we had. It's basically 7 classes with or without helmet kind of. And we thank all the participants who basically participated in this challenge.
Cool. Thank you. Thank you, Pranamash. Okay, and now we can have David to present for us the evaluation methodology for each shortened track.
Hello, everybody. We once again used an evaluation server to evaluate online all the submissions of the teams. We had lots of different submissions, as we heard from Thomas earlier. So for the different tracks, there are different problems, so they use different evaluation strategies. So track 1, multi-camera people tracking. We were tracking people across multiple cameras using an expanded synthetic data set, and the evaluation score was a higher order tracking accuracy, HOTA score, and as well as other metrics, but HOTA was used to decide the winner of the challenge. Track 2, traffic safety description and analysis. We describe pedestrian accidents, including movement, scene, context, attention, location, and behavior of pedestrian and vehicle. For this challenge, we primarily scored based on the language description. So we used a mean of 4 different language description scores, including Blue 4, Metero, Rugel, and CIDR scores across 2 video data sets. For track 3, naturalistic driving action recognition, the idea was to identify driver distraction behavior, different actions they were doing instead of driving. And the score there was the average activity overlap score, where activities must start and end within 10 seconds of the ground truth activity start and end times, respectively. So the people had to, or the algorithms had to identify both the correct activity as well as when it starts and ends correctly. according to the ground truth. Track 4, road object detection and fisheye cameras. We were detecting objects in footage from fisheye cameras at intersections, and the scoring there was F1 score. And finally, track 5, detecting violation of helmet rule for motorcyclists. We used mean average precision across all frames in the test video, ignoring small and redacted bounding boxes. The idea there is to detect not only whether people were wearing a helmet or not when riding motorcycles, but also their location in the motorcycle. Were they the driver? Were they a passenger in front of the driver or behind the driver, or things like that? So we used a leaderboard to encourage people to submit not just once, but multiple times to try to improve upon their own submissions, as well as to see how they stand against everybody else, and try to improve and get to the top of the leaderboard. Teams were allowed 5 submissions per day per track, for a maximum total number of submissions for each track of 20 for all the tracks except for track 4, in which we allowed 40 submissions. Now, the evaluation server automatically validated the submission format and sent back an error if the submission format wasn't correct. And the leaderboard and otherwise would evaluate the performance of the algorithm and provide a local score. Now, we did not reveal which team were at the top of the leaderboard. They were sort of anonymized until the end of the submissions. So during the submission period, you only saw team ID and their best score. But at the end, you got to see the full submission leaderboard with the team names as well. The leaderboard was available after submission close as well, and I'll present some results for both before and after submission. And finally, we had 2 different leaderboards. We had a public leaderboard and a general leaderboard. The public leaderboard assumed the teams wanted to compete for the challenges. And one of the requirements of that competition was that they would not use external data sets, and they would release their data sets public, or their codes publicly. Finally, if a team was not willing to do that, then they could submit to the general leaderboard. All right. So team submissions, we had quite a lot of submissions, 2,524 overall submissions, and that's a slight increase from last year, 42 additional submissions from last year. 134 unique teams that submitted results. That's a slight increase again from last year. Loaner submissions talks about teams that only submitted to one track, or only submitted one track one time, right? So they, kind of got discouraged and didn't want to submit again, or got busy or whatever. We had 10 of them. That's 1 more than last year. So overall, most teams did submit multiple times and improved their performance. And the average number of tracks a team submitted to was 1.33, which is a slight decrease from last year. So most teams submitted to more than one track. Finally, the tables here show you some statistics for the public leaderboard and the general leaderboard. For the public leaderboard, the number of teams submitting were 14, 9, 11, 52, and 43 for the different tracks. The number of submissions ranged from 67 to 829. And the mean number of submissions ranged from 6.09 to 15.94. So track 4 had a mean number of submissions of almost 16. So a lot of submissions for track 4, but track 4 had a maximum number of submissions of 40, whereas track 2 only had a maximum submission of 20, and the mean number there is 12.44. So a lot of teams submitted a lot of times for that track. Similarly, for the general submissions, which includes the public submissions, and it's basically all possible submissions, the track 4 had a mean number of submissions of 20.54. Finally, the graph over here to the right shows you the submissions sort of per day for the public and the general leaderboards. From the start of the competition to the end of the competition, we had 35 submission days, so slightly longer than last year by 3 days. And you can see people submitted throughout the entire time, but obviously submitted a lot more towards the end. You know, some teams returning from last year on tracks that were existing in last year, they were basically ready to start submitting right away. But some of the new tracks, you know, it takes time to develop algorithms to submit. And once teams got some pipeline working, then they started submitting towards the end, and we can see a huge increase towards the end there. These graphs show you the submission frequency per track and the team distribution. So we can see that there are some teams that submitted many times. For track 4, there are quite a few teams, probably around 15 teams that submitted all 40 submissions, so maximum number of submissions, and then it decreases. Track 5 also, lots of teams submitted many times. The other tracks, a few teams submitted a maximum amount, but the rest of the teams submitted fewer times. Oh, and the graph to the right shows you the percent submissions for different teams. So you can see some teams submitted many times. So it's almost a bell curve, but not quite. It's a little skewed to the right. All right. Now, finally, one of the things that the reason we designed the system this way is to encourage teams to submit multiple times, to improve upon their submissions, not just submit multiple times, but make improvements to their algorithms and design better algorithms, right? Not just submit using some new meta parameters to the algorithm that will give you slight improvements, but hopefully brand new algorithms that get you higher in the leaderboard and do better against the state of the art. And so this is what this shows you, the score improvement from the first submission. So number of teams with at least a 0.1, so 10% score improvement in one track, at least one track, is 82 teams. So 82 teams, based on their first submission and their final submission, were able to improve by more than 10% their score. 11 teams, and that's 12 teams more than last year, right? 11 teams were able to improve their score by at least 10% in 2 tracks, and 1 team was able to improve their score by at least 10% in 3 tracks, right? And then the tables to the bottom show you the mean and max score improvement for the public and the general leaderboards. All right, finally, we opened the evaluation server again after the end of the submissions, and you know, in the past we've seen quite a bit of activity as well after the end of the evaluation period. This year a little bit less, not so much, but still some people did submit. So we had 33 additional overall submissions after the end of the challenge, and 1 additional new team that submitted results, and no additional loaner submissions. All right.
Thank you, Professor Anastasiou. And we can see that actually this year the evaluation has been very challenging, because at the end of the challenge, we are seeing like a lot of submissions, and you see the system crash multiple times. But this is not, the fault of Professor Anastasiou. We just need a more powerful server in the next year, and we expect that the participation will be even more in the next year. So we will make sure that the submission experience will be more friendly in the next year. Okay, we are seeing also a lot of people are coming in, so if it's possible, we can also squeeze in and leave some empty seats on the site. Okay, so now we can share some observations we have for each of the challenge track. So for track 1, what most teams did is that they used the typical pipeline for multi-camera tracking, including the object detection, re-identification, single camera tracking, and clustering. But this year, the difference is that our evaluation is done based on 3D locations. So a lot of teams, they also run pose estimation. So when the body is being occluded, they can use the pose estimations to still estimate the precise location of the foot. So this is contribute to a lot of teams' high accuracy on our benchmark. Also, a lot of teams use advanced or like transformer-based models for object detection, re-ID, and pose estimation, and they show that these methods are very effective. So what the leading team did is that, first of all, they used the hierarchical clustering with appearance features and spatial temporal constraints to improve the clustering results. Also, this year, we have a bonus for teams using online multi-camera tracking method. So a lot of teams, when they do online multi-camera tracking, they have this global state of anchors that they define to ensure that the online tracking is smooth. Okay, so what we learned year over year. So first of all, this year is special because we encourage the use of online tracking methods. So the online methods will face challenges like computation, because for online tracking, we are mainly dealing with like streaming video feeds. So some of them with heavy computation may be hard to deploy in real world. And also we encourage teams to do large scale data exploitation. And also many of the teams, they presume that they know the number of people in advance, which is impractical in real world. So we encourage teams to do a dynamic management for future directions. So we will investigate the learning-based tracking methods using the graph neural network, which is GNNs, because we believe the learning-based method will lead to better robustness than just rule-based clustering. We also incorporate data sets with individuals in similar attire for more realistic scenario. For example, if we want to deploy the multi-camera tracking for sports events, like a soccer game, or in a factory where many people are wearing similar uniform, this will be very challenging, and we are planning to suggest that kind of challenge in the next year. Okay, let's welcome Tran. If you are online, you can present the observations for track 2.
Okay, thank you. It's clear for you to hear my voice or not?
Yes, we can hear you.
Okay, great. Thank you very much. And about track 2, similar for the track 1's observations. So the most team has joined our track to employ the vision language model based method for using. And we also found the leading teams, what did here is that they both use both the global and the local view to enhance the performance of the final perception result for the caption task. So basically, our data set provides the global view and provides the video with the instance labels information. So this global here means the whole frame information, and the local here means the instance level information. And also some teams did the visual text prompt engineer schema for the domain-specific task. So this is also very workable for the final result and will provide a very standard schema to how to do for the domain-specific task, especially for the track regarding the traffic safety. Extracting some hierarchical structures from caption as a pre-processing as also working. Leverage multiple informations and knowledge transfer across different traffic domains. Also another typical method some of our teams did in the challenge. So several feature directions First of all, a better evaluation system. This is very important. For this year's challenge, we use traditional metrics such as Blue Metro, Roger, and Cider focus on the syntactic similarity, but still very struggle to assess the semantic accuracy in Alliance's detailed captions. And we also hope the challengers or the persons who join the track in the future to explore the vision language model design, focus on the spatial temporal relationships, and especially the instance level to enhance the task performance. So we are thinking that the instance levels detailed information will help the model to do better. And sometimes a lot of methods still focus on the whole frame or whole video, but how to utilize the instance information is another important future directions. So this is the last sentence is that we found that even the vision LLM or the LLM-based method has a good ability in the zero-shot or generalization task in several downstream use case, but still we found that it still faces challenges in domain-based tasks, such as our traffic safety caption task. So we are thinking this is also a good direction to test more method regarding this kind of thing in the domestic tasks such as tracking. Thank you. Yeah.
Thank you, John. Okay, so we can continue to track 3. Let's see if Shaker or Professor Anush Sharma are here. If not, I can present for track 3 for them. So what most teams did is that they use a classification of different distracted activities such as phone call, texting, yawning, etc. And many teams apply temporal action localization to determine the start and end time for each activity. What the lead team did is that they utilized clip level video recognition, action probability, calibration or multi-view fusion, and adaptive thresholding algorithm module for classification, and also weighted boundaries, fusion, candidates, behavior merging, and multi-step processing algorithm was used for determining the start and end time, because that's the use for our evaluation. Future directions, first of all, we have annotations for each activity can be more refined for better localization. Cleaner ground truth labels can improve the development and evaluation of the research progress. And finally, increasing the data size further with adequate representation can improve classification results. This year, the data size increased from 30 drivers to 99 drivers, so it's a more challenging data set. Okay, Professor Gochu, do you want to present for track 4?
Again. So track 4, we so what most teams did. So obviously there are pre-processing and models and inference, and in these 3 steps, all the teams tried different approaches for pseudo labeling, image enhancements, like using diffusion model, NavNet, pseudo label, CycleGAN, stable SR, etc. For the model part, the most teams used ensemble models, including 3 to 9 models. And the backbone, they used YOLO and transformers. And in terms of transformers, like dynos and code DTR, etc. And in inference step, SAHI and histogram equalization for enhanced contrasts, etc., were used for improving the image quality for the detection. So what the leading teams did, the team 1 was used, they used the Vistron dataset on top of the fisheye dataset, and they also used the pseudo label based on the 3 code-editor models, and used ensemble of 7 models. The team 2 used stable SR ensemble of 9 models and histogram equalization plus SAHI. Team 3 used open vocabulary pseudo label dataset with even 5,841 images using CycleGAN, and used ensemble of 3 models, and also they used test time augmentation. So for future directions, so far we have identified it's probably, it is actually good to increase the size of the data set, but also most importantly, the diversity of the data set. And also the second thing we are pointing out is it's also important to aim resource constraint inference as well, because all the teams used like ensemble models consisting of multiple models, right? Okay, that's it. Thank you.
Thank you, Professor Gochu. So Pranamesh, it's your time now.
Thank you, Thomas. In the track 5, most of the teams since it requires like object detection, one of the first thing that they did was using again something like the previous tracks, using transformer models with ensemble techniques for detecting the various drivers or passengers who are like wearing helmet or not. And they use optimization techniques for class balancing, because the data set had a majority of the classes consisting of something like the drivers wearing helmet or not. Some of the classes which are passenger 0 or passenger 2 are not that frequently occurring. So therefore, they used like optimizer scheme to do this class balancing. Basically, then finally to have a trade-off in the precision and recall to have the best kind of accuracy that they can get using the, as I said, like this either transformer models or this like ensemble models that has been used. In the future, we in this year we introduced some videos where it's significantly congestion is there to handle to see how the teams are performing during occlusions kind of a cases, which can be further improved, and more such data can be included, and also like towards building like a real-time system using the inferencing, like so that we can have inferencing as a criteria for doing the evaluation, so that it can be used for more like a real-time implementation on the cameras. Thank you, Thomas.
Okay, thank you, Pranamesh. If that is you're done for track 5, then that concludes our workshop summary presentation. We thank you all for the attention. And now we have the privilege to welcome Professor Daniel Kremers from the Technical University of Munich from Germany. He's going to present to us the keynote presentation. So let's wait when we finalize the slides, and then he will be here. Welcome, Professor Daniel Kremers. Oh, okay. Yeah. That's the case. Okay. Oh, okay. Let me see if I can allow you to share screen. It doesn't show the option for sharing screen. Yeah, sorry about that. So we can take a 5-minute break if you need to use restroom or get some water, and we will 5 minutes. So currently it is 8:47. So it would be great if you came back at 8:52 a.m. Yeah, yeah. Oh, you also have the host name. Yeah. Oh, you can make him the also the co-host. Make co-host. Professor Kremers, could you try if you can share right now?
Instead,
Can people hear me?
Yes.
Is everyone back from the 5-minute break? Looks like it. Did I start?
yeah, I think so.
All right. Thank you very much for having me here. It's a great pleasure to be here. Apologies for the technical difficulties, but now.
Citation.
Oh, that's strange. Sorry, no, that's not. Stop share. There now. Go to the Zoom. Okay, I think now everyone should see, both online and here physically. It's a pleasure to be here. Thank you for having me. This is on large-scale dynamic scene understanding, and I think very much connected to the topic of this workshop. Let me start by telling you how we got into this whole field of dynamic scene understanding. We started roughly 20 years ago, in fact, in the field of driver assistance and autonomous driving, working with, at the time, the company Mercedes. We started putting cameras into cars. This is footage from 2005. So as I said, about 20 years ago, trying to record what's happening around the car, in front of the car, trying to develop algorithms such as these, starting from, as you can see, 2006 and onwards, algorithms to understand the world around the car in order to avoid accidents, in order to see obstacles, to, as you can see here, estimate their 3D motion so as to allow predictions of where things move in time, so as to anticipate what's going to happen and therefore avoid accidents and save lives. And this laid some of the foundations of what is now being pursued in the field of driver assistance and self-driving cars. A lot of the technologies we developed at the time were actually integrated into the cars in Mercedes and in other companies. But nevertheless, the field of autonomous driving has been slow in the making. You know, we started 20 years ago, and it just took years and years, and is still taking years. And it's hard to say what exactly is the bottleneck and what blocks this development. But what I see is that the field of automated driving is picking up quite some momentum in the recent years, both with legislations being put in place in different countries that enable self-driving or different levels of autonomy, but also with technologies by companies like Waymo or Cruise or Aurora or others that are deploying technologies in the markets, Tesla. Right? But still, to date, something that kind of prevents these techniques from scaling across the globe, that it is very hard to test and validate these tech stacks. So you develop a self-driving tech stack, and then what? And then the problem is really how can you assess the performance without causing accidents and killing people? This is, I think, a big challenge, and also how can you improve the performance? And one of the caveats is you can obviously go into a simulated world and test your algorithms in the simulated world, but how do you know the simulation is like the real world? And something that we must admit here is that the world we live in is just a very complex, dynamic world. Things move around, you know, cars, cyclists, pedestrians, they move around, and I think self-driving cars to date do not fully understand how humans behave in traffic. And I think this is important in order to enable self-driving cars. And I think this is to date the big differentiator between a self-driving car and me as a human driver. When I drive down the street, I have a very clear model of how things develop, right? How people move, how things, I can anticipate what people are likely going to do. And I believe self-driving cars to date do not have that capacity. And the issue is really, it's complex, right? Every human behaves differently. Just a simple example, you all know this from everyday life. You drive down the street and then the traffic light turns yellow, right? There are two kinds of people in this world I've learned from driving, right? There's the ones that accelerate, why? Because it might turn red, right? And there's the other group that slow down, why? Because it might turn red. So for the same reasoning, you get very different strategies that people pursue, depending on whether they're more aggressive, whether they're more in a rush or less so. I tend to actually accelerate when things turn yellow. I find not everyone does, and it's important to have this complexity in mind and to know that there are different kinds of drivers and to know that the behavior of humans in traffic can vary enormously across countries and cultures. This is the reason why I, as a German, do not typically drive in southern Italy. I don't have to go far from Munich to go beyond my comfort zone, to go into a regime where I don't have the right priors, where I cannot anticipate what people are likely going to do because they do crazy things in different countries. Or if you go to Mumbai, or, I've driven around in China, right? But not me at the steering wheel. It was my Chinese friend because he knew the country. He knew how people behave. He knew that in pitch dark, there would be bicycles, swarming around the car from both sides, right? I went crazy just sitting there thinking, oh my God. But yeah, driving can take lots of forms in different countries, and a self-driving car, you cannot just take one single self-driving car and hope it's going to work in Mumbai or in Delhi or wherever, right? You have to introduce priors, you have to introduce knowledge. And what does that take? It takes for us to really understand the world we live in and acquire that information and knowledge. It's about capturing the 3D world, and it's about capturing what happens in that 3D world, and this is what I'll talk about. So there's going to be two parts. Capturing the 3D world is something that we worked on a lot, and also capturing the dynamics. Now, when it comes to capturing the 3D world from cameras, obviously you can use LiDARs, you can use many sensors, but I am a firm believer in the camera as the lead sensor of a self-driving. And why? Because humans predominantly rely on their eyes as well to perceive the world. We don't have LiDAR, we don't have radar, we don't have ultrasound, and yet we can drive. And cameras, in the same vein, give you so much information about the world. Sure, if you have more sensors, you should use them. But I think we all agree, being at a computer vision conference here, that the camera might be the most powerful sensor. But how do you get 3D from cameras? This is a very long-standing problem, and you'll be surprised it's much older than computers. In fact, I've often read, this problem of bundle adjustment, where you reconstruct the movement of the cameras and the 3D world together, right? Everyone knows this, but when you hear about it, when you learn about it, like in my case, they always say, oh, bundle adjustment has been known for a long time. And then I say, how long exactly? Then they say, oh, I think someone did it in the 50s or something. But often there are no references, and even Wikipedia is fairly shallow when it comes to the origins of camera-based reconstruction. So I dug a little bit deeper, and these are some of the leading pioneers in this field. You may not have heard of them, but let me give you a bit of history on where we all come from, where the reconstruction of the world from photographs started. So there is Edouard Dolezal, for example. He's the founder of the International Society for Remote Sensing and Photogrammetry. And photogrammetry is this field of measuring things from photos, right? And this was a society that he founded in Vienna in 1910. And then there is this guy, Sebastian Finsterwalder. He is the pioneer of what's called analytical photogrammetry. So they didn't have computers, so they actually analytically computed 3D structure and camera motion from photographs. And some of these calculations took them years, right? We are always trying to get things to work in real time. They took like 3 years to do a reconstruction of parts of the Alps from photographs. And so he's considered the pioneer of analytical photogrammetry. And by the way, something I stumbled over in the process is that he was a professor at TU Munich, the place where I am today, right? And so it feels nice because we're really stepping in the footsteps of our ancestors. Same Karl Renner, he's a mathematician who used vector algebra, and he really pioneered the use of perspective and projective geometry in this whole setting. And then there's Otto von Gruber. He developed these least squares linearization techniques that we all use when solving the bundle adjustment problem. And by the way, Otto von Gruber was also a professor at TU Munich. And in fact, the founder of TU Munich was a geodesist. So, you know, this is in the wake of, in the process of studying the history, I realized where I am is really the exact right place to work on bundle adjustment. It's the birthplace in some sense. And then the two guys who really got things going are these two guys below, Helmut Schmidt, who came from Germany. In fact, he came in the team of this missile rocket engineer, Wernher von Braun, in 1945. So in some sense, you know, this is all very much tied to the history of the 20th century, how things evolved and how, you know, in the wake of the Nazi regime, a lot of really talented people left Germany, emigrated to the United States and took technologies and ideas along. And in the US, Helmut Schmidt, he had actually developed this whole framework of large-scale bundle adjustment to solve these camera reconstruction problems. He teamed up with Duane Brown. And Duane Brown and Schmidt together in the 50s, they deployed these methods on the first large computers of their time. They had some of the most powerful compute in the time, nothing compared to your smartphone today, obviously. But they deployed these techniques and they thereby laid the foundation of computer-based bundle adjustment. And how does that work? This bundle adjustment that, in fact, Duane Brown and others called the so-called bundle method. And later it was coined bundle adjustment because you have these rays of light, bundles of light rays that you try to adjust to make things consistent. And typically what you do in bundle adjustment, this is something you likely know from your own classes, is that you have a set of unknowns, the parameters of the cameras, the parameters of the 3D points, the landmarks, and then you have some loss functions, some nonlinear least squares where you have these residuals on these unknowns that basically say the projections of these points into my images should match the points that I see, this classical concept. And then here's how this proceeds. And this is, in fact, what I mentioned, Otto von Gruber, the linearization that he developed here for these techniques, is you linearize. You assume that you have a rough estimate of all these parameters, and then you linearize around this estimate, let's say the initial one. And then you have a constant R0 and then the Jacobian J. And once you plug that in here, you get a least squares problem to estimate the updates delta X in your unknowns. And then you update these iteratively. And so once you do that, you get this kind of least squares problem for the updates in the poses and the landmarks with the respective Jacobians here, right? And then you typically add a damping or regularization to say that the update shouldn't be too large, right? So you have this additional regularizer that creates out of it what is then often called the Gauss-Newton method, or the Leeuwenberg Marquardt more specifically. This would be Gauss-Newton here, and with the damping, it's often called Leeuwenberg Marquardt. So this is the loss function that you need to solve. And traditionally, and you can read up on that in all the papers from Duane Brown and later in the 50s and 60s and 70s, This is techniques that these pioneers developed. This is how it goes. You solve this. You basically, since it's a quadratic problem, you have this linear system that you need to solve with the so-called system matrix, and this is then in total called the normal equation that you have to solve to get the updates in the landmarks and the poses. So far, so good. The problem is these problems are huge, and even Dwayne Brown in the 50s spent a lot of time studying this system matrix. What it looks like, it typically has this form where you have a diagonal matrix for the largest block on the landmarks, gazillions of points in 3D, and then you have typically smaller amounts of camera pose parameters, and then you have this kind of sparse matrix structure. It's sparse, but it's not easy to invert. And just inverting this matrix is not easy. So people have introduced in the subsequent years this technique from linear algebra called the Schur complement trick. What it does is it basically decomposes. It shows that this full problem is equivalent to two smaller problems of this form, where you have one problem in the pose updates, and then once you have estimated the pose updates, you have an update in the landmark parameters. And this is quite a beautiful trick because it allows you to decouple the structure and motion problem in terms of first estimating camera motions, the poses, and then in alternation, you can back substitute in order to get the landmark update. And this is actually equivalent to solving this equation. The key bottleneck is the one that I highlighted in green, because even that Schur matrix, as it's called, is a large matrix, and it's structured. It's structured, it's sparse, but it's typically very hard to invert. And in fact, this inversion is the computational bottleneck. It takes a lot of time, and that slows down the bundle adjustment if you really try to solve big problems. And we're getting into an age in computer vision where we have big problems, where we have thousands of images and thousands of millions of landmarks. So these are gigantic problems, and you want to solve them fast. And typically, the way you solve this this problem here, the green one, is that you use a conjugate gradient method, an iterative solver to solve it, and then you use either an explicit or an implicit conjugate gradient method, and this is what's implemented, for example, in the well-known Ceres solver for bundle adjustment. And that's what people have been doing for years and years now. And what we've been looking into over the last couple of years is there a better way to solve this whole problem, to solve the bundle adjustment problem? Better in terms of maybe faster, more accurate, and more memory efficient. And we will see in the following slides that yes, there is. This is work that was developed by a number of my students. One of them is Nico Demmel with his papers on what he calls square root bundle adjustment. That changed a lot about how you do things. So what he advocates, I hope the microphone is still, sometimes it switches off, I don't know. Yeah, thank you. Let's hope it comes back on. Yeah, so he introduced null space marginalization as a way to solve the landmarks, and that accelerated things significantly. And there were two papers on this. And then we introduced a method that I want to present in detail today, and this is a technique that we call power bundle adjustment. And it, there are basically three benefits of this technique. First of all, the contribution in this work is that we propose to solve the large-scale bundle adjustment problems by using a power series extension of this Schur complement matrix. So basically, you need to compute the inverse of the Schur complement. That's the bottleneck, right? And we show that this can be approximated by a matrix power series. Secondly, we prove that this approach converges, so that it actually reproduces the same as the original approach. And then we show experimentally that this power bundle adjustment outperforms the existing state-of-the-art algorithms in terms of speed, accuracy, and memory footprint. And here's how it works. And this really takes you back to possibly high school. This is something that I teach my children, you know, we have 3 children and they're always hungry, right? And so I teach them, if you want to have food forever, this is how you go. You bake a cake, and then every day you eat half of the cake, right? A classic. And what happens is you have cake forever. That really amazes them initially. You can see how you can chop it up, and every day you have a little bit of cake. Obviously, it gets less day by day, but you have infinitely much, you know, you can eat cake until infinity. And this is called in the simplest form, is a version of what's called the geometric series. 1/2 plus 1/4 plus 1/4 plus 1/8 plus 1/16, etc. If you take this infinite series, it adds up to 1 full cake. And this is what you get here if you take r equals 1/2, right? Then you get this, right? And in fact, if you start from 0, then this sum will be 2. And this is a generalization of this for any r from -1 to 1. You have this kind of identity that the sum of all the powers of r is the same as 1 over 1 minus. What I didn't know in college and never learned, and this is something my student Simon Weber pointed out to me, is that the exact same result exists for matrices. So if you have a matrix m by m, and you see this only works for something that is somehow bounded. In the matrix case, you say the norm, in the sense of the largest eigenvalue of this matrix, should be bounded by 1. If that is the case, so it has the same radius as the scalar r here, right? 1. If that is the case, then you can expand 1 minus m inverse into this kind of series. And you can have a summation from 0 to infinity, or you can truncate at some value little m. And then you have a residual, the remainder, right? That's the remainder of the sum from m plus 1 to infinity. And what you can show is that this r is bounded by something that converges to 0. So if you let little m go larger, this approximation of 1 minus m inverse gets more and more accurate. And that's exactly the approximation we'll be using for inverting this Schur complement. And here's how that works. So here's the Schur complement matrix if you write it out. And then we pull out the u, and then you see something interesting. Inside the brackets, you have 1 minus a matrix. Right? So if you invert S, then you get this thing, 1 minus some matrix inverse times u inverse. And u inverse is easy to compute, that's fast. But this is the thing that is hard to invert, right? The one that couples u and w with different blocks. And now here we can deploy this result. We can say if mu, the eigenvalue of this matrix here, is bounded in the interval 0 to 1, then we can approximate S inverse exactly with this power series that we saw earlier times u inverse. So this is the term 1 minus this matrix inverse that we expand into a power series. And matrix power series are beautiful because you just have matrix multiplication to do. This is something that is very fast on computers. It's not a matrix inversion. So instead of inverting this matrix, we just have a sum of products of matrices. This is very fast and very memory efficient to do. And let's call this approximation to order m. We call it SM inverse, S inverse m. So the m's order approximation of this S inverse. Then we have this result. So first of all, we have the result that this is an approximation of the inverse Schur complement. And secondly, we have a convergence result, not only for the matrix inverse, but for the updates that we have in the paper, where we show if you compute the update in the post parameters with this S inverse of order m, then this update converges to the update, to the correct update in the post parameters as m goes to infinity. Which means if we take higher and higher order approximations of this power, in terms of this power series, we get better and better approximations of the update for the post parameters. And so this is what we'll do. And now the question is, someone was asking recently, I gave a talk, and then Michal Irani asked, how do you choose M? And there is a way to choose M. This is what we detail in the paper. Basically, if this is the inverse of the Schur complement approximated to order M, we can basically choose a stopping criterion for this approximation where we say we want M such that the update, the change from xm to xm minus 1 should be, compared to xm should be smaller than epsilon. This is a kind of the same stopping criterion that you have in inexact Newton. And what you can then derive is you can show that if you sum up all these updates, the average pose refinement is xm over n plus 1. And so once we choose this as a stopping criterion for M, we are sure that the error we make is small in that sense. Now, if we apply this to large-scale bundle adjustment problems, there is a nice data set called a BAL data set, bundle adjustment large. We see that we're significantly better. So here's plots that show the runtime of our method. And basically, you solve this bundle adjustment problem to a certain tolerance: low tolerance, high tolerance, and very, medium, high, and very high tolerance. And you can read these plots in many ways. We compared here to the various state-of-the-art solvers, the square root bundle adjustment, and the various forms of the Ceres solver, the conjugate gradient solver, preconditioned conjugate gradient solver. And this is then the power bundle adjustment, both in 32-bit and 64-bit. It's important because if you want to run this on a GPU, it should be compatible with a 32-bit implementation. And this is what we see. And so these plots can be read in many ways. For example, you can say that for a tolerance, let's say medium tolerance, we are faster and more accurate, right? So on the x-axis you have time normalized. On the y-axis, the percentage of problems on the BAL data set which you can solve to that tolerance. And you want to be in the top left corners, meaning you want to solve as many problems as possible through that tolerance in as short a time as possible. And you can see we're significantly faster to reach a certain precision, and we also end up being more accurate if you need a certain tolerance. For very high tolerance, for high accuracy, meaning small, very small tau, we are still significantly faster, but not necessarily more accurate. So it kind of depends a little bit to what tolerance you want to solve this problem. But in practice, you're often interested in medium and high tolerance, whereas the very high tolerances you're not so interested. But you see, if we really take it to the limit, we see at some point this power series approximation isn't the method of choice necessarily. Something that obviously you can conceive of is developing hybrid techniques that start with a power series approximation and then switch to a conjugate. Here's convergent plots on two BAL problems. So there's about 100 problems in the BAL data set. This is two of them. Here's the runtime, and here's the error, how it goes down. And you can see again that it is significantly faster independent of which tolerance you impose. So if you choose different tolerances, you see that this power bundle adjustment converges much faster. And this is basically what we set out to do, to show that we can do faster. What came a little bit, I think, as a surprise in a closer analysis is that it's not just faster, but it's much more memory efficient. This is what you see here. On the x-axis, you have the number of the observations in the millions, right? On the y-axis, you have the memory footprint of the respective methods, and you see they are linear in terms of memory consumption as a function of the observation numbers. But what you see mostly is that both for small problems, we have much better memory footprint, but also for large problems, this power bundle adjustment uses much less memory. And in fact, significantly less. It's like 5 times less than the square root bundle adjustment, and it's twice less than the series. And this is important because very often we find the real bottleneck to scaling a bundle adjustment to big problems is not so much the runtime, but the memory usage, because at some point the GPU hits the memory and then see. All right, so this was about power bundle adjustment to reconstruct a static world from cameras. Now I want to go into capturing the dynamics. This is the second part of my talk. And as I mentioned, this is important because we need to understand how do humans behave in traffic before we can deploy self-driving cars. And the question is, how do you get that information? And there are many car companies on the West Coast who boast themselves of having driven millions of miles. But then I say, what have you really seen in these millions of miles? Mostly nothing. You just drive down the street and you never typically see an accident unless you're actually involved in one, which you really try to avoid. And moreover, you don't understand traffic because if the car, you all know this, if the car in front of you or the truck, it brakes, you don't know why the car broke. You don't see what that car sees. You don't have the complete picture to really get an understanding of how humans interact. This is a complex interaction. We'll see examples. So what we advocated in a startup that we created about 2 years ago is that we should move from car vehicle data like this one to surveillance or aerial data, because it gives us a much better perspective of what's happening. It gives us a more of a bird's eye view of traffic. And the way the deep scenario tackles this problem is in multiple steps. They first reconstruct the 3D world with bundle adjustment like techniques from images. And then they train neural networks to track all the obstacles, trucks, buses, cars, cyclists, pedestrians in 3D. And 3D is important. Why? Because like if you take examples like this one, if you do a 2D projection of the scene, seen from your camera, whatever perspective you have, it looks like the car actually crashed into the truck. But if you reconstruct the objects with 3D bounding boxes, like you see on the right, then you see in a projection on the plane that they don't even touch. They didn't crash. And this is important, right? If you do traffic monitoring, you need to have a centimeter precision that really can distinguish whether two obstacles had a collision or not. It's a big difference. And in fact, what we find is that indeed our neural networks do exhibit, even though we have images taken from 100 meters up, they exhibit a precision where we can have bounding boxes with about 1 centimeter, accuracy in the order of centimeters. These are evaluations where we show what is the actual width compared to what our bounding box estimate that we determine. And so as you can see, the errors are in the range of centimeters. Here's some examples. This really works on a massive scale. So we can, as you see here, track hundreds and hundreds of vehicles and pedestrians and cyclists. And we can see maneuvers like a car in the middle here trying to merge into, or things that you should not do. Don't try this at home. We see crazy driving maneuvers that people do. I'm saying crazy. If you're from China, you'd say, oh, totally normal. But for a German, this is pretty crazy. And you see the interactions here between, vehicles, cars, trucks, cyclists, pedestrians. They're all labeled, so you have identities. You have different bicycles and pedestrians, and you see how cars try to turn and negotiate their way. Here you see an accident. Right? This car goes, and there are people crossing. The other car tries to go as well, and you see a lot of this is footage from the US. You see, so the company actually hires and records data in many countries, depending on the customer's needs, right? And here you see people just driving through the turning traffic. Again, something I do not recommend. How can this data be used? Well, first of all, you get all this data, you can learn how people behave. Another example of an accident, someone who decides very last minute that they need to go left. And obviously they're on the right turn or straight going lane and creates an accident. But then you can feed simulations with the data we record. And so you have a simulated world where you can first reproduce the accident, yeah? But then you can train, driving behaviors for your self-driving car, which in the exact same scenario would not run into an accident. And this is how we see all of this data can benefit the automotive companies. They can have data of what really happens in the real world, and we can populate simulations such that we have a simulation. We can simulate all the sensory data from every different agent in that scenario. And it's a simulation where every single agent is copied from a real human. So it's not hallucinated, but this is real human behavior that we can feed into the self-driving text. And we can go more, and this is the vision of deep scenario, that we can take all this data from vehicles, from surveillance, from aerial data, and populate a 3D foundation model that then serves endless applications in automotive, in transportation, and in logistics. And I'll give you one more example of a project we recently did together with Intel. And this is a problem you all know. You come to a parking lot, and some people park crazy. Which spot did you want to take, the left or the right? Go right in the middle. And this is a problem. And there are countries who want to, make this a violation, a traffic violation, that you block two parking lots. Right? And how do they do it? Well, at this point, they have humans that have to go around and take note of the parking violations. And if you have gigantic traffic lots, good luck with that. It's a huge amount of manpower in order to pursue these traffic violations. Then you can say, okay, let's just train a 2D car detector. Well, it turns out that doesn't work. If you get 2D bounding boxes like so, how do you know which car is parked properly? You can't just take the bounding box and somehow intersect it with the parking slots. But it turns out if you have 3D bounding boxes, then you can go. Then you can do it if they're sufficiently precise. And as I mentioned, the technologies of deep scenario allow you to really get 3D bounding boxes at centimeter precision. That will enable you to really automatically determine parking positions. So this is where you need 3D bounding boxes and 3D computer vision to and so we can take streams from monocular cameras, and this is a collaboration, as I mentioned, with Intel Scenescape and OpenVINO and Deep Scenario, where we basically show that we can do 3D bounding box detection, and we can leverage this for 4D object tracking. And we can determine traffic violations in real time on edge on the existing infrastructure. And the aim is to deploy that to pretty much all the parking lots. So, well, it's a screenshot from a video. And so we can go from 3D detections to automatically assessing traffic violations. Basically saying if it intersects significantly with the separator line in a projection on 2D, then it is a traffic. And we see that this 3D detection outperforms the commonly used 2D detection in every dimension. It gives you higher robustness on existing use cases. It's deployable on existing infrastructures at no additional computational cost. And you have a lot of use cases that it enables, things like automatic valet parking. You can have the cars parked automatically, and you can have this algorithm to verify that everything is proper, that the cars are properly parked. So we have a lot of customers, both for the traffic acquisition, but also for this parking violation detection. Companies like Aptiv, Audi, Bosch, Hexagon, Mercedes. So, and there's a lot more information at Deep Scenario. If you're interested, they're always interested in potential customers, but also potential business partners. That's it. Thank you for your attention.
Okay, we can open the floor for a couple questions for Professor Kremers. Anyone? If you have question, you can come up here. Yeah. Yeah,
Or-
you'll be, because
Or you can just say it and I'll.
yeah, we can
I'll
repeat it.
basically
Yeah.
repeat it. So a good point. I didn't go too much into detail for time reasons of how we do the 3D bounding box detection in the second part of my talk. It is basically using suitably trained neural networks. One of the key practical challenges is, in applications, we fly at different altitude. So you can obviously train a neural network to detect 3D bounding boxes from a certain altitude. But then what happens with the performance of this network if you fly at different altitude or different angle? And then obviously cars look different depending on the angle and the altitude at which it's filmed. And we cannot always take the same altitude and we cannot always take the same angle. Sometimes for legal regulations, for example, in the US, you're not allowed to film above an intersection, which somehow is a good regulation because if the drone, dies, it crashes on the intersection. So in the US, you have to film from an angle that makes it challenging. Or if you then want to tap into surveillance cameras, which we do now, it's yet a different angle. And so the big effort goes into somehow normalizations that allow the same network to be deployed on multiple altitudes and multiple angles, because we cannot retrain it for every angle and every altitude. This is not scalable. So this is kind of a key challenge where I help them, assure a normalization that allows that one single network, much like the Highlander, you have a single network to work on. The input is we train it with ground truth data. Images from a certain altitude and a certain perspective, and then ground truth.
But I'm asking about a picture. Is primarily used like a infrastructure thing for autonomous driving, or will it actually help to train autonomous models?
I think it's really designed to help autonomous. Also, the question is whether it's just an infrastructure challenge or whether it's designed to help autonomous driving and autonomous agents. Our vision is here to serve, as kind of this indicates, multiple potential applications. There's a slide. This one that tries to bring that across. There are multiple applications that we try to fuel, but the main one is indeed self-driving cars and providing them with an understanding of how agents around them behave. If you project yourself into the future, 20 years down, then every car will be self-driving and they will be somehow synchronized in the cloud, so they will know exactly what every other agent is in the process of doing. And they can align their strategies to a common one to maximize flow and throughput. Then it's easy. But for the coming many, many years, any self-driving car will typically share the road with human drivers. And sure, human drivers will sooner or later be replaced by an automatic one. It's solved. But we still, for many years, will have in downtown pedestrians and cyclists. You cannot have a self-driving bicycle. And so for many years, self-driving cars will share the road with humans in many ways. And if they don't understand how humans behave, then they cannot anticipate. And for me, safety in driving comes with being able to anticipate. And this is also why experienced drivers have much less accidents than young and inexperienced drivers, because inexperienced drivers do not have the that experience and knowledge about how humans typically behave. The more you've seen in the world, the more you've driven on roads and experienced other humans, the safer you're driving, because you can anticipate what people are likely going to do. And this is the anticipation that is really crucial for self-driving cars, and it comes with data. Data like the one.
Thanks, I have a question about your behavior model. You mentioned that because you can learn behavior, then you're not hallucinating. But my question is about the limits, where if the model is not what else then all of a sudden it's in the middle of the passage where you might not tell that it's a scenario. So then is it enough of a data, because those are simulated answers at this intersection, and that's almost happening. But then on the other side of the other characteristics.
So the question is about behavior modeling and whether what we do is sufficient for behavior modeling. I want to clarify indeed, in what I've shown, we are not modeling the behavior, we're just generating data. That is then the subsequent step that we're exploring ourselves, but also with partners, in whether we can develop complex agents that models of human behavior that can kind of match the data we see. The question is now, do we always have data for everything? We may have a data of the accident, but do we have data of what would have happened if we had done something slightly different? Possibly not, but with more data, we get better and better models of how we interact. This is our strong belief. This is also why we need a lot of data. Why it's not a one-time thing, and this is why deep scenario records hours and hours of footage to really have a lot of accidents and a lot of really critical scenarios in the data. And we also develop techniques to mine and process this data. For example, we have a technique that allows us to automatically detect accidents. So we don't have to sit you in front of the video and watch our bounding boxes move around for hours and then say, oh, you're on 1 hour, 35 minutes, 23 seconds, there's an accident. No, we can basically prune the whole data set automatically to critical scenarios, and that's exactly. Question in the back? So the question is, how does bundle adjustment handle dynamic scenes? It doesn't. It's designed for classical bundle adjustment, assuming a static. Obviously, if you wanted to reconstruct the dynamic world, you would have to generalize the whole thing. You'd have to, and then the question is, what do you mean by dynamic? And there's obviously many kinds of dynamic. Do you have predominantly a few rigid bodies in the scene that move around, or do you have non-rigid motion? Dynamic scene reconstruction is a complex challenge, and there's a lot of techniques, methods out there. This technique was really numerics for solving this nonlinear least squares problem. Meaning, if you can phrase your dynamic scene reconstruction into a problem of nonlinear least squares, and you can, and then it should also accelerate.
Okay, I think you should.
Thank you very much.
Yeah, let's give Professor Kenneth a round of applause. Thank you very much. Thank you. Yeah, actually, this is the second time that Professor Daniel Kremers as our keynote speaker, and you can see that after 2 years, we have seen a lot of new advances of his research, including the 3D foundational model and a lot of those cool things. And we look forward to have him come back maybe in the near future to introduce his new works. Okay, so now we will move into the presentation of our workshop papers. So we have 5 challenge tracks. We will start from track 1. We have a total of 30 accepted papers. In track 1, we have 7 accepted papers. So let's take a 5-minute, like a water break. So we will come back around 9. 45 a.m. And then so the speakers for track 1, please come up and we can check your slides and things like that. And we also want to let you know that in the afternoon we have a panel discussion. So for the panel discussion at 3:15 p.m., there will be a panel discussion on ethical AI that Professor Daniel Kremers will come back and we will have a panel discussion on all the interesting topics. Yep. So for all the track 1 speakers, please come up and we can check. I think. Okay, hi everyone. Let's get back to our attention. So now we will start from the presentation of track one. So for track one, let's start with the team from the Yachiro Engineering company. And so they will present their method on overlap suppression clustering for offline multi-camera people tracking. Let's welcome.
Okay. Yeah. Good morning, everyone. My name is Ryuto Shida. I'm a member of Yachiro Engineering, a Japanese civil engineering company. Today, I will talk about our multi-camera people tracking method that achieves the highest HOTA in this challenge. Let's begin with the objective. This photo is a photo of Azabdai Hills, which our company designed. For civil engineers like us, pedestrian trajectories are important data in the management of cities. On the other hand, obtaining this data is a challenging task. Therefore, we aim to establish the most accurate tracking method regardless of the pressure from this challenge. Allow me to introduce the content of my speech. I will start by explaining the primary concepts for tracking in the introduction. Then, I will introduce the details of our tracking methods. And finally, I will show you the results of the experiments. Let's begin the introduction. Generally speaking, multi-camera people tracking has three components: object detection, and object tracking, and re-identification. Especially the object tracking algorithm, as well as the re-identification algorithm, are essential components in multi-camera tracking. In this challenge, we focused on improving object tracking algorithms and re-identification algorithms. Typically, two types of single camera tracking methods are employed: motion feature tracking and appearance feature tracking. Our method uses the appearance feature-based tracking algorithm. We are proposing a new single camera tracking algorithm with high performance. In addition, a multi-camera tracking uses the similarity of the appearance feature too. This study proposes different algorithms in single camera tracking and multi-camera tracking. Up to this slide, I have presented our primary objective and basic approach of multi-camera tracking. Moving forward, I will explain the four main concepts of our works. This slide shows an overall picture of our method. In preparation, we perform frame extraction, people detection, pose estimation, and feature extraction. Single camera tracking and multi-camera tracking algorithms are essential to our method. Now, moving on to the aforementioned concepts. Our single camera tracking process is based on hierarchical clustering. Our first concept, accounting for time overlap, can significantly enhance clustering accuracy, which acknowledges that the same individual cannot occupy two or more places simultaneously. We call our tracking method overlap separation clustering, which has high performance for single camera tracking. The second concept is how hierarchical clustering, particularly with average linkage, mitigates misidentification in the re-identification process. While there might be instances where the cosine similarity between individuals could be moderately high, it typically tends to be low overall. This is the reason we use average linkage as a re-ID process. The third concept is that we use only highly identifiable images for clustering. In the clustering process for re-ID, noisy images, those that are dark, occluded by other people, or by foreground objects, or low in resolution, tend to introduce tracking errors. These images needed to be eliminated during initial clustering. Our method assesses identifiability based on pose estimation results. Images with high confidence in each key point are deemed highly identifiable images. And the last concept is that low identifiability images can be classified more correctly by assigning them to different clusters. In conventional clustering, these images tend to form a small cluster composed only of these images, or form a large cluster composed of different individuals. On the other hand, by assigning low identifiability images to existing clusters, this
Excuse me, I think the screen sharing is not turned on, so we're on Zoom.
on Zoom.
Oh, my apologies. Yeah, sorry about that. Let's share the screen. Okay, let's continue. Oh, sorry. Okay, you may continue.
okay.
Excuse me. I think the sharing is not the right screen. Let's stop sharing and then share again. Should be screen 2. Okay, please continue. Sorry about that.
In conventional clustering, these images tend to form a small cluster composed only of these images, or form a large cluster composed of different individuals. On the other hand, by assigning low identifiability images to existing clusters, this process maintains the cluster number. This process gives substantial tracking results. Our single camera people tracking method begins with the conventional hierarchical clustering, using single linkage as the initial step. Regarding video data, temporary neighboring images of the same individual exhibit high similarity. As a result, employing single linkage clustering with a low epsilon is considered a reasonable approach for tracking. However, hierarchical clustering may result in misclustering, particularly between occurrent individuals or those with similar appearances. Identifying misclustering based solely on appearance features is often challenging. Instead, we leverage discontinuities in coordinates or time overlaps to detect and correct such results. Our method aims for ideal tracklets, each containing only one person per frame. We distinguish time overlapping images as separate individuals. This separation process uses a combination of graph theory, centrality, and motion features to identify discontinuities and subsequently split tracklets into distinct entities. For further info, please refer to our paper. In the multi-camera tracking process, our method performs hierarchical clustering with average linkage, using only representative images from each tracklet. This hierarchical clustering process uses highly identifiable images to accurately spread the cluster. The representative images are selected by the pose estimation. If an image has high confidence in each key point, an image is considered to be a highly identifiable image. After clustering, this process assigns low identifiability images to these clusters. The image shown on the top right are examples of low identifiability images. Typically, these images causes tracking errors. In contrast, our two-step clustering process, initial clustering using only highly identifiable images, followed by the assignment of low identifiability images, helps maintain the cluster number and prevents mistracking. Up to this slide, I have introduced tracking methods. Moving forward, I will talk about experiments using our method. We do not train model in this challenge and instead use the champion model from last year's challenge. In light of this, we have considered that there may be better models than the one we used in this year's challenge. Finding the best possible model is among our future goals. This table displays the summary of the track 1 leaderboard. As you can see, our method achieves the highest HOTA. This table presents the results of the aberration study using the validation dataset. Our final results incorporates world coordinates into the algorithms. However, obtaining data with world coordinates is challenging in real scenarios. Without world coordinates, our method still achieves 61% of the high HOTA score, suggesting that our method may have high robustness when applied to real-world data. The contribution of this study can be summarized on the screen. Our framework achieves the highest HOTA of 71%. And this slide shows our future works. In this challenge, our team didn't consider computational cost. So we plan to carry out to reduce computational cost. Thank you for your attention.
We will have a Q&A at the end. Yeah. Sorry, I apologize again for forgetting to share the screen at the very beginning. Okay, now we can continue to the second paper, which is from the paper ID number 1. Should be opening. This. This one. Sorry. Okay.
Hi everyone. Today I'm very glad to present our paper as a proxy presenter, a robust online multi-camera people tracking system with geometric consistency and state-aware reality correction, representing our team SJTU Lenovo. Our members include Zheng Yuxie, Zilin Li, Wenjie Yang, Yuan Zhang, Yang Chen, Yang Zhang, and Xiao Ma. Multi-camera, multiple people tracking is a crucial technique for surveillance, crowd management, and social behavior analysis, enabling large-scale monitoring and comprehensive understanding of complex scenarios, including multiple individuals across different camera views. In the 2024 AICT Challenge Track 1, participants are required to track people across multiple cameras using an expanded synthetic dataset. This year, the scale of the dataset has been significantly enhanced to around 1,300 cameras and around 34 people to be tracked. Another facet of this challenge track lies in its encouragement to use online tracking. Where methods rely solely on the information from past frames to predict current frame results. Submissions that incorporate online tracking methodologies would be granted a 10% bonus to their HOTA score when determining the winner and running up. However, there remain 3 main challenges in the field of multi-camera online pedestrian tracking that are yet to be addressed. The first one is how to accurately match individuals across different cameras. This challenge can be exacerbated in densely populated scenes where high levels of detection noises significantly influence accuracy. The second challenge is the ID switch problem. and a new target initialization problem due to severe occlusion. As illustrated in our example, following a severe occlusion with a woman labeled number 20, the little girl originally labeled number 24 experiences a missed detection, which subsequently leads to an ID switch, where the woman is incorrectly assigned the ID number 24, while the little girl is mistakenly reinitialized as a new target 34. Another challenge lies in the re-identification of pedestrians with various poses and angles. When the appearance of individuals varies significantly across different viewpoints, and there's no temporal overlap to rely on, the task becomes notably challenging. To solve these issues, we designed a robust online multi-camera people tracking system that integrates spatial information within and across cameras and the state-aware appearance information of the targets. Our system consists of three main parts: multi-view matching with geometric consistency and state-aware ReID affinity, and a global target update and cross-view target initialization. Our system first performs object detection, pose estimation, and ReID feature extraction to provide spatial information and appearance information for subsequent multi-view matching process. We deploy YOLO-X as our detector, HRNet as our pose estimator, and MGN as ReID module. Specifically, in multi-view matching, we introduce global targets to store latest updated information of individuals from multiple views, including multi-view bounding box, multi-view 2D key points, and ReID feature bank, etc. With camera collaboration parameters, we mainly rely on spatial information to maintain tracking stability within a single view and consistency across multiple views. In our affinity measures, we utilize 3D epipolar affinity and homographic affinity to ensure multi-view consistency during tracking, while 2D IOU affinity is employed for single-view tracking stability. Besides, to tackle the beforementioned ID switch problem and the new target initialization problem due to severe occlusion, we propose a state-aware ReID affinity to adaptively correct these issues with appearance information. In our implementation, we perceive the target state in each camera view, which is named as 2D state. The 2D state of a target in a certain camera view is defined as occluded if its bounding box overlaps with others. If no detection is matched to the target at that frame, the 2D state will be set to missing. Otherwise, it would be set to detected. We recorded the 2D states in the latest 10 frames, and if a target is with at least one occluded or missing 2D states, we add a ReID affinity score to provide additional appearance information. Finally, the matching problem can be solved by summing up these four affinities and employing Hungarian algorithm. When the matching results are obtained, the matched detections can be used to update the information of the target. We hereby divide the update process into two separate ones. The first one, single view update, mainly deals with spatial information updating in each view, such as bounding box and the 2D key points. The other one, multi-view joint updates, is mainly responsible for global information updating, including 3D key points update and feature bank update. The location of 3 points is obtained via triangulation of 2D points when there are at least 2 views available. The 3D key points provide us accurate positions of individuals in world coordinate. The feature bank update process mainly aims to solve the re-identification problem, as is illustrated in the example. We observe low ReID similarity between the same person, but high similarity between different people with similar clothes. Therefore, to address this issue, we designed a ReID feature bank update mechanism where we retain diverse ReID features of each tracked target. Specifically, The feature bank will be updated by a feature vector from detection if and only if the following requirements are satisfied. It's required that the bounding box contains a visible human upper body and is without occlusion and with high confidence. Besides, the ReID feature vector should have a low similarity with existing vector from the feature bank, which indicates that it corresponds to a new perspective or a new pose of the target. If the detection is not successfully matched to any target in the previous multi-view matching process, we will try to initialize a new target for it. First of all, we utilize a cross-view matching process to associate detections from different views. The affinity matrix is similar to the multi-view matching process, but we use binary integer programming as the optimization method to respect the matching cycle consistency. For example, when the detection I is associated with detection J, and J with K, then detection I must also be associated with K. When two or more detections from different views are associated together, we name them as multi-view detections. Otherwise, we call it a single-view detection. Besides, a single-view detection often suffers from false positive detection problem. We adopt different initialization for multi-view detections and single detections. We design 4 checking states to specify different types of targets: confirmed, unconfirmed, missing, and deleted. The multi-view detection directly initialize a confirmed target, while single-view detection can only initialize an unconfirmed target, and need 3 consequent matchings to transfer to the confirmed state. Otherwise, it will be deleted. If a confirmed target does not receive any matching during at least 10 frames, then it will be transferred to the missing, but can still be reactivated via the matching with missing target process. In our system, only the confirmed target will generate outputs to ensure the tracking accuracy. Finally, our method achieved a Horta score of over 67 on the tested of AIC24 and ranked second on the leaderboard. Besides, with the 10% online bonus, our final score surpassed the offline method, which ranked first one on the leaderboard. We also conduct extensive ablation studies to prove the effectiveness of different modules of our method, especially the state perception of occluded and missing targets for ID switch correction. We also present some visual comparison between the baseline method and our method. We can also observe that after the severe occlusion denoted with red dashed circles, the baseline method encourages ID switch and a new ID initialization problem, while our method preserves well the checking accuracy. That's all for our presentation. Thanks for your attention.
Yeah. So now let's welcome the team from Nota to present their work.
Hello, I'm Jong-ho from Nota, and I will be presenting our solutions to AICT Challenge Track 1. The multi-camera people tracking MCPT task involves detecting and tracking people captured by multiple cameras simultaneously. We focused on addressing issues that significantly impact the performance of online MCPT, which uses only past and current frames. Specifically, these include inaccurate mapping onto a 2D map, extracting low quality or inaccurate features, and assigning multiple IDs to a person. The figure above shows the overall pipeline of our implemented online MCPT system, which consists of 4 main modules: people detection, single camera people tracking, SGPT, inter-camera association, ICA, and cluster self-refinement. First, people detection identifies people and SGPT tracks them within each camera. You can find the models used in this system within the figure. And ICA matches the same people across multiple cameras by clustering based on appearance features and 2D locations. At this time, the created clusters store the corresponding features and locations. Finally, the cluster self-refinement module corrects tracking length as accuracy. We can explain our proposed methods in the following slides. First, I'll explain how we use the pose estimation to improve the performance of our system. As shown in the left figure, we project people onto a 2D map based on their feet positions using a homography matrix. In cases of occlusion, we estimated feet positions using fixed values from visible body parts. However, as shown on the right, body ratios vary by camera angle, so we dynamically estimated these values per angle using key points from a pose estimation model. And to avoid storing appearance features from multiple people in a bounding bus as a left figure, we estimated the number of people by counting key points. Also, we used the pro-cross-test analysis to store various appearance features from different poses, resulting in enhancing tracking robustness. In the online MCPT, storing inaccurate appearance features in a cluster track link or allocating multiple IDs to the same person can significantly impact performance. To tackle this issue, we proposed a cluster self-refinement module. First, the appearance features refinement process removes inaccurate features from the cluster track link. Next, the overlapped cluster refinement process identifies and corrects instances where a person has multiple IDs. We improved the accuracy of our online MCPT by periodically running this refinement module. I'll discuss the details in the next slides. If the appearance features of several people be stored within a cluster track link, there is a risk of ID switching occurring, which could compromise the quality of feature tracking. To address this, we use agglomerative clustering to refine these features, effectively filtering out features from different individuals as a left figure. As a result, we could maintain accurate tracking for each person. In the overlapped cluster refinement process, we address the issue of multiple clusters tracking the same person. First, we look at the cosine distance of features and the Euclidean distance of 2D locations between cluster track links under tracking. When these distances fall below a threshold, remove one track link as a person A in the left figure. Next, we compare lost cluster track links where tracking has stopped with track links that are still tracking. If the cosine distance of features is below the threshold, the two track links are integrated as shown in person C. Now let's discuss our experimental results. Adding the CSR module significantly improved our HOTA score. Further enhancements with pose estimation resulted in a final HOTA score of 60.93. This improvement secured the third place on the leaderboard, demonstrating the effectiveness of our methods. Thank you for listening, and please ask any questions during the Q&A or poster session later.
Okay, now let's welcome the team from Hoser. Yeah, Andreas. He has been participating in our challenge for many years, so he's an old friend of ours.
4 years in a row.
Yeah, 4 years in a row. Let me put the slides on here. Yeah, so maybe you can look at there and to present. All right.
Okay, all right. Hi, everyone. My name is Andreas Becker, and I'm from Fraunhofer IOSB in Germany, and I will present our approach to track 1, which is called OCMC track. So first, the motivation. So multi-target, multi-camera tracking is the task of tracking multiple objects across multiple camera views. And yes, it has multiple applications like
like in retail or industry and logistics, where you can get an enhanced understanding of movements, patterns, and interactions, or you can optimize the retail layouts or the logistics processes and enhance safety in industry settings. And yes, I mean, I will skip the challenge task as it's already known, I think. Oh, how can I get to the next slide?
Maybe use this one.
Yeah, so okay. So let's move on to our overall concept. Our overall concept is an online tracker, which works as follows. We first do single camera processing using the tracking by detection paradigm on the individual cameras. Then we use the bounding boxes and transform them to world positions. And then we do the cross-camera association solely in the world coordinates. And in contrast to the previous approaches, we do not use pose estimation due to the computational overhead. And yes, on the right side, you can see our main contributions. So we propose a new matching cascade, and we focus on 2 points in our approach. So the first one is the correction of incorrect associations from previous time steps in the cross-camera association. And the second point is how can we improve the transformation of bounding boxes to world positions. And last but not least, we achieve competitive results in the challenge. So to the first problem, the correction of erroneous assignments. The problem of online tracking methods is that not enough information is available to do the association decision, in contrast to offline approaches, and that leads to a lot of false positive associations. And our idea is quite simple. We just re-evaluate in every time step our existing multi-camera tracks and exclude single camera tracks that do not match those multi-camera track anymore. We do this based on the position in the world and based on the visual appearance of the persons. And tracks, single camera tracks that we've removed from multi-camera tracks are eligible for matching in subsequent tracking stages. And the second part is the improvement of the bounding box to world projections. In general, we use the middle point of the bottom line of the bounding box as reference point for the homography projection. And as you can see on the right side, we first make our detector to learn better and more accurate reference point by enlarging the bounding boxes and you can see on the left image, the person behind the lamp. The ground truth bounding boxes only cover the visual parts of the person, but yeah, you don't get an accurate reference point in this case. So we enlarge all the bounding boxes in the training set so that the bottom line correlates with the position in the world of the person. And by that, we force the detector to directly learn this information without an additional pose estimation model. The second problem we addressed was that detectors like YOLO V8 only detect persons within the image boundaries. And that's a problem, for example, if the person is at the bottom of the image and yeah, we just use some typical body proportions. For example, the body is normally 2.5 higher than the width, and so we can enlarge the bounding boxes easily. And the last approach to improve the bounding box to world projection that we've done is that we virtually increase the size of bounding boxes and compute the world positions for different sizes of the bounding box and use these new bounding boxes these new world positions for matching. Let's see the results. As you can see on the left in the ablation study, all the proposed methods have a positive impact. You can see that concerning the projection of the bounding boxes, the adjusted detection boxes in the training data set have the biggest impact. And concerning the track splitting approach, we can see that the visual information is much more important than position information when deciding whether we have to split the multi-camera track or not. And on the right side, there are challenge results. Yes, we achieve fourth place with our online method, which is similar to the previous approach. Thank you for your attention.
Thank you. I hope you will participate again next year. All right.
So morning, everyone. Today I'll be presenting our work for an online approach and evaluation method for tracking people across camera in extremely long video sequences. So multi-color camera people tracking involves detection, tracking and assigning unique ID to individual across multi-camera views as illustrated in the image. And the main challenge include in such tasks, including handling cross-domain scene and some occlusion with the environment, as long as some non-overlapping camera views long-term VID problem. And I think the previous presenter and organizer did a great job on highlighting the detailed AICD chunks. So I'll focus on the change from AICD 23 and 24, which impact our solution. So there are significantly increased numbers of camera, numbers of track, number of scene, and bounding boxes. And you can see that the sequence has been been longer from about 180 frames all the way to 24,000 frames. And there are also additional 3D annotation and camera matrices being provided to us to assist on solving this problem. And here is the overall framework of our proposed online method, which can be divided into three main components. The first one, detection, and then spatial association, and finally a temporal association, which can also be referred as tracking. So first, for the detection part, we use a YOLO-based detector to process a raw image and identify bounding boxes and key point, generating detection notice. And key point ground truths are projected onto each camera view using provided camera matrices, ensuring the accuracy of the localization. And the image on the right illustrates the detection result on the AICD24 testing dataset, with key point marked even outside the image boundary, demonstrating the method can kind of be robust into estimating the 3D work coordinate with only camera view available. And the second step, we utilize the camera calibration to map detection into the global coordinate system. And then we group detection from different views based on the spatial proximity and some heuristic threshold. And we call these spatial nodes as we store their bounding boxes, appearance feature, and average global location. And this can actually ensure our detection from various camera views are accurately associated, maintaining the spatial consistency across the system throughout the tracking stage. And third, we then use standard BioTrack to link spatial nodes over time in a 3D world, ensuring the continuity in tracking. And this step actually integrates spatial nodes from a consecutive timestamp, producing the final tracking result. And the table on the lower left corner shows our final performance on the AICD24 testing dataset. So here are some quick visualization. I won't be too long. So yeah. And okay, so actually we have tried to propose another evaluation because during our participation in the challenge, we found that actually in such a long sequence of videos, so you can see in the table, we list some other different data set and multi-optic tracking we often use as benchmark. And you can see that actually in the AICD24 challenge, the numbers of each sequence frame are around, let's say, 24,000, which is much more longer than other benchmarks. So we observe that when we try to evaluate extremely long sequence that involve re-identification, the current metrics tend to favor offline method a lot. So challenge organizer also tried to promote the online method by adding an additional 10% to a method, to online method, but the gaps between online and offline is still observable, and we think. So this brought us to think that can we have like a better way to evaluate those online methods in terms of multi-optic tracking. So we try to play around with the original HOTA. So we introduced a parameter n, which represents the ratio of the evaluated frames to a total frame number of frames, ranging from 0 to 1. And we calculate the corresponding segment length and trim to crop the original sequence into overlapping segment. And each segment is then evaluated separately as the original HOTA to compute what we call HOTA at n, and n is the ratio, which is average over all segment to get a performance measure of the varying sequence lengths. And finally, we extend HOTA at n to m HOTA, so it works like mean average precision. So we try to integrate it over all values of n from 0 to 1 This can provide a more holistic evaluation of tracking performance across different sequence lengths, especially in online tracking method. So we show that the M-HOTA evaluation for online and offline method right here. So the left graph is for online method, while the right one is for offline method. We observe that the performance decline more steeply for online method as sequence length increases, indicated by higher values of N. So for like 1.0, and it means that we use the entire sequence to do the evaluation. And for like, let's say 0.2 of the N, we mean that we crop the entire sequence into like a 20% ratio and do an overlapping HOTA and do the average across it. Yeah, so here are some additional results for the result. We have M-HOTA on the validation set of AIC24. So we hope that this matrices can somehow inspire or will probably lead to a better discussion in terms of better evaluating in the online tracking method for like a large and complex multi-object system in this field. Thank you.
Thank you, Chris. So let's welcome the next speaker. It's a PDF. Yes. Yeah, can use this.
Hello everyone, my name is Rio and I'm representing the machine learning team from AN Robotic Ventures Company. It's an honor to present our paper, Online Multi-Camera People Tracking with Spatial Temporal Mechanisms and Anchor Feature Hierarchical Clustering. Let's start with the goal of multi-camera people tracking. It is to follow individuals across multi-camera views, playing a crucial role for large-scale surveillance applications like security systems and retail analytics. However, challenges such as occlusion, varying lighting conditions, and apparent resemblance, and identity switch due to overlapping person can cause detection and association inaccuracies. Additionally, most existing frameworks are offline methods, making them unsuitable for real-time applications. To address these issues, we propose our online multi-camera tracking framework. Our approach has three main components: multi-object tracking or MOT, multi-target multi-camera tracking or MC, and cross-interval synchronization or CIS as shown in the slide. For MOT, we use a time windowing approach to segment video input from multi-cameras into subintervals. Within each subinterval, a YOLO V8 object detection model identifies humans in each frame. OSNet feature extraction generates feature vectors from these human images, while BiTrack object tracking assigns unique IDs to initial object detection and track them across frames. YOLO V8 pose estimation is then used to extract spatial information, converting foot position into 3D world coordinates using camera calibration. The produced tracklets are fed into MTMC module, where constrained hierarchical clustering merge tracklets across camera. These merged tracklets are further refined through spatial temporal refinement. Finally, the CIS module synchronizes object trajectory across time windows by comparing tracklets with previous profiles. As I mentioned earlier, I'm going into detail of spatial temporal constraints used in our method. We employ 4 constraints during the tracking merging process. Firstly, the frame overlap constraint for same camera. It ensures that tracklets from the same camera do not share overlapping frame, indicating distinct objects. Secondly, the frame overlap constraint for non-intersecting camera pairs. It extends concept to tracklets from different cameras without a shared visual field using homography metrics for spatial overlap calculation. Thirdly, the position overlap constraint for overlap frames of 2 tracklets. We compute the mean Euclidean distance between tracklets position. If the distance is below a threshold, the tracklets may consider for merging. And finally, the neighbor constraint. This evaluates whether an object can move from one camera view to another without intermediate captures using a predefined neighbor table. Now let's move on to the anchor feature hierarchical clustering. This process involves comparing and grouping the anchor features of all tracklets across various camera perspectives within a specific time intervals. We use hierarchical clustering to iteratively merge tracklets, starting with each tracklet as a separate clusters. The algorithm identifies the pair of clusters that meet all the constraints and have the highest similarity based on a pre-computed similarity matrix. Anchor features of merging clusters are dynamically updated into a larger set of anchors during the process. This continues until no further measures satisfy both the similarity threshold and the constraints. Next is spatial temporal refinement or STR. It addresses the limitation of appearance-based features due to lighting condition and camera perspective. The STR construct positional table for each threaded cluster, recording world coordinate across time frames for multiple spatial coordinate in a single time frame. An aggregated position is computed by averaging these coordinates to mitigate positional discrepancy from factors like occlusions. Then the STR compares cluster pairwise, identifying those that share time frames and have world coordinates within a predefined intersection zone. If they meet this condition and constraint, cluster merge, resulting in a more accurate tracking. Next, we will talk about our last module, the CAS. It integrates object trajectory across distinct time windows from multiple cameras, constructing consistent trajectory throughout the observation period. The algorithm iteratively identifies the closing existing profile for each threaded cluster based on the distance metric. If the distance is below the threshold, the cluster merges with the profile. Otherwise, the new profile is created. This rule set continues until no further merges can be made, resulting in an updated trajectory profile accurately representing trajectory across all camera and time intervals. Our method achieved an HOTA score of 51.05 on the test set, securing 6th place in the AICTE Challenge Track 1. Moreover, we found that the optimal time interval size is 300 frames or 10 seconds, resulting in an HOTA score of 69.10 on the validation set. That concludes my presentation. Thank you for your attention.
Okay, thank you. Maybe we can have all the authors of the 6 papers can come up. We have a quick Q&A session. I know we are running a little late, so we can just have a couple questions. Let me confirm with the team. Okay. Yeah, I think that's all the presenters. Yeah, please come up here. Okay, is there any questions for these papers? Okay, I do have a quick question. So this year we used the NVIDIA Omniverse platform to generate the synthetic data for all the data sets. So is there any suggestion for us to improve our data set in terms of reality and also like this synthetic data set compared to real data set? What are the challenge compared to the real data set? Any one of you?
I can go. So I think compared to last year, we do see a very large increase of numbers in terms of those avatar tracks, and which is we think is very challenging and very, very cool to the community. But one thing we still observe is that the movement of these avatars is still considered pretty, I think, simple. They are either like standing or just walking linearly with, I think, very small speed variation. So I'm thinking that the most important difference between real world cases and the Omniverse data set is that the motion or like the movement that the object, the target will do is by far like a very large difference. So I think if that is provided in the Omniverse, it will be probably very challenging and also very meaningful. Yeah, that's my idea.
Okay, another quick question. So this year we do encourage online tracking, and we also want to know, you know, for some of the methods, it seems to require heavy computation, like you use post-estimation model, reality model, and detection model. Of course, as NVIDIA, you know, we are a GPU company. We prefer you to use more resources. But is there any way you can improve your methods to adapt to real-time processing to improve the runtime performance inside that? Especially for the teams using online methods from Nota or Andreas. Yeah. Yeah. Andreas, do you want to?
Yeah, hello. I mean, you can apply technologies like TensorRT, which is quite helpful in such cases. And as we did, you can omit unnecessary parts like post-estimation if you have other solutions to tackle this task. I mean, our detector is real-time capable in this case, ULV8. And I think the biggest problem in our approach is the reality model, which is the LiDAR, which is a heavy transformer. And I think if in a real-world setting, where it's not necessary to optimize to 0.001, I don't know, maybe you can use smaller models here and improve the speed.
Thank you, Andreas.
Hello.
we have a question from the audience. You can say it. I will repeat it.
Okay, for sure. So hi everyone.
Excuse me. We have we will come to you afterwards. Okay.
Oh,
Sorry.
okay. Sorry for that.
You can go ahead first.
Among your external, I mean, you look at data here. So what's the most important factor affecting the identification?
Yeah, so we have a question that what's the most important factor affecting re-identification? It's like the poses or illumination or things like that. Yeah, go ahead, Andreas.
I would say occlusions, people-to-people occlusion or occlusions by obstacles and partly visible persons at the borders. If you see, I don't know, only half the person, it's really hard to match it to a full body view.
Yeah, I think I will also say like the scale of the data set that is trained on, because like a lot of people with similar color of clothing, you need fine-grained details to improve the reality model. We have another question from the Zoom. Let's have that question first.
Yeah, for sure. So hi everyone, thanks for the presentation. So my question is like mostly based on how the camera calibration procedure should be done. So for example, sometimes what happens like when we calibrate the cameras with respect to each and every of these cameras that we have with respect to the shared floor plan. So if two cameras are like overlapping and there's like a particular overlapping region, so the homographic matrices or homographic projection points that are generated by camera 1 and camera 2, they differ. Because sometimes like the person is included in camera 1, but it's visible in camera 2. So how you guys are like handling that particular situation?
Okay, so there's a question regarding camera calibration. Anyone? Yeah.
So I think so for this year specifically, the camera calibration is being provided by the organizer. So I believe since it's generated by the Omniverse engine, Omniverse platform, those calibration, I think it's fairly I'll say near perfect accurate. So we did not encounter any specific cases like where whenever two camera views homographic result do not agree. But I believe that if it's like in the real world scenario, I think if the two camera views have some disagreement in the homographic, and let's say we need to decide which one to believe, I think we can have other like heuristic rule to either like to decide just simply like either do like an averaging across or weighting across different camera, or just simply believe one of the camera which have like a better view angle or the viewpoint of the target we are looking at. Yeah, so I think that.
Okay, thank you. One last question. I think that the gentleman have a question. Okay, yeah. So the question is, how do we handle like the storage and retrieval of the IDs for like the infrastructure of this kind of multi-camera application? I think I can take that question. So because these participants, they may just participate in the two months challenge, they may have not encountered that kind of infrastructure building. But at NVIDIA, we have a multi-camera AI workflow, and it is also available for early access now. You can check on our website. So for that application, we do use like a vector database, and we use that to store all the ReID features at scale. And then once you have a new like a re-identification embedding vector, you can search through the vector database quickly, and you can store the people's ReID features across weeks or months. Yeah, hope that answers your question. Okay, I know many of you may have other questions. We can approach to the authors afterwards, but we have to move on to the next section of the presentation for track 2. We're running a little late, but let's take another 5 minutes of water break. I think there was some coffee outside. So after 5, oh, they are already done. Or is in another building? Okay, we don't have any coffee, but like let's take a 5-minute water break and come back. And for the presenters of track 2, please come up here and check your slides and everything. Thank you, everyone. Yeah, for track 2. 31. Let me try to 31. Let me see. I don't have. Do you have the? Do you have it on the Google Drive? 31. This one. Let me see. Paper 31. Oh, you're not track 2. You're track 3. Okay. Yeah, you still have time. Okay.
Paper ID 10.
Paper ID 10.
I have uploaded my PowerPoint from the Drive.
Oh, okay. You're track 2?
Yes.
I already downloaded.
Oh, thank you.
Oh no.
I check it a little bit.
Yeah.
Let's go down.
Looks good.
Yeah, thank you.
No, thank you. TV 15. Just a sec. 15. I have your slides already here. And take a look and make sure everything works. Yeah. So
Yeah.
looking good. Okay. And
we are the same.
Same thing. Okay.
Hello, Thomas. Can you hear me?
Oh, go on. Yeah, I can.
Yeah. Hello. Yeah. Great. I think I'm online now, but previously I feel that the question coming from the conference, I cannot hear it very clearly. So as you know, we have a member in the conference as well, right?
Yeah.
Yeah, I'm not sure. Is it better for him to support you to collect the question from the conference, or if you
Yeah,
also...
we don't have like a wireless microphone or like a handheld mic. So it's okay. So when the audience asks questions, I will have your colleague here to repeat the question to you.
Of course, yeah. This is also one way. And if you need any help from the conference, our members named maybe Kavana, he will also will help this one to support.
Yuki is here. You can.
I have a question. So are you going to do sharing for the track 2 as well, like you did like for track 1? Or
Yeah, I can turn on all the. I have a collection of all the presentations here, so I will just. You can introduce the presenter.
Okay. So
maybe
you want us to do the sharing for track 2, or you do for
yeah, it's better for Chuan to do the sharing, and then I can turn on the slides for Chuan.
Okay, cool. Thank you very much.
Yeah, but if there's question from audience, you can also help facilitate that.
Okay, thank you very much.
Okay.
Great. Thank you, Thomas. Yeah, thank you very much.
Yeah,
But by the way,
you have the order of presentations, right?
yeah, we have the order. As the order is as listed up in the workshop homepage, is the same one. Yeah.
Okay. Yeah.
Yeah.
So
but by the way, I am currently open my video, but can you see my face or not? I'm not sure.
Yeah, I can see
Oh,
your
you
face.
can see. Okay, I cannot see my face. Okay, great. That's fine. Yeah, thanks. Yeah.
Hello everyone.
So maybe Thomas, just a quick confirmation here. So I think you use your PC for the presentation. So if we want to change for the next person to give the presentation, maybe I think you is better instead of our team member directly do this thing. It's okay, right? Yeah.
But
Great.
yeah, you can introduce each presenter first.
Yeah, thank you. Yeah, great. Yeah.
Okay, I think most of us are back. So now we are moving forward to track 2, which is the traffic safety description. And we have Chuan from the Woven of Toyota who will be chairing this session. Yeah, Chuan, go ahead.
Okay, thank you. Thank you, everyone. And this will be track 2 paper sessions. And I'm coming from Woven by Toyota. And today also we have several members join this conference offline as well. Let's start the first presentation coming from Alibaba, City Lava. So if it's okay, Thomas, could you start let's play? Yeah.
Yeah, so this presenter, unfortunately, due to visa issue, they cannot attend the conference in person. So we allowed that for like a pre-recorded presentation. But I think Zhi Zhao is also online. So if you have any question, he's available here as well. Let me play the video.
Hello everyone. We're the team from Alibaba Cloud Intelligence Group. In this talk, we will introduce our solution for the Track 2 traffic safety description and analysis in the 2024 AI City Challenge. We propose City Lava, an efficient fine-tuning method for vision language model specifically designed for urban scenarios. The Track 2 focuses on detailed video captioning of traffic safety scenes, especially those involving pedestrian accidents. By using multiple cameras and viewpoints, we aim to describe the moments leading up to the incidents along with the normal scenes, capturing all relevant details like the surrounding context, intention, location, and behaviors of both pedestrians and vehicles. In tackling this track, we've identified several challenges. Firstly, in some views, both pedestrians and vehicles of interest appear quite small, making it hard for vision language models to capture fine details. Secondly, the data quality varies greatly across different perspectives. Some of the low-quality data doesn't help in training the vision language models. There's need to design methods to weed out this noisy data. Thirdly, the city scenes in the BDD ITA set are complex, filled with background objects that make it tricky to locate the key pedestrians. Lastly, the original text descriptions are both template-based and verbose, raising the risk of the vision language models potentially overfitting. Despite the challenges mentioned above, we have gained extensive experience in this area. Our OpenTrack is a developer platform dedicated to the industry application of large models and agents, committed to providing a comprehensive toolchain for knowledge management, model training and deployment, agent development, and evaluation services, along with extensive OpenAPI support. It aims to deepen the application of industry scenarios and drive intelligent development. Leveraging our experience, we've developed an efficient fine-tuning pipeline that covers data evolution, industry-specific fine-tuning, model fusion, and depot techniques. We plan to implement this pipeline in Track 2, breaking it down into 3 key areas. Firstly, prompt engineering, which includes both visual and textual prompt engineering. Secondly, continued training, which incorporates techniques like SFT and RLHF. Lastly, inference augmentation (IR), aimed at improving model performance. Building on the pipeline described earlier, we introduced City Lava, an efficient fine-tuning pipeline designed for vision language models. Our approach encompasses 3 key aspects. First, in visual prompt engineering, we initiate the process with a best view selection module. This module primarily filters out samples that lack the vehicles and persons of interest. Subsequently, we employed both global and local views with visual prompts to enhance the model's capability to discern intricate details. Next, for text-based QA construction, we utilize Qianwen Max to generate a mix of long and short QA pairs, which significantly enriches the diversity of the egg. Lastly, in the model development phase, we adopt the block expansion technique for fine-tuning LLaVA. This strategy has proven to be superior to LoRa, not only in terms of performance, but also in reducing the resources required compared to full parameter fine-tuning. The best view selection algorithm serves to eliminate samples where target vehicles and pedestrians are either absent or smaller than a specified threshold. This led us to develop the mentioned filtering mechanism. Next, we substitute the original footage with a combination of global and local views enriched by visual prompts. In particular, we use bounding box annotations to identify the targeted pedestrians and vehicles. These bounding boxes are visualized directly on the frame, with green indicating pedestrians and blue for vehicles. This technique simplifies the task of aligning text with frames and enhances the model's focus on key elements. We believe the integration of global views, providing context, and local views, offering detailed insights, serves as an optimal visual input. This method proves to be more efficient and less noisy compared to the AnyRes approach in LLaVA. Next, our application study further confirms the effectiveness of our visual prompt engineering strategy. In textual prompt engineering, we aim to craft questions that not only accurately and comprehensively capture the content described, but also go beyond simple requests like "please provide a detailed description of the pedestrian and vehicle in the video." To achieve this, we incorporate a video stage outlining key points such as height, clothing, line of sight, relative position, movement, and environment to develop a new set of prompts. Furthermore, we devise a series of short QA pairs based on the source descriptions to combat style and template overfitting during the fine-tuning process. By using Qianwen Max to dissect each description, we categorize sentences into specific dimensions and match them with pertinent queries. This approach enables us to craft targeted questions and relevant responses from the model. The block expansion technique, a novel post-pre-training approach for large language models involving an increase in transformer blocks, was introduced by Llama Pro. We adapted it for vision language models. By tuning the added blocks with the new corpus, we enhance the model's knowledge base efficiently and effectively while avoiding the issue of forgetting. We implement backbone expansion by adding 12 blocks and fine-tune these new blocks using an aspect-specific corpus, keeping the blocks from LLaVA 3.4b unchanged. Our ablation study confirmed the superiority of block expansion over LoRa. Following these enhancements, we secured first place in Track 2 with a score of 33.4308. Our methodology proves to be a versatile pipeline that can be rapidly applied to data across various industries. In conclusion, we introduced CityLLaVA, an effective fine-tuning method for vision language models in urban settings. Our key consignals include the importance of view selection in eliminating unhelpful data and how integrating global and local perspectives with visual prompts is essential for recognizing smaller objects. iDiversity is crucial for preventing model overfitting and understanding the scaling law of vision language models significantly boosts performance. Looking ahead, our goals involve refining evaluation metrics and exploring the use of reinforcement learning with human feedback. Thank you for listening.
Thank you very much. So, Thomas, next speaker is in the conference or not? Yeah.
Yeah, I think so. The
Okay,
team number-
okay. Let's move to the next one. Yeah, so paper ID is 10 and coming from Ho Chi Minh University of Technology. Yeah, please.
Hi everyone, my name is Thái Jin Sung.
from Ho Chi Minh University of Technology. Today I will present a paper named Divide and Conquer Boosting for Enhanced Traffic Safety Description and Analysis with Large Vision Language Model. So the first part is about introduction on the track 2. The track 2 requires to analyze multiple video camera views to propose a detailed 5-gram descriptions on the traffic safety of the scenarios, focusing on the vehicle and the pedestrian as highlighted in red and orange here, as I illustrated here. So the motivation for our proposed method is that given this long 5-gram descriptions, this is quite hard for human layers to decompose it and perform a detailed analysis of these scenarios. So we have discovered the dataset and analyzed some main attribute of this description. So here, for example, we identified a caption for a dataset may have some main attributes here. For example, we have appearance, location, attention, and environment attributes. Here, for example, for the previous example, we can say that we can classify each sentence like this one to the appearance sentence, talking about the appearance of the pedestrian. The next one is about the location of the pedestrians and the attention of the pedestrians on the vehicles. And the last one is the environment involving the road conditions, the weathers, and also the obstacle. And the next part to our proposed method is to construct a data set that is divided into, each sentence is divided into different segments. So our proposed method is including 2 parts. First one is the pre-segment, and the next one is the dynamic prompt segment. For the pre-segments, our objective is to utilize a large language model to categorize each of the sentence into a different type of attribute. And the next part is that we're using an embedding models to embed each of those and categorize segments and to correctly refine our classification so that each of the sentence in the caption can be classified into each of type attribute. You can see here, for example, for the location attribute, we can classify as the sentence with the numbers on that. So we also discovered that on the dataset, there can be a sentence can be comprised of multiple attributes. So we did use a system prompt to guide the language model to use linking word to combine informations, and this one we experiment that this one will allows the language model not to be confused by the collapse of the attribute in the sentence. And also we use another technique to better guide the language model to extract here is the few shot prompting. We use a set of predefined few shot prompt to enhance the extraction accuracy. So, and after we have, we also have this figure to showcase our the reason why we want to do the 2-stage segments. The first one is the human labor segments, where that is our human labor, and the middle is the phase 1, where we perform pre-segment using language model. The next one is the phase 2, when we refine our extraction using the embedding models. So we can see that in the first phase, we discovered there's some information loss due to the large language model tend to have some loss in their output, and also there in the third rows the first highlighted in red, we can see that the sentence tends to be reordered. The line scroll tend to reorder the sentence. So we experiment that this kind of attribute may affect the performance of the models. And after we use the phase 2, we guarantee that the dataset extracted from that will be correctly the same as our human label. So, and the next is our training pipeline. We use a two-stage training pipeline. The first stage is that we try to perform autoregressive training to perform captionings on each of the segments. And the next stage is to train a dynamic combiners to combine those segments into a detailed descriptions. And for inference, we use those two states also. The first is captioning each segments and then use a dynamic combiner to combine those segments. So our method achieves a second ranks on the public leaderboard on the full test sets. And we also showcase some of the experimental results here. So we say that we found that we can train each of the lower adapter for a training method will result in a better score than a single lower. And we also experiment some rewrite method. So the second figure says that we test different set of combination of our of these segments, and we showcase that our rewrite method actually performed the best. And in conclusions, we did propose a preprocessing data method named segment extraction to construct a new segment-based dataset to train the model for the WTS dataset. And the second contribution is we introduced a two-stage training framework tailored for the dataset, improving the accuracy for generation. And this is our link on the code. Thank you for listening to my presentation.
Thank you very much for the presentations. Okay, let's move to the next presentation coming from Simon Fraser Universities. It is okay to share the slide here?
Yes. Is the presenter here for the paper ID 28? Yeah, I think the presenter is not here, but I have uploaded their slides. So after the workshop, we will share the slides of all the presenters on our workshop website, so you can all take a look. Maybe we can continue, Chen.
Okay, great. Yes, let's continue for the next presentations. So the next presentation is coming from paper ID 27, enhancing the traffic safety with power-dense video captioning for end-to-end event analysis. The team is here.
Yes.
Great, thank you. Yeah.
Yeah, you can use the arrows to control first slides. Thank you.
Hello, everyone. So today I'll be presenting our accepted paper, enhancing traffic safety with parallel dense video captioning for end-to-end event analysis. Can I see the screen from here? Yeah, on the laptop. Okay. So to begin with, let me talk about the motivation behind working on this project. So our main goal here is to generate long and fine-grained captions for the traffic safety videos that were provided by Toyota Woven Traffic Safety Dataset. Now, over here, we can see that there's multiple different angles that we have for the video. So we have overhead view, you have pedestrian view, and you have vehicle view as well. And the way the data was structured is that we were provided with caption dataset, and we were also provided with bounding boxes for the detected vehicles or pedestrians in the dataset. So what is the main concept? The main concept is to implement a parallel dense video captioning integrated with clip visual features to enhance the accuracy and efficiency in generating fine-grained captions. So what do I mean by fine-grained captions here? Now, we're not basically just describing a video in terms of the detected objects, but we are providing very specific details for the caption. So for example, the age of the pedestrian, the color of the t-shirt that they are wearing, the action that they are performing. Is it the recognition of the vehicle? Is it trying to avoid that particular vehicle, or what exactly is going on in the scene? So here's a quick overview of our framework. So we basically start by performing parallel dense video captioning for simultaneous event localization and captioning. So historically, dense video captioning has been the more common technique that's used in generating captions. But when I'm saying parallel, meaning we are captioning events within a video in parallel. So each video would have, for example, 5 different events segmented into 5 different events, and we are captioning those in parallel together. And then we use a clip feature extractor, which helps us in embedding together the video and the text at the same time. And from there, we train several different models. We train one for WTS event data, and then one for WTS normalized frames, and then one for BDD 5K, which is it's a much bigger data set. And we then perform knowledge transfer, where we're simply just feeding those pre-trained models on these data sets in the main model that we're using on the WTS event data. Now, one important thing that I need to mention here is that we didn't actually, in our solution, we didn't use any of the bounding box information that was provided. All the captions that were generated was purely just on the pedestrian and vehicle captions, along with the videos that were provided. None of the bounding box information was used to ground the captions. We ran into some issues when it came to the captions that were generated with unknown words, like, for example, kilometer per hour is a token that the model cannot really understand. And these were, this is where post-processing came to fix all these different words that did not make sense in the generated caption. And here's a table of the evaluation study that we did. So we compared together the performance improvements when using clips, for example, as a feature extractor, and then domain modeling, and then knowledge transfer from the models that were trained on the different data sets, and then post-processing. And we realized that combining all these 4 concepts together gave us the best score, and that helps in achieving the 6th place in the challenge. Thank you very much.
Thank you very much. Okay, let's move to the seems the last presentation for this track. Paper ID 15. Yeah, the team coming from the University of Science, Ho Chi Minh City. It's okay for the presentation?
They are here. Yeah.
Okay, great. Yeah. Thank you.
So good morning, everyone. Today I'm presenting my paperwork in track 2. The paper's name is Multi-Perspective Traffic Video Description Model with Fine-Grained Refinement Approach. So first of all, we'll go to the introduction. So you can see here the motivation of this track is to, we have the input is a very long videos, and we need to describe the videos into sentence by sentence, including the locations, the actions of the pedestrians, and also the weather context. So we are tackling these problems by using a VLM and rule-based refinement method on behind to refine the pseudo caption generated by the VLM. And on the aspect of the VLM models, we're using 3 different types. The first is the single view models. The second is the motion blur models, and the third one is the multi-view models. And for the refinement methods, we're tackling 3 aspects: the pedestrian aware, the vehicle aware, and the context aware. So this is the overview pipelines of our paperworks. So we have 4 key areas. First is a textual attribute extractions, and the second one is a visual extraction attribute. The third one is a video captioning module, and the final one is a refinement module. So we are going to the extraction module first. So for textual attribute extractions, we can see the given raw captions, including a lot of informations like the locations, the attention, behavior, and the context attribute. So we employ the n-grams method to extract the keywords from these sentences. And after many analyses, we find out that we can build up 4 clusters of keywords. And by using these keywords, we can fine-grain down the long sentence into the smaller chunk captions for training the model with only that specific context, not all the context at one time. So for the visual extraction model, we employ 3 types of the data set from the original one. So we have a very long videos, and we use FPS equals 30 to extract the frames from the videos, and we construct 3 types of data sets. The first one is the stacked time frame, and the second one is the motion blur frame, which is using the average of the time frame that sum together. The third one is aggregated by frame and view together. So next, we are going to talk about the video captioning models. So for the single view one, we employ the visual encoder is the VIT models, and the decoder is the T5 model with 3 billion parameters. The key points in this model is we're using the text and time tokenizations. So you can see in below here, we encoded the time into the sentences so that the model can learn which it face how the changes in the sentences according to the visual attribute. So the second models is the motion blur one. We just have weighted some of the frames to have images in its faces, and we use that images to train with the text caption, the chunk caption one, and fine tune it on the BEIT3 and the BLIP2 models. So for the multi-view models, we will have the second presenter to present this.
Hello, everybody. My name is Minh Nam Trần. I'm going to continue the presentation with the multi-view model. So we implement the multi-view model for the multi-view model. And the input of this model here is many sequence of frames from the video. And then we use the multi-view attention to calculate attention over the views. And finally, we output a single aggregated view from the multi-views. So this is the refinement model containing 3 modules here: the pedestrian aware, the vehicle aware, and the context aware module. For the pedestrian aware module, we have 3 items. The first one is the pedestrian color detection, and the second one is the pedestrian aware detection. For the pedestrian color detection, we use the upper part pixels of the pedestrian, and then using k-mean clustering with k equal 15 to calculate the color of the person. And next, we will align the centroids of the k-mean clustering algorithm to the human readable color. For the pedestrian aware detection, we use alpha pose to detect the body key points, and then for a sequence of 10 frames, we have the vector direction of the head, and if the vector touches the boarding box of the car, then the pedestrian will be aware that where the car is. For the vehicle aware module, we will have the vehicle motion classification, which will predict the speed of the car using the average image. And for the vehicle action classification, we will draw a trajectory of the car using the middle the center of the boarding box of the car, and we will decide that we will decide the behavior of the car, like is it turning left, turning right, or going straight. For the context-aware module, we have 3 models. The first one is the context brightness. The second one is the context weather, and the third one is context road surface. For the context brightness, we will calculate the average color intensity across all pixels and all channels. And then we use a threshold to decide that the image is dark or bright. For the context weather, we will use YOLO V8 version 8, and we count the number of umbrellas inside the images. So if there are more than 2 umbrellas, then the weather is rainy, and otherwise it is sunny. For the contextual surface, we will use the segment anything model to segment the water puddles from the main road, and if there is any water puddles, then this is the roads is like very sharp. And this is the experiment store results. On the internal data set, the best S2 score is the motion blur method with the backbone BIE33 and the refinement module. For the S2 score of the external data set, we have the best method is the motion blur with the backbone Blip2 and the refinement module. Overall, the best method is the motion blur with the backbone Blip2 and the refinement module at the score of 22.67. And the below is the comparison between the prompt by the without refinement on the left and with refinement on the right. And using the refinement, we can correct the output here. Like on the left, with the model will predict that this is bright, but in the environment, you can see that this is dark. And using the refinement module, we can correct the prompt. Finally, thanks for listening.
Thank you very much for your presentations. So I think, Thomas, currently the presentation is over. Maybe we can go to the QA sessions for this track.
Yeah. For all the authors of track 2, please come up and we will have a Q&A session. Does anyone have any question, either on Zoom or in the room?
Maybe from my side, just have 2 quick general questions for whole the team. Maybe the first one is, thank you very much for your participant of our track for this year. And this is the first year, first time we hold up this track together in the ASD challenge. So similar to the track 1, we also really hopefully to know if you have any comments about the data quality or for the improvement. Anything do you want to share here from the team?
Anyone?
So for the dataset for track 2, I think the dataset quality is happy for my challenging during the 2 months of challenge. I found some difficulty in the data annotation method, data annotation of the data. For example, I found that some bounding box of the pupil of the pedestrians on the external dataset doesn't quite matching with the exact pupil in the datasets. And also I found that there is some missing in the dataset on the internal datasets. For example, there's some videos with the dot. I cannot file. I found the bounding box, and I cannot file the bounding box after the dataset is updated. So, but overall, I see that the image quality and the captionings is very well done.
Thank you. Great question and comments here. Actually, so we generated the bounding box for our data set with the first frame is annotated by the human along with the tracking algorithm. So we notice this kind of thing. And of course, so this can be done by improve the algorithm from the tracking, and also we can input more human annotated box in the future to improve the quality of the bounding box information. This is important because we also want to encourage the team to focus on the instance level understanding to use this information to enhance their model. Thank you for your comments. Yeah. And another comment from me is that for the last presentation from the team, they say about the multi-view information. Actually, one thing we want to enhancement here is that the view provided in our data set is synchronized to each other. So I think that's also a very good point and a unique point to think about how to utilize the multi-view if it is provided to give the behavioral analysis regarding the caption task from the video. It's also very interesting direction in the futures. Yeah. Let's back to the conference. Firstly, any question, Thomas, from the offline currently?
We don't have any question in the room. Oh, there's a question, please.
And also for population studies, how much would be lost again?
Okay, we have a question, so I will repeat it here. So the question is, what is the computation requirements for each of these methods? And is there any ablation study have been conducted for your methods?
So for our framework, we trained on a Titan RTX, which is around 24 gigabytes. And for 30 epochs, it took around 7 hours to train. In terms of ablation study, we noticed the biggest gain was in knowledge transfer. So the main data set, the WTS data set, it wasn't as rich in terms of scenarios between pedestrian and vehicle like the BDD data set. And that's where we noticed the biggest gain when knowledge was transferred, or we used model trained from BDD and then fine-tuned on the WTS data set. We noticed a lot more gain in the CIDR score, to be specific.
Okay, we have a question from David.
Kind of similar question though. Irrespective of the training of the models per se, but can you think of whether your algorithms can be run in an online way on IoT devices? Can the models at inference time be run on in a resource constrained environment?
So the question from David is that whether the algorithm can be run in an online way and on like a low cost device, things like that, for real-time processing.
I would like to say that the first thing, our model, we use T5 model, and we train it with a configuration of about 3 billion parameters. So I think if you use quantization and like 4-bit quantization, you can run it on the edge device, but the inference speed is quite slow.
Yeah, we look forward that you can improve your model for more advanced application in real world. Thank you very much.
Thank you, Thomas. And I think time is almost up. And for me, just also one thing is want to share here is that I found that almost the team this time used the encoder from the image information. So we also thinking maybe if we change the encoder for the video encoder, so how the result will be changed. That's also one thing maybe we can think together in the future as well. Yeah. Thank you. Thank you for everyone's presentation. Yeah.
Thank you, Chen. Thank you for the great comments. Okay.
Thank you.
Okay, so now that concludes all the paper presentations for track 2. So before we go to lunch, we still have the presentations for track 3. We have 4 papers. So we will take a 5-minute quick water break, and then we will wrap up with the track 3 presentations.
Thank you very much, Thomas. Yeah, very helpful.
Thank you.
Thank you,
Chen.
Very much for Jerry.
Oh, thank you. Thank you. Do we have Anuj with us? For the presenters of track 3, yeah, you're welcome to come up here and check your slides. You are 31, right? Everything looks good?
Yes, it's good. Okay.
Okay, thank you.
Hi. Great talks for the AI city
City
challenge.
challenge,
Yeah,
yeah.
I regret that I didn't take part in some challenges. Sounds quite familiar for me. So we are doing traffic detection by the videos.
Oh,
I
cool.
see that you're using some data sets in the challenges, but I checked the website and they protected by the password.
Yeah. We have like an application form. You can find it on the homepage. So if you fill in the application form and just check which data set you need, then we'll send the password to you.
Oh, okay. Even if I didn't participate in a challenge.
Yeah. Even after the challenge, they are available.
Okay.
I think for track 5, it's not available after the challenge, but for the other tracks, they are available.
I see. Maybe you have some other public available driving data sets, video data sets from NVIDIA.
Yeah, all our available data sets are in the application form. So we have a vehicle tracking data set. We have the person tracking data set. That's the most.
Only for the city challenge.
Yeah. So you don't have to participate in the challenge. You can use it for your own research.
Okay.
Okay.
Yeah.
Thank you. Thank you, Igor.
Hi, Vitaly. So Boston University.
Yeah. Good to see you again.
Yeah, COVID. I moved to the West Coast. And
Yeah.
Yeah, so Fred graduated and I tried to get forward.
Yeah.
This is fabulous work.
Yeah. Welcome. Yeah. It's close. You just come here from the UW, so.
And actually, I need to go to UW and get some meetings with students.
Okay.
Are you
but-
not you're in for the form?
No, I currently work in Redmond, which is just across the lake. But my most of my team, like Ashore, they are in the Bay Area. But I'm kind of like working remotely right now.
So I want to ask you, but you answered actually from the previous person. Yeah, if I were to reconnect with a data set, new students, like right undergrads, we can just fill out the form.
Yeah.
Obviously, this challenge.
Yeah, even fresh data set are still available. So if people want.
I did use it.
Oh, Fred.
Oh, Fred.
I mean
I think you could change. Yes, right. But now, yes, that's available. But also the first 2 tracks, they're available.
Yeah. So if people want, they can fill in the form and just use those data sets.
And so within a week or so.
Yeah.
I had a question. This didn't come up with Spread because we were doing everything kind of in a batch in the retrieval for the retrieval by natural language. When you distinguish between online versus offline, where does the fixed lag fit in? So let's say somebody has a method where it's a fixed lag, so sliding window.
Yeah.
Where would that in evaluation framework fit in?
Yeah. So that would be tricky. Yeah, I think we can, like last year, we incorporate some of the computation time in the evaluation metrics. That's possible because we can ask them to submit their results to GitHub, and then we use the same device to run all their methods, so we can compare their computation time.
But in terms of would it be penalized with 10 points, so even right, because you're not looking in the future, but you have the sliding window, and so you always.
Yeah.
All right, maybe
that would be challenging. Yeah, but we can discuss more. Anuj just left. Okay. Or maybe we can ask like your. Oh, we got yeah. Then maybe you have this is great work. Oh.
Hello everyone, now I'm going to introduce my work. The topic is multi-wheel action regulation for
So this is the first, which is the second.
Hi there, welcome to the Naturalistic Driving Action Recognition Challenge. I would like to thank Dave Kuhn, who is here as well. The data set was funded by Federal Highway. So that's how the challenge actually materialized. I'd like to invite the first team, Multiview Spatial Temporal Learning for Understanding Unusual Behavior in Untrimmed Naturalistic Driving Videos.
Good morning, everyone. So it's not language. So I'm Long Hang Pham, and I'm the representative presenter for our team solution to the track track 3 in the ICT challenge this year. And we are come from the Singapore University Automation Lab. So the purpose of this track is to, obviously we want to recognize when the driver get distracted and getting some alerts so that the driver can focus back into actually driving the vehicles. And the most challenging problem in this track is that obviously we don't have enough data, and obviously the video data with fully labeled for every time frame to do this kind of research. And also it can be very difficult to processing and classifying the video rather than doing image classification. So in this track, given the new data set from ICT challenge, our team performed the research and then submit the result into this track. So we, for the problem formulation in this track, we simply cut the video into several clips, and then which each clip, this is we have the time boundary for each category during the driving activities. Our solution framework consists of 6 steps. First, given the cut video, we have very small clip, and then we use K4 cross-validation technique to train and validation 3 different models. We use the video MAE 2 U-Former V2 models and the X3D models. Then we just simply ensemble all of these models to get the graph prediction of the activity. And finally, we perform some post-processing with and refine the predict score with multi-view post-processing. So in this work, we just simply use 3 models. The video MAE is just simply the extend version of the mass auto encoder, which is just translate from image classification into video classification. The uniform V2 is just a combination of the VIT plus U-Former V1. And finally, the X3D is just a lightweight models. Here we analyze some of the class comparing to the model performance. During our test with the validation set, we can see that the video MAE can work relatively really well for all the classes. But the Uniformer V2, when we train it, we see that it only works for the dash view camera. And based on that, we also trained another version of the Uniformer V2. And we've only focused on the right camera. And it's only work when we have the class talking to passenger at the back seat. And finally, for the X3D,
H3D model, we can simply see that it only works for the right camera only. And the other two dash and rear camera, it cannot work well. Based on that, we simply perform the multi-step post-processing. So first, for every 16 frame, we predict the class of the activity using the ensemble models. Then we filter out all of the activity that had a lower score, that had a score that lower than 0.65, which is just indicated normal driving behavior. In the third step, we then linking and discarding all the normal driving activity, and then for any class that is longer than lambda 2, which is equal 7 seconds, then we then link them together as a single class. Finally, most of the action we notice that it happened around 1 to 30 seconds. Then we only simply remove all of the small interval classification that is less than 30 seconds to get the final predict class for this time frame. And this is just simply the summary of the data set of the SYNC-DD2 of this year. In our full experience, we can see that using the 5-fold cross-validation, the fold number 2 we can get the best result using fold number 2, and it can see that in using the ensemble model, we can get even better result than using just only single models for all these tasks. And finally, we can also try to test with different camera view with different fold. And we can see that the result in accuracy on F1 score, they vary across different fold. So if we only use one single camera view, then it cannot work well. So this is a random process. So finally, we just try to combine all of them together to get the final ensemble result. And our team played the 5th place in the final, in the first test set of the Tracker 3. And so in conclusion, we can conclude that we can use the pre-trained visual foundation model to recognize action recognition tasks. But the most important part is that the correlation between the activity when we link them together. And so we have to use the multiple view ensemble technique to improve the performance for the final result. So that's all my presentation. Thank you very much.
Thank you. The next presenter would be presenting on multi-view action recognition for distracted driver behavior localization.
Yeah. So unfortunately, these authors, they also have visa issues. So we will play their pre-recorded videos.
Hello everyone. Now I'm going to introduce my work. The topic is multi-view action regulation for distracted driver behavior localization. This paper was collaborated after by Xu Yuehuan and Jiang Shuai, both from Beijing University of Post and Telecommunication. I will introduce the work in this first step. Here comes the background of my project. As we all know, distracted driving is highly dangerous, which is seriously harm to the safety of the society. Through my research, I believe computer vision techniques can provide the much-needed solution to identify and eliminate distracting driving behavior. There are some common challenges in this field, such as lack of labels, poor data quality, and low resolution. Those are really high-risk challenges. Fortunately, 2024 AIC Challenge Choice 3 provides high-quality datasets which can satisfy the experiment competition. After the introduction part, I'm going to introduce you the method that we used in this project. Firstly, let's see the overview of our design. You can see this diagram shows how a distracted action recognition method is presented. The system takes videos as inputs and goes through video clip sampling, action regulation classification, multi-view fusion, adaptive thresholding filtering, merging and removing, and post-connection to obtain the final result. After the overview part, let's see the core deep learning network that we used in our design. The purpose of this module is to accurately classify behaviors in video clips and provide accurate classification predictions to support subsequent temporal localization. To achieve this purpose, we choose Video Swing Transformer in this part, which is a transformer-based 3D behavior recognition network. This model not only leverages the global information modeling ability of transformers, but also employs a method of moving windows to connect across windows. It allows the model to focus on information related to adjacent windows, extending the field of perception to some extent and resulting in higher efficiency. Due to a series of advantages of video swing transformer, we select SwingL as the backbone network for behavior regulation. Besides, we adopt a strategy of training 3 praise separately to further improve the accuracy of the model. Now we have introduced our core training module. Here comes our temporal localization module. This module has 3 components. First is threshold filtering, which aims to address the issue of inaccurate prediction due to the difficulty of learning for the classifier. Second is merging and removing, which aims to concatenate short video segments into longer candidate segments. And the last component is further processing, which is designed to further refine the behavior boundaries from coarse localization to fine localization to improve the final recognition accuracy. And here comes our results. Table 2 shows a breakdown on the verification set with different correction strategies. It indicates that the adaptive thresholding strategy is quite effective, significantly improves the score from 0.5066 to 0.6184. And Figure 4 shows the results of selecting top M on the validation set. This figure indicates that the adaptive thresholding is highly sensitive to the top M hyperparameter. And the selection of the thresholds is crucial in locating the regions where the behavior occurs in sliding windows temporal localization algorithm to more intuitively show the effect of our module. The performance of the model is visualized in Figure 5. It's noticeable that our method performs excellently in classification process. This is due to the fact that we fully optimize the outcomes of action regulation from 3 perspectives and employ numerous useful techniques. At last, I want to introduce you the results of our team's work on Test A in AICT 24 Task 3. In this figure, you can see that our work ranks in a relatively high level, and the score of our work is very close to other excellent works. Finally, here comes to the conclusion part. Firstly, we propose a robust and efficient two-stage framework for distracted behavior classification localization based on the sliding window approach, which is suitable for untrimmed neutral driving windows. Secondly, multi-wheel fusion and adaptive thresholding strategy effectively filters our photo detection and promise detections. The post-processing procedures we designed successfully achieve the goal of close to fine localization of behavior boundaries. Okay, thanks.
The final paper would be deep localization using change point detection for temporal action localization.
Hello everyone, good morning. My name is Nefara Vishihab. I'm from Iowa State University. I'll be presenting the deep localization paper using the change point detection temporal action localization. The main selling point of the paper is like everybody was doing fancy stuff, 3 GPU, 4 GPU, 5 GPU, stacking up everything, and then bunch of stuff. In this particular paper, we just did 2 simple things. First thing is using the change point algorithm to find out where's the start and where's the end of a particular event, and then using just a VQA using video chat GPT model to figure out what's the activity is going on. Just like as simple as this. These are like a limitation you can just go through. I'm not going to like go into detail what's that. The main thing is like finding out distracted driving activity, the start and the end point, and then what's the activities actually. And the objective is like the particular thing is like once we get the change point detection, actually the VQ is almost close to real time. It just takes 3 seconds to 2 seconds to say what kind of activity is actually. This is like a data set collection from the three data set. One dashcam 2, one is the dashboard, one is the behind rear view mirror, and one is the upside view. These are like another view, like seeing how the data looks like from a detection perspective. Methodology, as I said, camera view, then key point extraction, and then generate an action proposal, like proposal as in like what's the start and the end time, and then using a VQA just classify what kind of activity it is actually. and then post-processing, like post-processing as in like extracting what the like a video model say, video language model said, and then figuring out the word from it, and then saying it if it's doing right or not. So there are like 7 key points. So we focused on the key points related to face, 17 key points. The key points related to face, hand, and then shoulder, that's it. And other key point related to waist, knee, and then those kind of a thing, they're like little important. This kind of we figured out by a trial and error. They don't significantly or like even slightly improve anything over there. So we just stick with face, hand, and shoulder. How did you do the key point thing? We did a graph-based change point detection. It's kind of a pretty familiar algorithm, change point detection algorithm, and where n is the number of points, usually 1 to 2 minutes of frame, and then we use a L1 matrix to figure out the key point thing. Action, like an action interval. Interval is like the start. Technically, instead of going for the time, we know like how many frames are there in a particular second, or like and then we just wait for the frame number stuff. And then from there we do the p-value approximation. We didn't use the skewness thing because it seems like it was like moving the change point detection further ahead, so we didn't use it. And then from there we say, for example, this is an example how did it then the starting frame number and the ending frame number. From there we back calculated the time thing and then figure out from which second it started and from which second it ended. These are the statistic thing if you care or not in general, but those are like just for the purpose. This is the most like crucial but yet really simple thing we did. We kind of again kind of a trial and error design 3 VQA question to using and asking video ChatGPT model to, and then giving the video, can it tell what kind of activity is going on? These are like 3 questions which it seems like the most relevant to our work. And then this is the like having every activity saying, and then the answer was like which activity is saying I feel like this is the one. And then in some cases it says vague thing. Whenever it's a vague thing, we consider it as a wrong thing because there's no point of saying it is a true or something. And then the event detection thing is that using the change point detection algorithm, this is kind of accuracy. And like and another thing is the event classification literally depends on the event detection. So once the event detection part or the change point stuff is not working that well, it actually impacted our event classification stuff. If you see the event classification in the 3 question, mostly the 3rd question, these one helped. Thing is the intuition is a bit more detailed and like giving it like a really to the point like a question to answer. So in that way one interesting thing is though in event detection part it's kind of a struggle, but because of the VQA design, it's some kind of overcome the issue with the event detection thing, and then somehow like a event detection and somehow the accuracy got bit improved but not drastic improved or something. And these are the error analysis when I don't know if it's visible or not that much. Like how the change point thing specifically accurately prediction going on something visible, yeah, kind of. And if you see the graph, it's somewhere it's got screwed up, and that's where you see like almost half of the times it's not saying accurately where the start and the end time is. And sorry, these are the accurate one, and then these are the place you see it's like kind of a spiking up a lot, and then these are the portion where it's saying not much accurate. Thank you, and if you have a question, feel free to ask.
Are we giving Q&A time?
Yeah.
Welcome. Yeah, all the authors, if you can come on the podium, then audience can ask any questions they have.
Okay, if there's no question, so for all this driving action recognition, I see that you also have like the multiple cameras inside the vehicle. are you considering, like, for example, combining those with some dash cameras? For example, if you see an accident or things like that, it's more likely for the actions within the vehicle to behave in some way. So is there like something that you can consider incorporating into your approach?
I can go a different.
Yeah.
For that thing particularly, we didn't like for our approach. I think we mostly focused on one particular camera view, because other was like, again, the competition was the main issue. If you take all the three cameras together, that's a huge competition.
Yeah.
Unfortunately, I don't have access to that much competition. So
Yeah.
I just focus on the one camera. I think if I'm not wrong, we are focused on the dash camera or right side. I think that camera we are focused on mostly, and that's where we are getting most of the change point accurately going on. But still, I think for the finding the change point, it was a struggle as in like the algorithm was and first thing is the resolution is not that good or like that much accurate for a change point to work really good. It's kind of a real-time thing, so it's not that good. But and then if you want to see like if a driver is responsible or not, it mostly depends if that our like it mostly depends on if we can achieve a good accuracy in terms of seeing which kind of activity is happening. Given that the activity recognition is really good, I think we can come up with something saying if it's a, like in terms of any accident, it's a driver's fault or someone else.
Okay. Thank you, Long.
I think in my case that because our framework already used the multi-view from all the three cameras together for the final prediction. So if we add another dash cam for the outside world, then I think the class definition of action needs to be revised, because right now we may have some new classes for especially for the case that we have an incoming cross, because that will react it will have some similarity between the current classes with the one that the driver react to the sudden change in the outdoor environment. And I think technically we can do it, but we have to redefine all the class that already existing in the dataset.
Okay. Cool. Is there any other question from the audience, either in the room?
Yeah.
Yeah.
Yes.
Yeah. Let's start from the question in the room, and then we'll come to the question on
Sure.
Zoom. Okay.
How accurate do you think?
So the question is how accurate it is for the key points to locate the actions in for the drivers. Yeah, you can come to the mic so the people on the Zoom can.
It's not that much of like good. I think that like the algorithm itself plus the because of the image quality is not that good. It's like said, I think it's most of the cases, half of the time it's accurate and half of the time it's not.
So there's room for improvement.
A lot of room for improvement. If there is an improvement in the key point detection algorithm, then the classification will accuracy increase a lot.
Yeah. Did you try to see if the text hand is behind the steering wheel, that some of those key points would go away, and can you do some kind of occlusion detection and things like that?
We didn't.
Yeah, so we have a follow-up question. So if the hands are behind the wheel, not captured by the cameras, is there some way to like overcome that kind of occlusion?
We didn't have enough time to even go there because the whole key point thing was taking a lot of time. So we didn't explore that part.
I think we have to add key point tracking.
Yeah, there's a lot of a thing we can do, but I think when we are submitting it, we are like at the key point detection, and then we just have the key point detection, but then we need to figure out what kind of a task was going on, like what kind of activity was going on. So we just literally stay with the key point, whatever we have, we jump to the classification.
Okay, we have another question from Zoom. Shreyas, do you want to share a question?
So was any sound-based disturbances also accounted for, apart from video? I mean, apart from images and video?
I don't think sound was really recorded for this.
The sound is not provided with the data set, but if you need to incorporate that in your pipeline, like what modification is needed. So do you want to?
Thank you.
We didn't know.
Yeah. I think they haven't considered that, but
because the sound itself wasn't there in the video.
yeah, the sound is not with the video, but I think the pipeline should be very similar. Okay.
If there information, we couldn't share the sound. If someone accidentally said something, so RB that allow us to share the sound right now.
Yeah, Professor Anush Sharma said that there is restriction in terms of the license that they can share the sound with the video because that will cause some license issue. So yeah, but thanks for understanding. Okay, so that concludes all our sessions for the morning, and in the afternoon we have more sessions for the presentations of track 4, presentations of track 5. We also have 2 panel discussions, and then we have the very exciting awards ceremony, and then we'll go to the poster session. And thank you all for your attention. Let's enjoy our lunch, and then we'll come back at 1 p.m. Thank you. See, I'm already sharing. Right? Okay.
Yeah, anytime.
Okay. Okay, we're gonna start in a couple minutes until like we're waiting some other audience to join, and then we will start track 4. Is the first team ready? Okay. The robust data augmentation and the ensemble method? No? You are, okay. You're the first team, right? Okay, please come and let's wait a few more minutes until, yeah, just maybe warm up. Okay, let's start the track 4 and our first presentation. Please come and present. The title is Robust Data Augmentation and Ensemble Method for Object Detection in Fisheye Images.
Okay. Let me move this to there so the share screen can see it.
Okay, I see.
Okay, you can use the arrow to control the slides. Okay.
And you have 10 minutes.
Okay. Okay. Thank you. Hello everyone. My name is Hùng Dương from VNPT AI. Today I will present our paper, Robust Data Augmentation and Ensemble Method for Object Detection in Fisheye Image, with also our solution for AICTE Challenge Check 4. Before we begin, let me walk through some of the main content that included in today's presentation. First is a problem definition session, which will provide a general concept of the Check 4 problem. This followed by a methodology session in which I thoroughly describe our approach. Finally, I will present the result of our experiment and also some images as a demonstration of effectiveness of our methods. So with further ado, let's begin. Firstly, I will summarize the basic concept of the 2024 AICTE Challenge Check 4 probe. Fisheye cameras, which were previously utilized in self-driving systems, are well known for their wide area coverage. Recently, traffic surveillance system has started to take advantage of the fisheye lenses for comprehensive coverage of road and intersection. However, the trade-off in the strong radio distortion posing the new challenge to traditional object detection algorithm, especially when objects were located toward the edge of the image. The primary object of the project of the 2024 AICTE Challenge is to design a system that can accurately detect the vehicle and region in a traffic image captured by a fisheye camera.
Our methods focus on primarily on data. We analyze the unique characteristic of the fisheye 8K dataset, then search for similar public dataset and experiment with combining its supplementary dataset. We then process the combined data through the state-of-the-art object detection model, incorporating ensemble technique and pseudo-labeling to achieve the final result. As illustrated in Figure 2, the fisheye 8K dataset contains images that are captured from the overhead angle and annotation for small objects. Thus, they are the main criteria for selecting the publicly available road detection dataset. After carefully evaluating the criteria, we narrowed it down to 3 public datasets, including the Visdrone dataset, the MIO-TCD dataset, and the UAV dataset. Figure 3 shows the sample from the Visdrone dataset. As you can see, the camera angle is set a wide view cam angle from above. The size of vehicle is small, and the viewing angle had many similarities with the fisheye 8K dataset. Figure 4 shows the sample from UAV as well as the MIO-TCD dataset. About dataset selection. So we combine each selected dataset with the fisheye 8K chain set and train the CoDTR model on each combined dataset individually. The model will later evaluate using the fisheye 8K validation set, as can be seen from Table 1. Only Visdrone dataset boosts the performance of the fisheye 8K validation set. Thus, we only selected the Visdrone dataset for our further experiment. The synthetic data generation process includes the 4 steps. First, we split the original image into 2 square images. Afterwards, we apply the fisheye distortion effect on each square image using the formula formed from iFishTool. The images are later cropped to remove the dark area. Finally, the new bounding box coordinate are calculated by converting each vertex individually and then selecting the minimum bounding box rectangle of the newly generated convex hull. About the model selection, we select model based on the fisheye 8K benchmark, which reported by the author of the dataset, and the COCO test depth benchmark. The CoDTR and the intern image model achieved best and second best performance on the COCO test depth benchmark respectively, while Jolo W6 used the highest MAP on the fisheye 8K benchmark. The Jolo V9 is newly introduced in model in 2024. For model assembling, we utilize the wave of fusion algorithm. The MAP score achieved by selected model on check-for dataset are present in Table 2. As illustrated, the CoDTR model demonstrated superior performance compared to the remaining model. Thus, our subsequent experiment primarily focused on CoDTR model. Additionally, it is noteworthy that training a synthetic Visdrone dataset yield lower MAP compared to the training on the original Visdrone. However, using the training strategy makes the model more robust to radio distortion. As a result, combining 2 models in the model assembling phase will help boost the final result. Figure 7 demonstrates the difference between the detection made by CoDTR model trained on original Visdrone dataset and the synthetic Visdrone dataset. As illustrated, the model trained on synthetic Visdrone achieved better accuracy when object was small and located toward the edge of the image. To increase diversity, we partitioned the fisheye 8K dataset including both the trained set and the validated set into 3 folds by selecting cameras with different ID and dividing them into the new change set and validation set. The four are divided so that ratio of object quantities between the change set and validation set remain approximately around 70-30. Afterward, we train on CodeETR model on each fold. The result evaluate using the official evaluation system. To generate a pseudo label, we combine prediction made by CodeETR trained on 3-fold created using the k-fold speed strategy mentioned above. The newly generated label will let user train CodeETR in order to achieve better performance. We adopt two strategies. In one strategy, we use a pseudo label as a validation set to evaluate CodeETR trained on Visdrone and FishEye 8K combined dataset. In the other one, we combine the pseudo label with Visdrone and the FishEye 8K dataset and train the CodeETR on this new dataset. Note in this step, there is no validation data. We simply select model obtained from the last epoch. As demonstrated in table 4, our first strategy boosts the MAP score on the check-for test set by 2.17%, while increase the 4.79% were recorded when using second strategy. So we assemble 7 models, including model Zolo 9, Zolo W6, internal image, CodeETR synthetic, CodeETR 4.0, CodeETR chain plus val, CodeETR chain plus val plus pseudo using the web-of fusion method. This method were proven highly effective in previous competition. Model CodeETR chain plus val plus pseudo were chosen as the primary model and assigned the highest weight because it produced the highest MAP result. The example have to add objects that primary model miss and eliminate some fail detection. Since a competition metric use the F1 score, we need to remove some object with low confidence score. We set a threshold of 0.3 to 0.4, and for the nighttime image, the confidence score threshold were low to between 0.2 and 0.3. And our compute pilot achieved the F1 score of 64 to 0.06, so an increase of 7.02 compared to training solely on the FishEye 8K dataset. With our proposed method was secure the first place in track 4 of the 2024 AICTE challenge. So thank you for your listening.
Thank you very much. Thank you. Thank you for the first team. Yeah. You can introduce them. The second team, ID number 50, the title Road Object Detection Robust to. Okay. Okay. So let me read the title again. The road object detection robust to distorted objects at the edge regions of images. Thank you.
Hi, I'm Buksu from Nota. Today we are gonna discuss the issues and solution of object detection in edge regions of imaging. As you can see, we'll start with a brief introduction to the task and then explain the methods we used. And finally, we'll present the result and conclusion. This image captured by FishEye camera highlights the central challenge we are addressing. FishEye cameras are great for traffic monitoring because of their wide field of view, which lets us cover large areas with fewer cameras. However, in FishEye camera images, objects become increasingly distorted towards the edges, making detection difficult. Additionally, due to this distortion, non-target objects like street signs are often misclassified as target objects as car. Let's start with an overview of the methods we used in our study, categorized into three main sections: task-specific method, general methods, and ensemble methods. We aim to address the two challenges mentioned in the introduction through task-specific methods. We use slicing-aided hyperinference to tackle edge distortions and semi-supervised learning to resolve misclassifications, resulting in significant performance improvements. Additionally, we further enhanced performance through general methods such as data augmentation, histogram equalization, and super-resolution, as well as by using the weighted boxes fusion ensemble technique. Now let's move on to our task-specific methods. One key method is slicing-aided hyperinference, in short, SAHI. This involves partitioning the original image into slices and resizing each slice to fit the model's input size. By doing this, small objects that might otherwise be missed are enlarged for better detection. The predicted boxes from each slice are then aggregated for the final detection, improving accuracy for objects at the edges of the images. Another task-specific method we use is semi-supervised learning. We assign store labels to non-target objects to enhance the model's ability to differentiate between objects. By training the model with both target and non-target objects, we reduce misclassifications. To accurately assign these two labels, we use the CodeETR model trained with the LVIS dataset. As you can see, there were many cases where a person on a sign was predicted as an actual pedestrian, or a cone was predicted as a pedestrian. However, after training with the store label data, we were able to reduce these misdetections. Let's start with the general methods. We used rotation data augmentation. We apply several basic augmentations, including random flip, precise, crop, and auto augmentation. Given that fisheye camera images can have various orientations, we also use rotation augmentation to make the model robust to objects viewed from different angles. As shown in these images, these augmentations help the model handle different visual perspectives and object placements more effectively. We also use histogram equalization. Histogram equalization is a technique used to enhance image contrast by redistributing intensity values. It transforms images with a narrow range of pixel values into high contrast images. This improves the detection of objects in dark or low contrast areas. The graphs illustrate the pixel distribution before and after histogram equalization for both day and night scenes, demonstrating the enhanced contrast. And we use super resolution. Super resolution is another technique we use to enhance image quality. We upscale training images by 1.5 times and test images by 2 times using the stable SR model. In the training phase, doubling the size would take too long to so for efficient learning during the competition period, we scaled it to 1.5 times. This technique helps improve the accuracy of our detection models by providing higher resolution inputs. Finally, we use an ensemble methods to combine multiple detectors. We create several detectors using various techniques and then apply weighted boxes fusion to average the coordinates of the bounded boxes. This ensemble approach leverages the strengths of different models, improving overall detection performance. The images demonstrate how WBF combines predictions from different models, resulting in more accurate detections. These models used in the ensemble, the outputs from the various methods described above were used in the ensemble as appropriate. Here are the experimental results. As shown in the table above, the baseline is the CoDINO with a Swin backbone, and we can see a significant performance improvement when applying task-specific methods. By also using general methods and ensemble techniques, we were able to achieve a final F1 score of 0.6196. By addressing the two main issues with our proposed task-specific methods, we significantly improved the performance of fisheye camera object detection. Additionally, by combining various methodologies to enhance detector performance, we achieved a high final F1 score of 0.6196. For future work, we will focus on tackling additional challenges and reducing computational complexity through model compression techniques like knowledge distillation and network pruning. And yeah, thank you.
Thank you very much. Thank you. Thank you very much for the second team presentation. And the third team is improving optics detection to fisheye cameras with open vocabulary pseudo-label approach. Please welcome. Okay.
So good afternoon, everyone. My name is Long Pham, and I'm from SKU Automation Lab, Sun Kwon University. This is our team solution to the track for this year. So I will just go straight into the problem. So we can see that fisheye cameras is everywhere in the street, but mostly for observation. We actually don't do this for data extraction or doing any kind of processing, and mostly for the operator to manually monitor the traffic areas. The problem for this kind of scenario is that we don't have enough label. So no one thing of labeling the fisheye image for object detection or segmentation. And also we have the distorted or scale object. Obviously, so it's very hard for us to actually do the labeling by ourselves, by human, especially if the object is very small. So in this track, we are very fortunately to have the label data set, and we can begin to perform research on this field. When we encounter with the AIST fisheye AK data set, we encounter several problems by ourselves. The first one is that we discovered there are a lot of from missing label, especially for the bike and pedestrian. When the bike is nearly near each other or overlapping, and we only have one label for a whole group of bytes. Then we have some shift bounding box and some inconsistent between the small truck and the car in consecutive frame. In order to so our team solution is just to tackle data, not actually doing anything to the model. So in this work, we come up with a whole framework for training and then inference based on the YOLO work for doing the pseudo label. And then we also use CycleGAN to enrich the data set for nighttime scenario. So I just go through all of the modules together. First, the YOLO work, which is just the new YOLO model that incorporate the open vocabulary to recognize the unseen object. In this case, we just simply use the pre-trained model of the YOLO world and then input the label and also the alias of the potential class in the fisheye dataset, and then we generate a bunch of pseudo label, which in our experience we can mostly solve the problem with like inconsistent labeling or some missing data. Obviously, for the case of some of the small object, we have to manually adjust the corner a little bit to make it more fit into the actual object. Then the problem begin with the nighttime scenario. So obviously, we can think of a solution for enhancing the dark illumination into a bright one. But we noticed that the daytime image is color RGB and the nighttime is only black and white. So if we try to convert from nighttime to daytime, we lack a lot of data. So obviously the result will be very bad. So the reverse way is more feasible, is that from RGB, you can easily convert to grayscale without losing any kind of detail or texture. So we simply do that by using CycleGAN, and we just simply retrain using a very small subset of the data set that we have. In total, we get all around, we can double the number of images of the fisheye 8K, and we have around 16K image. Combined with the pseudo label from YOLO world, in total, we got around 280K of labeled instant object. So we simply use the data set, our collected data set to train mostly the YOLO family. So we start with YOLO world, YOLO V7, and then YOLO 8. At that time, the YOLO V9 is too new, and in the end, we don't have enough time to try the YOLO V9 models. And here we do some application study with our proposed solution. First, we just add some bunch of background image from Coco dataset to get some kind of like non-label object or the object that we don't want to appear into the detection, and it's already improved the result. We also try to add into our CycleGAN data generation and pseudo label from YOLO world. And in the end, we can see that we can improve the accuracy very significantly using only the YOLO world model, which is a very old model. And considering the problem with small object, there are two solutions. First is SAHI, and the second solution is very simple. We just increase the trending resolution of the image, also the inference image size. And we just simply do that and increase to the full HD resolution. We can get some minor improvement, and when we ensemble all of those three models together, so we can detect small object and large object using each separate model at separate input side, and the ensemble result can get us a very, very high accuracy both in AP and F1 score. And this is the actual submission of our team on 40 submission, and we just collect all of them together, and we processively try different configuration setting and inference setting to get the highest score possible. And in the end, our final solution is just to assemble 3 YOLO D6 model, 3 different sizes. And we noticed that if we try to infer with a very large image size, that our GPU can handle around 2560 with some confidence threshold of 0.6 and IOU 0.5, we get the highest F1 score of 0.6194, which is just 0.002 with the second team. And we actually don't have to do anything like using very big model or complex scenario. And this our conclusion for this task is that even though this is a new task, a new CAP data set, but if you have good data, you can refine the data, then you don't need a big model to perform to get a high accuracy. And if you can see that because we use a very low lightweight model, then if we try to get the real time, then we can easily extend the result to a different real time scenario. So that's our team solution. Thank you very much.
Thank you very much. Okay. Thank you very much for the third team. It was very interesting, and the third team had very small difference between the second team. Yeah. Okay, the fourth presentation, enhancing road object detection in fisheye cameras, an effective framework integrating SAHI and hybrid inference. So we're gonna play the
The
video.
pre-recorded, yeah. Unfortunately, they also have visa issue. So.
Hello everyone. Today I'm to say our work on enhancing road object detection in fisheye camera, an effective framework integrating SAHI and hybrid inference. This is certainly crucial for intelligent transportation system as it tackles the unique challenge posed by fisheye camera. We offer a broad field of view but introduce significant image distortion. This problem is the focus of Track 4 in AICTE 2024. To address this, we use the fisheye 8K dataset for training and the fisheye 1K event dataset to evaluate our solution performance. Here are methodologies addressing the problem defined in Track 4 of AICTE 24. Involve a multi-step pilot. We begin with data preparation and train several object detection models using various data augmentation techniques. Subsequently, we integrate prediction from models employing SAHI inference with those that do not. The final result are then refined through our broad processing strategy. In data preparation, we leverage the WordScape dataset for pre-training some of our models. This dataset provides a diverse range of scenarios, which helps our model generalize better to unseen data. Besides partitioning the original fisheye 8K dataset with 9:1 ratio, we also partition the fisheye 8K dataset into day and night subsets to address the specific challenges posed by different lighting conditions. The analysis for each dataset we use shown in this table. For object detection, we employ a combination of state-of-the-art models, including CODAT, YOLO-R, YOLO-V6L6. We enhance this model with data augmentation techniques like multi-scale training, flipping, and also mosaic to improve their robustness. The result of evaluation on validation data of each model on various datasets is shown in this table. To tackle the challenge of detecting objects at varying distance from the camera center, we introduce a novel distance-aware loss, DAL function. This function prioritizes objects farther from the center, where detection is more difficult due to distortion. Our approach begins by dividing the camera image into grid boxes. It assigns a pre-calculated attention value stored in a list we call V. We then modify the intersection of a union RU loss in CODAT with our proposed DAL. The alpha here, modulating factor balance the generalized RU, GIOU, loss with an additional loss term. Ensuring that boxes farther from the center are penalized more if they do not match the ground truth. The detailed loss function is shown on this slide. You can see that here. To further enhance accuracy, we use weighted box fusion to ensemble our model prediction. This technique leverages the strength of various models and reduces their weakness, leading to more precise and dependable detection. The comparison of our ensemble models is shown on this table. For small objects, such as pedestrians and bikes, are often more challenging to detect, requiring a lower confidence threshold in our object detection model. Conversely, larger objects like cars, buses, and trucks are detected with a higher confidence threshold. So, to optimize the balance between sensitivity and precision, we apply post-processing techniques to refine our prediction. Different confidence thresholds are used for small and large objects, ensuring more accurate and reliable detection. Our approach has achieved promising results. In the AICT Challenge 2024, our solution secured the fourth position among over 50 participating teams, demonstrating its effectiveness in real-world scenarios. Thank you so much for your attention. I'm very happy to answer any questions you may have. Thank you.
Thank you very much for the fourth team's presentation. And the fifth team, low light image enhancement framework for improved object detection in fisheye lens datasets. Please present.
Thank you. Yes. I can use this to change this. So hello everyone. So today I would like to present about our team solution for Track 4 AICC challenge. So as all the team already mentioned about the challenge of the dataset, so I just briefly to introduce again. So you can see from here that the main problem of this dataset is about the image resolution and also the low light scenario. So you can see from here that many object is labeled but very small, and the scale is a problem. And also our team we concentrate on the low light scenario because we think that for this application the nighttime monitoring is very important for the traffic monitoring. And also we think about all the application also, for example, like construction monitoring, and then the nighttime is very important. So that is what our team focus on. So here the proposed solution. So we think that because we think the low light scenario is a problem. So we try to find other model to solve this problem. So recently there's one of the very good model like GS80, I think CPPR 2023, they published, and then they mentioned that they have the ability to convert the nighttime to the daytime. So we try to use this model also. And beside of this model, we try to implement the super resolution when in the infrared. So the first is the image enhancement. So for example, if we just try the normal NavNet model, this is the very well-known super image enhancement model. We can increase the daytime, but for the nighttime, it's very difficult to see the difference. So we try to apply this kind of model for convert from nighttime to daytime, and actually we receive a good result compared to without this kind of model. And also, like I mentioned, we try to use super resolution also, and actually this is we time for scale, so it's very heavy to use this kind of model. But we tried two times submission with this model, and the result very good. And actually, I think because we need real-time detection, but if we can try the offline detection, then the super resolution working very well. So this is the result that we run our baseline model. So you can see from here that if we use the raw data set, it's difficult to achieve the baseline. But if we apply the image enhancement and also convert from night to day, then we can outperform the baseline, and that is the current result. And by using ensemble, and also we train the K4 and also apply the weighted box fusion, we can achieve the 5th place. And also you can see from here that there are some mislabel. Of course, it's difficult to label because when I check the data set, I can see that some of the image contain the object, but it cannot be labeled because it's too blurred. So I think if we apply super resolution, then the problem is the model see the object is a true detection. but we cannot label because it's low resolution and we cannot label at that time. So that's all for my presentation. Thank you.
Yeah. Next. Okay, the last presentation, FEDET, an effective traffic object detection framework for fisheye cameras. And we're gonna play the presentation video because also the visa issue. Okay. So this is our last.
Hello everyone, this is Luoxing Shuang, and today I'll be introducing the effective traffic object detection framework for fisheye cameras developed for Task 4 in the AIRCT Challenge. This project was a collaborative effort by Luoxing Shuang, Cui Zhe, and Su Fei. We are from Beijing University of Posts and Telecommunications. I will introduce our work in the following 4 sections: challenges, methods, results, and conclusion. First, I'd like to introduce some challenges. This picture shows some hard dampers in the dataset. For instance, fisheye cameras introduce target rotation and shape distortions. Moreover, there is a significant disparity in target features between daytime and nighttime scenes. What's more, small objects at the image periphery are also difficult to detect, and street scenes frequently contain numerous densely parked stationary vehicles. Next, I'd like to introduce our method. Let's analyze the dataset. Figures A and E show that the dataset has an unequal distribution of categories. Figures B and F demonstrate the presence of numerous small objects in the dataset and a significant diversity in the scales of different categories. As can be seen in figures C and G, there are also significant differences in the occurrence preference of different categories across different time. So, we use many data enhancement methods like cropping, rotation, scaling, mosaic, color manipulation, and histogram equalization. This picture shows our pipeline. We experimented on 3 object detection models: ULO-V8, QDTR, and InterImage. Each model performs well at detecting different classes of objects. We implement distinct different training and inference processes for images taken during the day and night. Next, I'd like to introduce our iterative post-process. This is flowchart of confidence score refine module. We divide the image into 3 regions and use histogram matching techniques. Figure A shows the original distribution of confidence scores across the specified distance intervals before adjustment, and Figure B illustrates the frequency distribution of the confidence scores following the application of refinement techniques. This is an example after we use the statistic objects processing. Next, I'd like to introduce the third part. Table 1 presents comparative results of object detection models evaluated on the validation dataset. ULO-V8 shows strong performance, and Table 2 shows results on the test dataset. Table 3 shows the ablation results on test dataset. Finally, we ranked 6th in the leaderboard. And this picture shows the visualization of the final submission results, from which it can be observed that our detection results are quite accurate. In conclusion, we analyze some problems that need to be solved urgently in the visual eye detection issue, and we propose the advanced object detection framework named FEDATE. Thank you for your listening.
Thank you very much for all the presentations, and I would like to invite the presenters, all the presenters here, so that we have some Q&A. Please. So if there is any online attenders, please, if you have a question, send your question. And is there any questions from the audience in the room? Oh, okay. Okay, there is one. Please go ahead.
Generation of light from daily. How do you think of the problem of light of the car? Is there an organization that provides light or reflection from the world? Because it's like the problem of light, and artificial we don't see that, so can you generate this type of data?
Okay, the question is in converting from generating the image from night to day, right? Day to night, yes, sorry. Day to night, yeah, or both. Okay, so because of at night there are lights, the bright lights, and when you convert from day to night images, how do you generate the lights? Did you try?
So actually, if we look at the data, there are actually two types of night. I just simply say night, but actually there are two types of night. The one night is that everything is very dark. The car light is not very brightly affect the overall. It means that the car headlight, they are car headlight, but they are not shining directly to the camera, so everything is fine. And the other scenario is that we have the same situation that you said. So our team solution is simply that we split two subset of night image, and we train two separate cycle gain model for each type of night. Then we just simply mix them together, and we try to. And I mean, it's mean like we try to mix two ways together to correct some kind of like we have some range of non bright and then bright. So that is the way we handle it.
Okay. Okay, one more.
Speaking about the night to day, so at that model, actually, we checked the paper and then they mentioned this is kind of generative AI. So when they already trained this model with the big from night to day, so they already learned something. So there are three kind of I think data set. This is trained on the LLV2. So this kind of data set already learned on the large amount of data set from night to day, so it like automatically convert the night time also. So this is we just try and error in our solution.
Thank you very much. Okay, is there any? Okay, please go ahead.
Yeah, so have you tried any like camera on distortion method when you run the and how does that work?
Sorry, try distortion model.
Yeah, like on distortion.
On distortion.
On distortion first and then run detection. Will that improve
Okay.
or not?
Okay. Did you try distortion first and then you try to improve?
I think this problem is because of the data set. The data set should give the camera setting about that also. So I think there are one Q&A question and then you mentioned there
Yes.
we not provide the camera setting.
We don't have it.
Not a problem.
We don't have the camera models. Yes, that's why.
So actually, we also did try that solution once, and in our case, we just guess the camera calibration parameters. The problem is that some of them work, but some not, because we have around 25 different camera angles. We only try the easy one and the very hard one where you got the vehicle that has some rotated. So it's this part is upside down, and this part is correct orientation. When we try our guess calibration is kind of very weird image, so in the end we just scrap that idea and go with a normal idea.
Okay. Thank you very much. Okay. So I would like to ask just one more question. What was the hardest challenging thing in this challenge? Would you like to share? Like out of, yeah, go ahead, please. Everybody has something to say, right?
I think the voice, the view of camera, and the size of vehicle and precision in image is very small, especially when object is towards the edge of the image.
Okay, the small objects. Okay, all right. Thank you very much for all the teams for your all hard work, and all the best. Thank you.
Okay, thank you for all the teams of track 4. So let's take a 5-minute break. Currently it is 1:51 p.m. Let's come 1:52 p.m. Let's come back at 1:57 p.m. and then we have 4 papers for track 5, which is helmet detection. If you are the presenters of track 5, please come to the stage. We can check your slides first. I'm not sure if Pranamesh is online.
Yes, I'm here.
Oh, good. Yeah. So maybe in 5 minutes you can be the facilitator for track 5.
Yeah, sure.
What time is it on your side?
Oh, it's 2:30 a.m.
Oh, yeah.
22.
Sorry for keeping you late.
That's fine. That's fine. Yeah.
Okay.
Yeah.
Hello everyone, I'm delighted to present our paper titled Robust Motorcycle.
Okay, Pranamish, I think we have most people here. I think we can get started with track 5.
Okay. Thank you, Thomas. So first of all, I would like to invite you all to the track 5, which is the helmet violation detection. We have 4 papers in this presentation, and I think the third paper will be like on-site, while the other 3 will be for the pre-recorded version. So the first paper is the paper ID 36, which is on robust motorcycle helmet detection in real-world scenarios using co-TTR and minority class enhancement. So yeah, over to Thomas.
Hello everyone, I'm delighted to present our paper titled Robust Motorcycle Helmet Detection in Real-World Scenarios using Co-TTR and Minority Class Enhancement at Track 5 of the AICT Challenge, part of the CVPR Workshop 2024. Firstly, I will present the problem definition and the challenges associated with it. Then, I will introduce our method, which includes the detection module, a symbol module, minority optimizer, and virtual expander. Following this, I will share the experimental results and conclude with our findings regarding to the effectiveness of our methods. So, the problem we are addressing is the automatic detection of motorcycle helmet uses in real-world traffic scenarios. This task is crucial for enhanced traffic safety and ensuring legal compliance among motorcyclists. Helmets significantly reduce the risk of head injuries and fatality in motorcycle accidents, making their use a critical safety measure. Enforcing helmet law helps in reducing the severity of injuries during accidents, thereby saving lives and reducing healthcare costs. Additionally, automatic detection system can assist law enforcement agencies in monitoring and enforcing helmet law effectively, thus improving overall traffic management. Our system processes video footage from traffic camera as input, analyzing each frame to detect motorcycles and their rider and identify whether or not they are wearing helmets. The output is a set of bounding box around detected objects classified into different categories based on helmet uses. However, one main challenge in spotting motorcycle helmet use is dealing with complex traffic conditions when there are many vehicles, since get crowded with overlapping objects, making it harder to detection model to identify individual riders. Also, factors like different lighting conditions, weather change, nighttime fog, and various camera angles make detection even harder. These factors add unpredictability, so we need strong algorithms that can handle different visual environments. Another big challenge is the imbalance datasets. Often, there are many more examples of riders with helmets than those without. This imbalance makes it tough for models to learn well because they tend to favor the majority classes. Fixing this issue is a key to improving the accuracy and reliability of the detection system, especially for the less common classes. Our framework integrates several advanced components to provide a comprehensive solution for automatic motorcycle helmet detection in real-world scenarios. It begins with Co-TTR model, which processes video frames to detect motorcycles and their riders, effectively managing class imbalance and enhance detection accuracy. To further improve performance, we employ an ensemble module using weighted block fusion to compile results from multiple inference routes, enhancing scalability and adaptability. The minority optimizer addresses dataset imbalance by adjusting confidence threshold to improve recon and underrepresented classes. Additionally, the virtual expander reduces false negative by generating additional bounding box at specific confidence threshold, fine-tuning precision and optimizing recon. This integrated approach ensuring our system can handle complex traffic conditions in parallel datasets, providing a robust and reliable solution for automatic motorcycle helmet detection. In this slide, I will talk about our detection module, the core of our motorcycle helmet detection system. This module utilizes the Co-TTR model, renowned for its robustness and complex visual environments. CodeETR collaborative label assignment strategy effectively manage class imbalance by allowing multiple box candidates to associate with the same ground truth box during training. This enriched model learning process, especially for underrepresented class like motorcycle violations. To handle different weather and landing conditions, we use multiple checkpoints and image size during inference. This helps the model to adapt to challenges like rain, frost, and glare, ensuring it works well in various scenarios. By processing images at different scales, models stay accurate even with the change in object size camera angle, making it reliable for real-time traffic monitoring. Let's dive into the symbol module, which significantly boosts the accuracy and reliability of our helmet detection system. The symbol module employs a technique called weighted box fusion to merge results from multiple detection models. Unlike traditional methods that might discard some predictions, weighted box fusion considers the confidence score of one bounding box to create an average box. This approach greatly enhances the quality of the compiled predictions, reducing errors and increasing accuracy. By integrating results from different models and different routes, the symbol module ensuring that our system adapts well to various conditions such as camera angle and weather change. This makes detection more stable and reliable even in complex traffic scenarios. The next main component of our framework is the minority optimizer, a key component designed to tackle class imbalance in provided datasets. One of the major challenges in helmet detection is the imbalance distribution of classes. As shown in the chart, there are many more instances of motorbikes and drivers with helmets compared to the passengers without helmets and passengers with helmets. This imbalance can lead to biased models that perform poorly on underrepresented classes. The minority optimizer addresses this issue by adjusting confidence score specifically for rare classes. By lowering the threshold for these underrepresented class, we can improve recon without significantly affecting precision. This means our system becomes better at detecting instances that otherwise misses, such as passengers without helmets. The minority optimizer identifies classes which few resemble and set lower confidence threshold for them. This ensures that even low confidence detection for gray class are considered, thereby increasing the chance of correctly identifying them. Let's move on to the virtual expander, another critical component of our helmet detection system designed to reduce false negative. Our detection process, one recurring issue is the inconsistent in detection helmets, especially in the challenging conditions. For instance, the same rider might be detected without helmet in one frame and with helmet in another. This inconsistency can be due to factors like multiple riders in the single boarding box or poor visibility conditions such as fog. The virtual expander addresses this by generating additional virtual bounding box at specific confidence. This approach helps to capture instances that might be missed by the primary detection model, thereby improving recon. By carefully adjusting this threshold, the virtual expander ensuring that we minimize the false negative without significantly impact to the precision. This method involving creating extra bounding box for objects that model might have low confidence in detecting. The virtual box helps to ensuring that even uncertain detections are considered, thereby increasing the chance of correctly identifying helmet uses. We test our system using the AICTE Challenge 2024 datasets, which includes 100 training videos with detailed annotation for motorcycles and riders specific in helmet uses. Our performance was measured using mean average precision metrics. Starting with the CodeETR model alone, we achieved a baseline MAB. Incorporating with weighted box fusion technique, improve our MAB by effectively combining prediction from multiple models. Adding the minority optimizer further boosts our MAB by adjusting confidence threshold for gray classes, enhance recon without compressing precision. Finally, the virtual expander refines our result by generating additional bounding box to reduce false negative. Our integrated approach secured first place on the AICTE Challenge 2024 Trackfire leaderboard, outperforming over 40 teams. This underscores the robustness and reliability of our system in the real-world scenarios. In conclusion, we developed a detection framework using the CodeETR model to identify helmet rule violations, adapting well to imbalance data and various conditions. We also introduced two key algorithms, the Minority Optimizer with improved recon for underrepresented classes, and the Virtual Expander with reduced false negative. The enhancement significantly boosts our system MABs. However, the Virtual Expander, while improving MAB slightly, increased computational demands, affecting the scalability and cost effectiveness. Despite this, our system remained highly effective and lead the leaderboard. Thanks for watching. If you have any question, please contact us.
So thank you. So we have the next presentation, which is paper ID 17, an effective method for detecting violation of helmet rule for motorcyclists.
All from China Mobile. Today, we'd like to share our resolution, an effective method for detecting violation of helmet rule for motorcyclists for 2024 AICT Challenger Track 5 here. Motorcycle becomes one of the most popular means of transportation, especially in developing countries. For example, sales values of motorcycle in India grows around 4 times from 2017 to 2021. The maximum growth ratio is around 130%. On the other hand, the high speed of motorcycle is larger than 50 kilometers an hour, and their speed in city is from 2005 to 50 kilometers an hour. It can cause heavy traffic accidents. We found that the motorcycle fatality rate is 5 times more than the passenger cars per 100,000 registered vehicles, and helmets could protect the driver and the passengers or even save their life. So 2024 AICT Challenge Track 5 aims to develop a method to detect motorcycle helmet violations, which makes a substantial contribution to improve public safety. In this competition, 9 objects should be detected. The first object is motorbike. Driver with and without helmet is called D helmet and D no helmet. The other objects are shown as follows. The distribution of chain datasets is visualized. Severe data imbalance can be observed. Instances of class 3, 5, 6, 7, and 8 are all less than 100. Even only one annotation of class 7 is mislabeled. Most instances belong to class 0 and class 1. From the sample of the dataset, we can find parts of motorbikes and the riders are occluded. All these challenges makes this competition difficult. We select 2 SOTA models, Dino and CodeETR, to detect objects. Heavy data augmentation, including mosaic and mix-up, are used to solve data imbalance during training. Test time augmentation is also employed for test time inference. To improve the performance further, we ensemble these 2 models and fuse their results for final submission. When selecting models, we focus on the transformer-based models compared with the SOTA models at 1333 times 800 resolution and find dyno performance best. And then we try code DTR with higher resolution and achieve better. Model in simple is a common used tricks for improve performance and robustness of model. Therefore, we compare the different fields registers to merge their predictions. NMS obtains almost 0.0 score gains and then weighted box fusion. Different structures also make around 0.02 score gains than two models with the same structure. Finally, our method achieves 0.4824 score and ranks the second place in the leaderboard. In the end, we visualized the prediction result from our model. Thank you very much.
Okay, thank you. So the third presentation is paper ID 5, which is motorcyclist helmet violation detection framework by leveraging robust ensemble and augmentation methods.
So, hello everyone. My name is Hung Sung from VNPT AI. Today I will present our paper, Motorcyclist Helmet Violation Detection Framework by leveraging robust ensemble and augmentation methods, with also our solution for AICT Challenge Check 5. So I will skip this slide because previous team had talked about it. So only use the person and vehicle detection submodule with number of classes as defined by check 5, not feasible due to a severe imbalance of class P2 and P0. Therefore, we, in addition to developing the person and vehicle detection submodule, we also develop the head detection submodule, object associate module, post-processing for checking module, and score correction module to improve the MAP score for class P2 and P0. We will go through the detail of each module in next slides. The object detection module includes two submodules, namely heat detection and person and vehicle detection. To achieve the best result, we use a test time augmentation technique and web fusion as sample method to combine the state-of-the-art object detection module, such as Zolover 7, Zolover 8, ODTR, and Everson Depth. We propose to use the object association module to assigning on possible pair of human motorbike and human head. This output serves as input for subsequent checking module, which try to check a group of vehicle, driver, head, and passenger using the same checking ID for them. Receiving output from object association module. In this module, we propose to use customized checking module to capture vehicle direction information. This information is then integrated with output from head detection submodule to potentially identify presence of P0 and P2 on vehicle. This slide shows how we detect possible P2 object and possible P0 object. The number of P0 and P2 object is much smaller than that of the driver and P1 object, leading to the low confidence score and reduced overall MAP score. To address this, we apply the offset value to a confidence score of P0 and P2 instant in video where the objects are present. Based on experiment with data over two validation set, The offset value are set to 0.1 for P0 and 0.2 for P2. Details this score correction scheme are outlined in algorithm 1. Due to the few sample of P2 no helmet and P0 no helmet, the model overfit to and perform poorly on validation and test data set. To address it, we create more frames with diverse background on the red glasses using the training data. This helps the model distinguish between the similar frame with different objects. We use manual and automatic copy and paste methods, adding 45 samples for P2 no helmet and 58 for P0 no helmet. We use a Photoshop tool to copy and paste the head in the same image to create P0 and P2, as you can see in B and D images. To generate image contain P0 and P2 with higher quality, we use a segmentation model to extract human from other image and paste them into the target image. This table shows the impact of various methods such as copy and paste augmentation, example, and score correction on MAP performance. Our data augmentation improves the MAP score by 3.34% over the baseline. We also apply the web of fusion example technique to 11 checkpoints from 0/7, 0/8, and CodeETR model. So the table shows our solution has achieved the final MAP score of 0.4792, ranking third among participant team Track 5 in AICT Challenge 2024. So thank you for your listening.
Thank you for the presentation. So we have the last presentation of this track.
Hello everyone, this is Hongpu Zhang, and today I will introduce a cross-to-fire two-stage element detection method for motorcyclists developed for Track 5 in the AICT Challenge. This project was cooperative effect by Hongpu Zhang, Zhi Cui, and Fei Su. We are from Beijing University of Posts and Telecommunications. I will introduce our work in the following 4 sections: introduction, method, results, and ranking. The first one is introduction. As you can see, there are several problems in the data size, such as low video quality, varying object size, and complex traffic conditions. Therefore, it is difficult to detect those 9 categories. Due to the varying object size in videos, detecting the whole image at once will miss the targets and lower the accuracy. Therefore, as depicted in the figure, we have designed our framework, which divided this task into 2 stages. The design of each stage will be detailed in the following. In the first stage, we utilized a cross detector to firstly identify the boarding box of people and motorcyclists, which can eliminate the interference of backbone. In view of the higher accuracy and faster inference speed of the ULV bar, we adopt the ULV bar as our multi-core detector. Upon obtaining the overall boarding box of people and multi-bags, we employ CodeETR as a 5-grade detector to detect the 9 categories. Actually, this task can be divided into 2 tasks: distinguishing whether a person is a driver or passenger, and discovering whether they are wearing a helmet. Therefore, we exploit the 2 classifications as shown in figure. One bridge is to classify driver or passenger, and the other bridge is to determine whether they are wearing a helmet. This is our 5-grade detector. To filter out the false positives, we propose 3 post-processing stages. For the score fusion, we determine the final score by combining the first and second stage confidence scores to retain the correct targets. Second, we employ deep thought for tracking creation to reduce the number of false positives. When the frequency of a certain category exceeds for 15% of the total detections, we correct it to this category across all frames. Different detectors perform differently on different objects. We use model fusion to merge the result of different detectors to improve performance. To verify the effectiveness of the proposed framework, we conduct application experiments. Table 1 reports the result of different detectors in the second stage, such as EULOVEBA and CodeETR. Table 3 shows the contribution of these models. The first row to the last row, MAP gradually increased from 31.9% to 39.4%. In the end, we get the 7th place with 39.4% MAP. Thank you for your listening.
Thank you.
So thank you for the presentation. Maybe then we can take few questions. If from online, if someone wants to post a question, they can put in the comment box, and also like offline if people have questions.
I think the previous presenter from for the presenter of track 5, do you want to come up and can answer the questions from the audience?
Yeah. Are there any questions from the audience? Maybe Thomas can also facilitate. I'm not able to.
There's no question from the audience at this point. Do you have any questions from for the author?
Yeah. So I have like one question. Like obviously we have seen that the class imbalance is one of the thing that a lot of teams were trying to handle because of the issue. Like any specific thing that you basically found regarding the congested videos or the low light conditions, something like fog or night times, which maybe you try to handle it to improve your accuracies?
To address it, we try to add more P0 and P2 object into image using Photoshop tool and segmentation model.
Yeah. So, but going forward, do you think like any improvements that we can do to particularly handle the congestion conditions or the nighttime conditions, or maybe the foggy conditions if you had seen?
Yeah, it means like for the class imbalance issue, you see like for certain class, there are only very few objects. For certain class, you have seen a lot of objects. Have you tried any techniques to improve your model?
We try to add more objects in class like P0 and P2.
Oh, using augmentation.
Yes.
Okay. I think we have like one question in the, it's not a question related to this track, but it's something like, will the recording of the workshop be available for subsequent viewing? That maybe Thomas can answer. I'm not sure if that is going.
I saw this question earlier. So the recordings of the workshop will be provided by CVPR and it will be available maybe a month afterward, after the workshop. Yeah. But for all the presentation today, we have their slides and their paper and also their poster will all be put online after the workshop.
Thank you. So maybe
there is
thanks
a
to all
question
the
from-
participants. Any
Yeah,
other questions that we have?
Yeah, there is a question from the audience.
Okay.
In general, the different, the multiple passengers, were they specified like passenger 0 was always in front of the driver, or was the positions of them relative to the motorcycle driver?
Yeah, so the question I think is for Pranamesh you. So the question is that for the different passengers, they're labeled as P0, P2, things like that. Are they relative with the driver of the motorcycle?
Yeah. So the P0 is basically any person who is sitting in front of the driver. So this can typically be kids who are sitting in front of the driver. P1 is just immediate after the driver. If we have a rider who is sitting at the back of the driver, that is P1. And if we have another rider who is also present after P1, then it is basically taken as P2. So we have that schema accordingly of P1, P2, and so therefore, like you will see like a lot less people with P0 or P2, because actually like by rule it's not allowed, but although in the developing countries you will see like these kind of cases are there, and there are also penalties which are given if you have like 3 persons in a motorcycle. So this in that way tries to basically address that. And another reason why we had these things of P0, P1, P2 separately, because currently we have like the violation rules which differentiate between if the driver is wearing the helmet or not, if the passenger is wearing the helmet or not. So therefore we had that division also in our classes.
Okay, I hope that answered your question. Okay, if that's all the question, we want to thank all the presenters again for track 5. Finally, we have 3 independent research papers. Some of the presenters here for the independent research paper. Yeah, so maybe you can come up to check your slides, just make sure it works, and we'll just have like a 2-minute break.
So which paper are you on? 116 26是吧？OK， 你会用PDF 对吗？对，用这个 OK， 我是第2个，对，你用是第2个。好，谢谢。Let me just check the slides for. Okay. Oh, this is by Professor Gochu. Okay, this is the third one. This is the third one, and the first one is a video. Yeah. 我就直接开始吧。
Okay, so hello everyone. This is I'm Yizhou Wang from the NVIDIA Metropolis, and I'll be the host for this session, for the independent paper presentation and QAs. So this year we have 3 independent papers. So we have let's welcome the first one. The first one is named as PVCAP, 3D Dynamic Scene Understanding through Open Physics-Based Vocabularies. So that's the ED for this paper.
Hello everyone, this is Cao Minfeng, and today I'm very honored to present our paper, PVCAP, 3D Dynamic Scene Understanding through Open Physics-Based Vocabulary to AICTE Challenge Workshop. And now we shall begin. The presentation has 5 main parts. First, motivation. Second is proposed method. And third is experiments. Fourth is application study. And finally is conclusion. So let's begin with our motivation. Recently launched a visual language model such as CLIP have demonstrated impressive capability in training solely on inherent scale image-language pair. Moreover, almost all visual language models have tackled indoor objects under controlled illumination and camera view. However, our outdoor 3D environments are time-varying, uncontrolled scenes under natural phenomena. Therefore, captions from such unseen scenes and objects are hard to obtain in a SOTA one-shot algorithm, resulting in insufficient caption. Therefore, we proposed a method that comprised of multiple groups of deep learning and visual language modules for enriched and refined 3D caption. First, the proposed 3D CPP module consists of three major groups as shown in Figure 2. Each of them are defined as follows. Firstly, a single image is used in the design module to segment and recognize various objects and other scenes. From each, multiple objects predefined classes like cores are used to refer to predefined physical size in width and height, and the object locations, that is x and y, real-world coordinates obtained. Secondly, the depth module estimates the depth map with non-dimensional scales from a single image. To convert such non-dimensional to physical scales, output of this module is used for object approximated physical scales. These results are forwarded and merged into captions. Finally, input image are encoded to obtain image features where text are recognized through constructive learning. Such texts are used for part of overall captions except for physical scales of objects. Second, iterative VQA, that is IVQA, is proposed to further refine the caption for an image. The figure 3 depicts a looping scheme between the IVQA and Nissin. The list of object events consists of words with similar meanings that describe an object or an event. The answer with the highest causal similarity score is considered the best. To ensure the most accurate selection, all words with similar meanings are looked through until the best answer has been chosen. Together, they form the proposed PBCAP. The proposed integration used a large language model, a so-called LLM, namely GPT-4, which incorporates the physical scale from 3D CPP and the captions generated by IVQA. The output of this complies semantic segmentation along with corresponding location and descriptions expressed in a language-based segmentation format as a list of object description and the bounding maps of the object in pixels. The output of 3D CPP is a caption that includes details about physical scale, that is, object size and distance, and IVQA contribute additional description that capture the overall dynamic conditions with adverse weather conditions to provide contextual information for the LLM. The final result of caption refinement is an enriched caption that encompasses the information about road conditions, water levels, and related object locations. The instant order of disease is achieved based on the depth map of the DDEF and the spatial correlation between objects enriched through the iterative grading prompts. This section describes the efficiency of the proposed 3D CPP, and in the table 1, there are several example images with the ground truth caption, and as you can see, the proposed 3D CPP generates a more detailed caption which describe the 3D scenes better than BLIP2. And the experiment 2 describe the final PV cap output by combining the IVQA output and the 3D CPP output. And from the segmentation output by the 3D CPP, the PP caption can capture better 3D detail. And here's the application study. We show some field case proposed by 3D CPP. To conclude, we have proposed a PV cap system for enhancing 3D scene understanding through Enrich caption.
Okay, thank you for the presentation. Let's go to the second paper. Okay, it's called KI-GAN, Knowledge-Informed Generative Adversarial Networks for Enhanced Multi-Vehicle Trajectory Forecasting at the Signalized Intersections.
Hi everyone, I'm Chu Hongwei from University of California, Riverside. Today I will present our research about trajectory prediction at signalized intersection, and this project is a collaboration with North American Toyota Life. My presentation will mainly divide it into 4 parts: the introduction, methodology, experiments, as well as the conclusion. Firstly, let's have a quick review of the research gap and the contribution. During our literature review, we found that current multi-vehicle or multi-agent trajectory prediction model often ignore how traffic lights and other information except the position of the vehicle affected to the driver's behavior or the vehicle's behavior. So we proposed the KI-GAN framework to develop that method. In addition, we also found in the traditional GAN-based method, they always, in the social porting part, they are always designed for the pedestrian. So there may ignore several information of the vehicle, such as the type of the vehicle or the distance between the cars. Here is a quick review of the KI-GAN model. In the architecture, we can find we do not only use the position of the vehicle, we also integrate the traffic light information and the motion information, as well as the type information into the whole pipeline. We use all of this encode feature to this wipe night. And another most contribution of our project is that we developed the wipe night. Here, let's take a quick look at the wipe night. As I mentioned above, it is designed for the multi-vehicle scenario. It's not only consider the relative position of each vehicle as well as the velocity of each vehicle. Due to the time limitation, I ignore the mathematical part. But if you are interested in this one, you can discuss with me during the Q&A session or the poster session. And we also try to apply some attention mechanism into this framework to test whether our webnight is better than the others polling method. Then here is the qualitative result of our KI-GAN. We can find in different kind of traffic, it performs always great, especially in the dense traffic scenario. Here is the quantitative results. Compared to some other multi-object or multi-vehicle, multi-agent trajectory prediction method, our method performs better on the SIND data set. By the way, the SIND data set is the only data set that provided all of the information we need to use in our model. So we can only test our method in this SIND data set. And the upper four method only designed based for pedestrian and ignore some traffic information and vehicle information. But the method proposed by Lee's Live, this method use some traffic information as well as the vehicles information. But compared with that, the KIGAN also performs better. We assume that may due to the VibeNet we designed for the GAN method. Then we also did some ablation experiment. We try to remove all of the encoder and test the performance. The results show all of the encoder and all of the information will give some positive effect to our final result, especially the traffic information. So the traffic signal information, it is the most important in the trajectory prediction, especially the signalized intersection scenario. And we also compared our VibeNet with other polling net, for example, the social net and the hidden poll net. The result also show our proposed VibeNet benefit to the whole pipeline of the KIGAN. And here is some conclusion. Firstly, KIGAN present a great result in trajectory prediction at the signalized intersection, and different kind of encoder and the information also made some positive influence to the whole framework, and the VibeNet is also workable for this task, and our results show that this model performs better than the previous one. And our group also do some research based on this. Firstly, as I do not mention, this project only considered all of the vehicles, the cars, the trucks information, and ignore the pedestrians information. So in the future, we hope that we can develop some method not only designed for the vehicle, but also all of the agent, all of the object at the intersection. And we also to develop some model, especially for some specific scenario. For example, the yellow light dilemma zone scenario, as well as the red light running situation. If you are interested in that, we can also discuss offline. Thanks for your listening. I'm Chu Hongwei. If you are interested in our work, please do not hesitate to let me know via the email or my LinkedIn or some website. Yeah, thanks so much.
Yeah, thanks for the presentation. Then let's go to the third paper.
So already opened. Okay.
Hello, everyone. My name is Mukir Yustin. Our research team members Anjarg and Professor Mukhtargat from United Arab Emirates University. I will present our research name Simple in Place data augmentation for surveillance object detection. Traffic dataset or other low resource dataset often suffer from class imbalance, which hinders the equal detection of the objects across different classes. Here is fisheye 8K dataset class object instance distribution graph. Therefore, we propose a method seek balance of the classes by augmenting objects in the same place which preserve realistic appearance of the image. By doing it, class objects which allow number of samples can affect model training process. In this image, we show the proposed technique for the image. We grouped together image captured from the same camera and augment each image by placing objects instance from other images in the same location of the original position by ensuring non-overlapping original objects. We made an experiment on 2 public data sets for this surveillance. First one is the Fisheye 8K dataset, which has 8,000 images. A second dataset is a UAE TTRAC. It has 140,000 images. We sampled 450 images, a subset from the Fisheye 8K dataset's transit, which is only 8.5%. Fully identical to class distribution of the full Fisheye 8K dataset. We select 7,140 images, a subset from the UAE TTRAC datasets. Datasets transit and UAE TTRAC datasets label are originally dedicated for object tracking, which is not suitable for object detection. Therefore, we find active road region and lured out other regions. We selected 3 values for augmentation. Those values represent number of objects from each classes that was placed on the images. As a result, number of instances for each classes increased to these values. Here we show training results of YOLOV 7 model, and on the small set of Fisheye 8K dataset, the MAP 0.5 score improved from 0.47 to 0.5. Here we show training result of YOLOV 7 model on the small set of UAE TTRAC dataset. The MAP 0.5 score improved 0.7 to 0.71. In conclusion, to enhance model performance on stationary camera-based dataset, we focus on optimizing augmentation strategy tailored to each class, employing effective model ensemble, ensuring dataset quality and balance. These steps collectively contribute to improving overall model accuracy. Thank you for your attention.
And now let's start the Q&A session. Can I have the authors of the papers? So any questions from the audience for these 3 papers? Sure.
Sorry?
The question is your project depiction.
Yeah.
The information or into the 3D or into the augmentation or what is the
It's just the 2D information.
So the question is like the input of the prediction include the 2D information or like orientation information, something.
It's just the 2D information, the position, pre-processed by other algorithm. The data set is collected by the drone, but what we can use, since the data set do not provide the information, the image information, they only show some position, the point, and the node information. We can only use that information. Yeah. We try to predict we try to observe the 12 ring, and it's lasts about 6 seconds. So we observe 6 seconds and predict the following 6 seconds or 9 seconds the result. Yeah. Yeah.
So any other questions? No. Okay. Maybe I have a question for also for the behavior prediction paper. So I think you have compared with several like methods about that area, but I'm not sure if you have tried some like typical methods like TNT or dense TNTs and apply some modules specifically for the signal like signalized intersection data or some more pre-processing for your method to test it out the performance.
When we developed that method, we also noticed that the TNT, the vector night, and the dense TNT, they performs also great. But their method is based on single vehicles pedestrian. It is a little bit difficult to apply some multi-vehicle or multi-agent task to that pipeline. But in the future, we hope that we can specific focusing on one vehicle, one agent, and test the performance whether it's better than the dense TNT or other single vehicles pedestrian. Yeah.
Thank you. So there's no questions. Then we'll like take a 10 minutes break. Right? Maybe 10 minutes break.
Yeah, cool. So if that's the case, we conclude all the paper presentations for our workshop. So let's have a break of 20 minutes. We have a coffee break. So then we will have our panel discussion on ethical AI and also the intelligent transportation systems that will start at 3:15 p.m. And after that, that will be the exciting part of our workshop, which is the award ceremony. And after that, we will have a poster session in the other building, which is the building art. Yeah, thank you.
Oh, Professor Shi.
Show the picture. Yeah,
Picture.
I'll take it in front of the.
Sure, yeah, okay.
右手边还有吗？
Yeah, we can do like how we want to see.
You mean take a picture?
Yeah. Okay.
How to?
So we may have to go to. Can you use that mic a little closer to your table or something?
That's all. Single. I want to maybe together and the single. Yeah. It's okay.
Yeah.
Okay, I think it's okay. We will together. Yeah.
So go to the
section.
Our track.
Yeah. 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 Okay.
Or move your laptop.
Okay. So
One use.
Yeah. Okay, thank you. Maybe we'll together.
Okay, thank you. Yeah.
Yeah, let's take picture all of us.
There are some people here about. Yeah. Okay, thank you. Thank you. Thank you. Yes.
Yes, Tom.
I'm not leaving. Oh, yeah. This is my phone call. Yeah. Okay. Oh, oh. For your now, here. Yeah. I mean, I was talking to them as well, like I did made a bigger so, we are like really, we are going to put more resources and any more highly of the college. Good for you. So if you have anything helping with that, that will be fun. I could continue with it for that. So sure, and I will mostly speak over the we use a lot of that, but for that to make at least the market a thousand. Okay. So oh yeah, so that we can work on some because that the people the people leverage the people. For the generation of people working in China for cameras and models, we already have a lot of like scripts, everything makes sense. For the next year, I think we spend data with people looking at this. Even the same time, working about what the guy we will have a debrief after this. That's fine. So you use your laptop then? What do you think?
Yeah, then idea from Dr. Gotu, I think it's a good idea. We can somehow pass the laptop
Okay.
slightly,
Okay.
like passing a mic.
So I'll
unmute that.
Yeah, sorry, we forgot to turn on your mic. Oh, let me mute here. Yeah, go ahead, anyone.
All right, so sure, I'll use this mic. All right, so is this on? Is this on?
Yeah.
Okay, perfect. So AI City Challenge was developed from the beginning to be a forum to push the boundaries of what AI can do to improve smart cities. And most of the tracks that we develop for AI City Challenge are always keep this in mind. How can we push the boundaries of the state of the art, but in particularly on problems that would be useful in a smart city, things related to transportation, to retail, to safety and things like that. So if you look at all the different tracks that we've done so far and all the tracks from this year, all of them have some sort of aspect of trying to improve society and improve how we do things.
Yeah.
So I think this is an important challenge, and the idea is obviously, as always in the field of AI, that you try to make the world a better place, that you develop technologies that, as you say, will help society, will advance society. But with anything, this is commonly my observation, that anything that potentially helps society can also be a potential danger to society, and so it has to be, done responsibly, and this is obviously a question how to assure that there is no misuse of data and etc. for the wrong purposes.
Yeah, adding to what David and Daniel have suggested. So from AI City start point, we have the vision of push the boundary of the society. And initially, AI City Challenge start from very specific point. We are focusing just on vehicle detection. We are thinking like transportation would be a perfect example of the AI City use cases, but turns out as we explore more and more, they are not just vehicles, not just outdoors. So we keep expanding our territory. So initially we're only starting with the vehicles. Now we have both vehicle and people. We have both outdoor and indoor. And now even now we have both real data and also synthetic data. So we keep mixing everything together. We believe the combination of everything and explore different territories can born a new innovations. So that's our direction. And I think even in the future, we're not settling up here just for, I hope just not just for videos, but like Daniel have mentioned that for CVPR, cameras are supposed to be the ultimate sensor. We are also thinking about some sensor fusion. There are some other recent challenges in the AI City domains. They have a sensor fusion as a very big topic, and we are thinking we're fusing multiple cameras as well as fusing different data types.
Okay, yeah, I think in terms of the social benefit of the AI City Challenge, for track 1, definitely we are focusing on improving the retail store, for example, the shopping experience using automatic checkout. In terms of the warehouse, the management, and how to improve the efficiency to save the operation cost for running a warehouse. And also for tracks 2 to 5, they are all centered around improving the safety of intelligent transportation system, the safety of driving, how to detect the anomalies, and how to prevent the people, for example, from being drowsy and causing accidents. That will also help improve the general public's safety in terms of traffic. So I think that's the value of our challenge. Okay, I think the next question is more interesting. So about privacy protection, like what kind of ways we can apply for all these Trojan track to provide the privacy? For example, when we have a security camera, how can we protect the human faces being used for like unintended purposes, or like the license plates, even like how can we prevent this from being leaked while we have a like comprehensive data set and well labeled with well labeled annotations? Yeah, David.
So again, this has been a challenge that we took head on from the beginning of the AI City Challenge. Even from the first couple of years, we identified this as being an issue, a potential issue, and we made sure that our data sets did not contain identifiable people and vehicles, or that we got permission from the people and vehicles to use or the people to use their liking in the data sets. In particular, a lot of our strategies have been around using angles or distances that would make the people not recognizable, or if let's say the vehicles were close enough, or the people were close enough, hiding by blurring the faces and the license plates of vehicles and things like that. More recently, we've moved a lot to generating data sets by using CGI. So in those cases, then those are no longer an issue. Privacy is no longer an issue because all the actors are not real. And finally, again, more recently, we've started developing data sets like the one developed by Woven by Toyota that uses actors. So they're paid actors that have agreed to be recorded for these data sets, and we have their permission to do so. But yeah, in general, this is a very important topic. Obviously not a good idea to use video from that was recorded without the consent of the people in training AI models and things like that.
So maybe to add to that, what David just said, indeed, it's a very important problem, and it's also not an easy problem. We've worked on a number of data sets where, just by law, you're required to blind out the license plates, the faces, etc. That is, I find, still fairly easy because fortunately, the problem of detecting license plates in images and detecting faces is a fairly solved problem. So this is good for us because it means we can create massive amounts of data and automatically make sure that license plates and faces are basically blurred out. But it's, as you mentioned, sometimes it's more complex. For example, sometimes you may be able to recognize a person even though you don't see the face, because you can recognize how they move, etc. So there's a lot of information in people observed in videos beyond just the face that would allow you to identify who you're looking at, right? And how to somehow anonymize that is much more difficult because we cannot just blur out the movement and the whole person, because then the whole challenge of person detection, if you blurred out the person, is a little bit not working. So there is a bit of a trade-off that the data set has to be useful so that you can actually train detection, tracking, etc. algorithm, but it should be sufficiently anonymized, and that's not easy. And then you, as David said, you can go with synthetic data, but then often there is the sim to real gap, that if you train something on synthetic data, it might not actually work in the real. Like for the SLAM stuff I presented, we often find if you train a SLAM pipeline in a synthesized world, it will typically not work in the real world, because the real world is just more complex than the simulation. And then one option is, like David said, that you pay actors to do it. But then the question is, do you get sufficient diversity in this? If you have 5 actors, can they cover all conceivable humans in all conceivable appearances and etc.? So this is a difficult challenge and indeed an important one. Yeah.
Yeah, I have a follow-up question. So if the faces are blurred and for applications like if like a soccer game, everyone wearing jersey, or like in a factory, everyone wearing the same uniform, like without face details, it's very tricky for these kind of cases. How can we approach this? Yeah.
Yeah, I just want to add on to what David and Daniel have said. So it takes efforts like to protect privacy. I remember during the presentation of track 3, one of the audience asked questions, how about we use the voice to identify the activity? And it's kind of a voice is like you may not notice that it's about information that needs to be protected. So it's a part of the privacy that somebody is very easy to miss. And when we organize all those data sets, we took all those into consideration. Like for track 3, we removed the voice. Otherwise, for example, you can hear the driver is saying, I'm reading a book or driving something. You can use that to detect the activity. So removing the voice obviously make the challenge harder, but that is what we have to do. And can researchers is pushing the boundary to perfect the algorithms can make the privacy protection more achievable.
Yeah, I have one thing to add. For example, we can also explore some new like sensors, like some infrared cameras, like some LiDAR. Those kind of sensors does not really include that like images of the faces or license plates. So those kind of data will like play a very important role to protect the privacy. And also, as Thomas mentioned, when we have a lot of players in the like playground and wearing the same like
Uniform.
uniforms, so we can be able to like distinguish them by some like the post information, the gate information from them to also it's achievable to be to be used in our like AICD challenge something.
And maybe to add something about the privacy protection, something I often find is that there are regulations in place, right? Government regulations that may be different from country to country, and they govern as to what you are allowed to store, what data you're not allowed to store. And sometimes I find these regulations are a little bit behind the times. To give you one example, years ago, we developed, this was about 10 years ago, we developed a scanning device that used a set of RGBD cameras mounted on a rig, and you push a button and it goes around a person and you get a fully detailed photorealistic 3D model of the person. The regulations stated that we have to delete the images, but we could keep the photorealistic 3D model. And that's obviously a little bit stupid because you can resynthesize all images from the 3D model. You know, it's so photorealistic, you could recognize the 3D model, right? And then obviously you realize that these data protection regulations are completely behind the times, that whoever developed these regulations doesn't understand what we can do. And this is on a much larger scale true for deep learning, right? We can train a neural network with tons of data. And then if they say, oh, but you got to delete the data for privacy reasons, well, if you keep the trained network, you've seen works where people are able to recover training data from the trained network. So obviously the idea that once I remove the training data, it's all good, that is too simple, right? Because it's somewhere hidden in the weights of your neural network. That information that you gathered from the training data is there. And then you have a generative AI that can synthesize a real person. And you think, wait a second, where did that guy come from, right? And even if you delete the training data, that may not be sufficient really from an ethical perspective. There is still a privacy issue.
Okay, thank you.
One more quick thing to add. So I just want to come back to what you were saying earlier about it's really important that we think about what could be used to identify a person. And, we think about faces and we think about license plates as being very easy to identify a person, but gait is something else, right? So if you have captured someone in your data set that walks with a limp, then it's very easy to identify that person again, right? So that may be an identifying mark that really needs to be protected. And so we really need to think a little bit outside the box of how we anonymize these data sets and what we need to do to ensure anonymity.
And if I may add to that, there's one caveat. The more we anonymize the data, the worse the performance of the algorithm in the end, right? So there is this weird trade-off that we're facing. If we anonymize more, the performance will likely go down, right? And so that's a difficult kind of compromise to find.
Okay, thank you. I think that help us move naturally into the next topic, which is about the fairness and bias issues. For example, like Professor Daniel Kramer said, like different countries may have different regulations. For example, at Europe, there is a GDPR, which is pretty strict, but maybe in other Asian countries is less strict. So you will collect a lot of people of like a certain races. And that if you train on this kind of data set, and then you apply it on a different country, you may not have very good accuracy or things like that. Another possibility, you have a lot of volunteers, and these volunteers are all students. And what if you are applying this model to elderly people? And that may create a discrepancy as well. Like, how can we address this kind of data problem?
So I think very often stories are interesting to illuminate a little bit the difficulty and the challenge. So there's one story, a good friend of mine is in Munich, Albrecht Schmidt, a professor of HCI. And he recently told me that there is a paper apparently from a team in China where they wanted to understand how humans behave in everyday life. So they basically just took a little village in China with 10,000 people and tracked every single person for, I don't know, several months or something, right? And he said, well, I mean, that data set is worth gold if you want to understand human behavior, right? At the same time, according to German regulations, it's completely impossible to do anything like that. You cannot just track the whole population of a small town, right? This violates any kind of sense of privacy that the German government would have or the Germans have. And so you come to a point where you can do certain research in some countries that you cannot do in other countries. And so there is a bias somehow that comes in.
Yeah. Let's see if we have any thought to address this.
Yeah, I'm thinking those discrepancies in the different areas exist anyways. So I'm thinking maybe the synthetic data could be a way to solve and to bridge the gap in between. But like I mentioned, synthetic can create data set like for under different regulations, different circumstances, but then apply model trained on synthetic data set back to reality, there will be a gap in between. That is a different challenge.
So actually, that kind of issue is commonly happens in a lot of different areas, not only those kind of AICD challenge applications. Also like image, even simple like image classification, we have in a like image data set, we will have different like class distributions for different classes, different object classes. So we have several kinds of like method to solve those kind of imbalanced data set or
we can call it long tail problems. So we can try to use those kind of ideas from that domain and borrow some of the techniques to here. Like we have, even if we have a little bit, just a small amount of data for like European countries, so we can try to do some for example, simple example like reweighting, like resampling the data, or some do more like just simple data augmentation, or yeah, we can develop more, of course, more advanced techniques to solve that kind of issue. So yeah, I think that might be yeah, that's a solution for that.
And of course, the most important part is we should really be thinking about this as we design new data sets, right? And we tend to do that a lot here.
Yeah.
I see the challenge. Just about every year, we're coming up with a new data set or an expanded data set or something like that, right? So as we design new data sets, either by recording scenes in real life or synthetic data sets, our choice of subjects, our choice of scenarios needs to be varied enough to try to cover as many aspects of society as possible. So we're always keeping that in mind. But that's something you guys can all think about as well if you're going to design a new data set in the future.
Okay, thank you. So we still have one last question, one last topic to discuss. Actually, there are two aspects. Like at AICT Challenge, we have developed so many different data sets, and all these participating teams, they contributed their technology. So how can we avoid like potential abuse of our data set and the resulting technology? Like, for example, we have the multi-camera tracking data set. How can we prevent like people using this data set for like illegal purposes? Or like how can we prevent people using the technology? Like, because all the code of the teams, they are on GitHub. How can we prevent people using this code to do like illegal business, things like that?
Do you want to start?
I want to. Yeah, I think one important thing we can do is to use the license. Like for all the AICT Challenge, we collected all the data in December, and we spent almost a month to draft all the data license for each challenge track. We make sure that for each challenge track, the data license are reviewed by our legal representative, and make sure that for all the misuse of our data set and potential resulting technology will not be used for this kind of purposes. And we also, our legal team is alert to to monitor the people that are using these data sets. And also we have a very strict process to accept application to our challenge. EJO is helping to monitor that as well, to make sure like all the participating teams, they are from like a legal research and institute organization. They have the email domain name is from a legal organization before they can use, before we send our passwords to them. So there's some measures we're actively taking. Yeah.
So to some degree, we can only take so many precautions, right? So eventually we release the data set and someone can use the data set however they so please. And we release our codes and someone can use those codes however they please, right? So part of what you said is also very important, is we need to keep track, and try to identify if someone is using these in the wrong way, and then potentially go after them legally. But ultimately, it is the responsibility of you all. It's the responsibility of everyone that downloads our data sets and uses the codes developed by teams submitting to the AICT Challenge to guard and be careful how they use these codes and the data sets. To, you are ethically bound by the license that you signed in how you use the data sets and how you use the codes. So keep that in mind.
And to add to what David said, it is complex and there's only so much, as he said, one can do in terms of misuse, right? Either you don't disclose anything, then that prevents any kind of misuse, of course, but it really doesn't advance the field much. And the whole point of, disclosing information about methods, about data, source code is really to advance the field. And this is also the core aspect of the AI City Challenge, of course. But there is, misuse cannot be fully avoided. Even with license regulations, a lot of the source code that we put online over the years, we initially put it under GPL license, thinking that that would prevent any kind of commercial use. Well, over the years, I've seen many companies who have very actively used all our codes. I don't want to name the companies, but it's lots of, big companies. And I found they don't really care about license regulations. And when you approach them, they say, oh, I don't know about the licensing, but yeah, that's your code that we're running here, right? And they're often extremely naive about this. But then on the other hand, I see, what can I do? It's not like I'm going to start a legal battle with some big corporation about the use of the code or not, right? And the other side is that the GPL license actually has the effect that even the beneficial use of the code doesn't happen, because the companies that might do good things with the code don't use it because it's GPL licensed, right? And so we're now increasingly moving to a more BSD or MIT license so that we can say, well, everyone can use it. And then you kind of hope that it will be used in a good way and not in a bad way. And yeah, I think the only thing we can do at that point is really to raise awareness of what are good uses and bad uses of artificial intelligence.
Yeah, just want to add to that. I do agree that if we don't do anything, there's no risk. But if we do want to push the boundary, and we need, there are risks. Like AI City Challenge has been doing, is we encourage the community to open source their code so that can benefit everyone. Everyone can keep working on the code from the winning teams that's shared online, so that we can push the boundary even quicker. I think that's still gonna be what we're gonna keep doing this in the future. But like David has mentioned, like all the researchers working in this domain needs to be conscious about protecting the privacy, don't misuse the data set and stuff. And from AI City Challenge preparation side, for example, the data set, when we collect the data set, if any people participating in the data set collection, they have their bio information exposed, we're gonna have the license properly signed with the agreements. And for any, for example, the roadside cameras, we do the facial blurring so that the facial recognition cannot be applied and the face won't be recognized. AI City Challenge is gonna keep doing that, and hopefully we can keep pushing the edge safely.
There's one aspect of data misuse or possibly not quite legal use that is omnipresent in our society, right? Everyone celebrates the success of large language models, and everyone celebrates the success of things like Stable Diffusion. But then you look into what were they trained on, who actually owns that data, and if it's things like Wikipedia, is it okay that a company uses all the knowledge that is in Wikipedia, creates an LLM, and makes loads of money with that, right? And Wikipedia doesn't profit. And as you know, this is a very complicated, aspect of data ownership, etc. Is that a misuse? I don't know, but I'm sometimes a little bit surprised how little people actually think about ownership aspects in this field of who actually owns the data and what people then use it for.
Okay,
with that, I think that left a lot of room for us to think about these challenging problems. And it's not only the questions as like the challenge committee that we need to be aware of. We also hope that the participants can also brainstorm these questions with us and how we can improve our challenge while keeping the usage in a safe way. Okay, thank you all. Let's give applause to all the participants of our panel discussion. So now let's move on to the panel discussion of the second topic, which is intelligent transportation systems. Let's welcome our panel discussion members. We have Norimasa, we have Professor Gochu. We also have David.
Okay. So let's quickly switch gear to a new topic, ITS. So actually, like I mentioned in the previous discussion, AI City Challenge starts with the ITS problem from very small point by detecting the vehicles. And this year we have track 2, 3, 4, and 5. 4 tracks all focusing on transportation, both safety and efficiency. So in the ITS domain. And in this session, I think we are very lucky to have all those brilliant minds and brilliant expertise together on this table. So we have Norimasa Kobori, Dr. Norimasa Kobori from Woven by Toyota. They are the owner of Track 2, traffic scene description and analytics. And we had Anuj Sharma, hopefully he can join later in this session, who are the owner of Track 3, naturalistic driving behavior recognition. And we have Dr. Gochu from United Arab Emirates University, who is the owner of Track 4, road object detection in fisheye cameras. Right? And we are very honorable to have David Kuhn here, who is from FHWA. So this is a very, very good opportunity to hear from what David see and perceive all the technology we are discussing here. So I think we can start it by, so for Track 2 and Track 4 owners both here, those are 2 new tracks and very innovative and eye-opening actually, in my opinion. So how about we start with sharing some incentives behind creating those new data sets? And is there any unique story to share?
Okay, maybe I can start this, okay. So hello everyone, I'm Norimasa Kobori. I'm from the Toyota, and also Toyota created a new company, Woven by Toyota. So actually, our company is now making the smart city next to the Toyota's driving course. And then that city is exactly, we have the digital twin environment. So we have the real environment, at the same time, digital environment. And we are thinking that in the future, especially like automated driving or transportation, we can more, how to say, leverage from the more infrastructure, new like infrastructure. So therefore, we are exploring that a couple of like experiment, and then actually the next year we will open the city, and before that we were also shooting the data and then release to the public to encourage the people and also the advertisement of the urban city itself. Yeah.
Okay. Hello, everyone. Thank you. This panel discussion, and I'm Mukhtar Al-Kocha from United Arab Emirates University, and we have published this fisheye 8K dataset last year at the CVPR 23 at the same workshop. And obviously, fisheye camera has wide coverage area so that it can like monitor whole intersection, big intersection with single camera. That is the biggest, biggest advantage of it. And
using that, you can actually monitor the whole intersection motion, but we're not talking about like identifying someone there, but it's for detecting the objects on the intersection. It's good enough. And obviously using single camera reduces the cost and maintenance and everything. And I feel very grateful that in this CVPR workshop, our track has lots of participants and people have interested in it. And some of the people have already told me that please continue this challenge in the next year. So yeah, that's all. Thank you.
And my apology, like we do still have Dr. Prathamesh Chakraborty online still. He's to my surprise still energetic enough to stay up this late. He's from India time zone or stay up this early. And he is the owner of Track 5, detecting violation of a helmet rule for motorcyclists. So Prathamesh, how about you share some stories so that David can have a better idea of Track 5 as well?
Yeah, so thank you, sure. So yeah, one of the thing is
just a second. Yeah, we can hear you.
Yeah. So one of the thing in Indian traffic conditions, like we think like cameras are basically the most important sensor that can be of lot of help, because in these kind of conditions, we do not have the typical lane-based driving where the other kind of sensors, something like loop detectors or the radar-based sensors can work the best. So therefore, having cameras to do a diverse task, starting from like vehicle detection to some more advanced and particularly problems which are specific to these developing countries regarding safety. So something like this, like helmet violation, as like one of the team also pointed out, like we have like a lot of like motorbike drivers in such conditions, and they are the persons who are basically like more prone to injuries whenever we are in a crash because they are open to the entire environment. So in that way, I think like having the AI-based solutions using cameras can have like a lot of applications in all the fields of transportation in such conditions.
All right, thanks, Prathamesh. So basically, David, we're really glad to have you here. So basically, this year we're going to have all kinds of challenges. Like we have the object detection from fisheye cameras, which is a very hard task, and we have object detection for a particular class, like the driver versus passenger, helmet versus no helmet. We also have the language model captioning on a video clip. So now we want to hear your opinion on those techniques, like or is there any trends or anything going on from within FHWA and stuff? Please share with us. Thanks.
Yes, thank you. So certainly, I think that the history of the IIC challenge really reflects the overall history of how computer vision has been applied to road transport and to how we're thinking about it in Federal Highway Administration. So if you go back, 10 or 15 years, when I first started getting involved in research with Federal Highway Administration, and we were very focused on vehicles and vehicle tracking, and our ability to use computer vision was very limited. We were able to look at, very small clips, usually very highly designed experiments. We did a little bit with driver monitoring, but it was, again, in very structured research environments. And then, going back about 10 years, you started seeing some new techniques that allowed you to look at larger amounts of data. We started getting the naturalistic studies. And from there, everything sort of opened up in all directions. So now a lot of our research and the research that are in the challenges here aren't just looking at drivers in private vehicles, but you're looking at pedestrians. You're looking at different sensor types with the fisheye cameras, and you're looking at the whole range of things that might be on the roadway in very complex environments with the motorcycle helmet data. These are things that we're looking at in Federal Highway Administration too. So we're looking at all sorts of types of traffic that are in the roadway, and the form factors and number of ways that people travel has really expanded considerably in the last 10 years in terms of micromobility. So you see electric scooters, different forms of electric bikes, and everything in between, as well as more things that might be, robotic or, not human operated in the roadway. And so this makes a very complex environment. And certainly computer vision is a major mode for being able to identify and study this type of work. And, at some point, a lot of this can actually be used in safety and mobility applications in real time, but there still is a lot that you can do in a research environment before you build those sort of edge devices. I'll just stop there for now.
All right. Yeah, thanks a lot for sharing those. We do have Dr. Anuj Sharma joining us, who's the owner of Track 3, and please jump in anytime if you want to see anything. All right, so I've just threw out a hard topic, right? So I do know there's a challenge started by US DOT, the intersection safety challenge, where they are saying if existing equipments can achieve certain accuracy. So my question is, with all those technologies we're exploring, researching, and developing here, accuracy at the bottom of the day would be the thing we are focusing on. So do you think, any of you, right? Do you think current accuracy is good enough, or how far away from the accuracy that can move the needle, that can impact both safety and efficiency of transportation system?
Well, actually, our team is just starting this year, and then accuracy-wise is still improving. And then one motivation is a collaboration with the insurance company. Like a simple accident is basically we can be replaced by the AI. And then actually currently the insurance company is doing that manually doing the description. And then this time we structure that all this description activity. And then we make some a semi-automation, which means that some annotator is just checking the box, and we can make that some description. But as you see that the result, still there's a gap. And then also the description doesn't cover the metrics. One a description is covered, but one description doesn't so much cover for the traffic safety. And then that part is still we need to improve. And then that is also the interesting point. And then after we achieve this, we want to connect to the prevention. Yeah, this is our what we are thinking. Sorry,
Okay, my point is looking at the problem in a reverse way, Shua, is that depending on the accuracies the applications would develop. So for example, right now in vision-based technology to identify crashes, we might not be accurate in detecting every single crash, but if you have camera on an intersection and you can identify near-miss accidents, you can build a statistical model around it and say that whether this intersection is safe or unsafe. So you might not be able to prevent individual crash, but you can see the trends. And as the accuracies improve, there will be more real-time application rather than just batch processing of the data. So I think we always in transportation, at least I feel, is we are always bounded by what sensors are out there and how we are implementing it. So the applications would be just keeps getting better and better as the accuracies improve. But we can, I think we are at a point where we can start using some of these things for doing a lot of analysis. The other example is, for example, weather prediction on pavement. That's another place where I have seen people DOTs have started using some AI models to see if the pavement is dry or wet and things like that.
All right, yeah, I do think adding those, the camera is the most universal sensor that can capture everything, and using, for example, fisheye cameras have a great advantages since I have a huge field of view and it's cheap. But I do feel like solely based on fisheye cameras, that's why it's a challenge, right? It's hard to detect everything accurately. Like we see in our Track Pro challenge, I think the winning team have a score, F1 score about 60 something. So maybe this question to David or anybody have an idea? Also, Pranamish, you can jump in anytime. So do you think it would be better that we combine camera with other sensors to provide a better results?
So let me actually go back to the last question, and I think, I think Anuj, that's a good point, that some use cases are going to be easier to solve than others. I also just want to point out that technology is just one layer. So if you have a safe system approach, technology is never going to be completely bulletproof, and you want to look at how much can you get to with technology. What are the failure modes if it doesn't work, and what else is in place to help protect people so you don't have deaths and serious injuries in traffic. And part of that is, a lot of our work has been very focused on computer vision, but we're very aware of looking at multimodal analysis. So we have funded recently some work in terms of integration of image and LiDAR data, both roadside and vehicle-based, in part looking at cooperative perception to help identify and predict objects, particularly pedestrians, other vulnerable road users that might be obstructed from sensor data. I think there's also an opportunity to look at radar and image data, again, for that similar perception and situational awareness. And certainly if you're looking at behavior, I think it was great to have this discussion earlier about the privacy and the audio channel being turned off. There's a lot of information that you can get from the audio channel without necessarily having the actual language or speech. So you might be able to get the sense of, tension or anxiety in the voice. And that might be a useful type of analysis where you don't need to actually preserve the language or the recognition of the voice. So those are some things that, is potentially out there in terms of multimodal analysis. And I think, really that is going to give us a lot more depth, but at the same time, it's going to be much more complex.
All right, then I do have a next question following up this one coming up to my mind is, so right now, like you mentioned, we are focusing on the perception. I think one of the team previously in the individual paper presentation session also do prediction as well. So perception, prediction, then what's next? So I'm curious about what would be the actual complete loop look like to enhance the transportation safety. For example, when we do everything, would eventually gonna be alarm inside the vehicle to the driver, or would be something mounted on the traffic light pole to alarm the pedestrian? What would be the complete loop look like when we have accurate perception and prediction? What's next?
So I think couple of the ideas exist, and one idea is not just only the one vehicle perception, like a couple of the vehicle perception and how to integrate around the intersection something. And then now maybe you can see the many paper about the event-based camera, and then just simply use the event-based camera and visual light communication. We can do some communication between the vehicle to the intersection of the traffic signal. Then maybe we can also integrate that all the perception information to more make it safer to understand that the 3D information. And yeah, that is also the one idea. And also regarding the more technology wise for the vehicle is currently a vision large language model is getting popular. And then also there's one potential to replace the perception module by the vision large language model to end to end, include maybe the path planner or controller. This is also we are very thinking to very promising or good direction to the research. Yeah.
Okay. So definitely we can use other sensors on top of vision, because vision can detect people on the streets, like unless they are very occluded, like I just rode the Waymo in San Francisco before coming here, and at night it was great. So I felt like, okay, this is going, and but the thing is, Waymo will definitely see things, and it can avoid crashes. But how about the other drivers? The human drivers, right? And if we put some cameras on like using fisheye cameras, let's say, on the camera on the street and it can detect the cameras and the car is coming, the person is here, it's about to cross, and it's gonna the crash is gonna happen in 10 seconds. It can detect it. The AI can detect it, but how can we let the driver know it or the pedestrian know it? That's the important thing, I think. So as you said, like maybe there could be some device inside all of the cars that could receive the signal. If there is a signal can be sent out from the device on the street, and that could make an alarm. Or on the street, there could be also maybe a siren or something that could make a sound, make people aware of it. And yeah, this could help a lot. And also, I think, in UAE, there was a day a couple months before, there was a day that they announced there was a zero accident in the whole country, the traffic accident, I mean. So UAE uses lots of things to reduce accidents. One of the things was elevated intersection. It's about like 20 centimeters elevated. The whole area, intersection area is elevated, so that all the cars, when it comes to the intersection, they have to reduce the speed. And they said that it reduces the accidents rates by like 30%, if I'm not mistaken. So I think we should, mingle everything and reduce.
I think that's a very good point. I think both of you mentioned, but I think the end goal is perception, prediction, and then control. I think the control is the big part. So, and the control can be long-term control where the algorithm is suggesting something like raised intersection has this much safety benefit. It can be mid-range control where you can optimize signalized intersections or have cars going at a certain speeds. And then finally, short-term control in the sense that if an incident happened where everything is being rerouted, and those control would be at both aggregate at a disaggregate level at individual intersections, but also a hierarchical level. And finally, the idea would be that can we now have large language models where the traffic operator is just talking to this thing that this is my objective, and can RL take care of all the controls within at a different levels. So I think we have a long way to go. Perception and predictions are just the first brick.
Just to mention one place where I think we've seen some work on the control aspect, and that is work zone intrusion. So both in terms of feedback to drivers who are passing the work zone, as well as to people in the work zone. There's been a lot of work looking at what is the control aspect, what is the human in the loop, what are you able to automate? And I think that is a good use case for early trials. I think, for instance, intersections or conflicts between vehicles and pedestrians may be more complex, and will take some more work to figure out what is the human factor and what is the human in the loop in terms of those control aspects.
All right, that sounds great. So like control, we bring up a different domain, like a whole different challenge. Maybe we can explore this this domain later in our AICD challenge dataset as well. And I do want to ask about, so right now we have the synthetic dataset. We have the ability to create a virtual environment. And do you see the benefits of training models based on the virtual environment, creating any data set, mimicking any scenarios, and how do we, it's known there's a gap between the synthetic versus reality. How do we, what we can do to bridge the gap? Yeah, anyone? Yeah.
Well, I think very important topic, and especially the ID stuff is for the real pictures, it's quite cost for the annotation, so it's better to start the synthetic. And also like a recent couple of like research, they're using the now for like a Gaussian splitting and creating the, like a 3D model. And then in the 3D model, it's really photorealistic, and then putting some like a vehicle on this picture. This kind of combination also possible to train the model or validation. And then maybe, yeah, of course, there's some domain gap between the virtual and real. That part is a quite important topic for us, but that is also, how to say, we want to challenge, because Woven City has a real environment, the picture and also the real picture, and digital twin picture is a pixel-wise view aligned. So we are putting some like human cost to do that calibration. So that means like for the future, we also can test that this kind of how to minimize this the domain gap. So we are quite welcome to everyone to participate to the Woven City. Yeah. Thank you.
It's not an either or. So I think you can do human in the loop or hardware in the loop. You can do augmented reality in a way that you can really start teasing out where are the issues with the simulation, where are the issues with the real world. So for instance, we funded some work where we did a connected simulation where we had two human agents in the simulation. One was a driver, one was a pedestrian. And we had a human-human interaction. We had the machine interaction, sometimes when the vehicle was a machine and sometimes when the pedestrian was a machine. In the research we funded, people tried to guess whether they were interacting with a human or a machine, and they couldn't guess. But if you actually looked at their behavior, they behaved differently when they were interacting with a human pedestrian as opposed to a machine pedestrian. So there's something in that humanness that was represented in the simulation that was different. We're not quite sure what it is, but it shows that just the simulation itself, the machine acting as pedestrian, wasn't adequate to get the same reaction.
I think just adding on to that, even the simulation itself would be getting better and better. So I think that those boundaries would be merging, like we are all waiting for ChatGPT
Waiting next
to come up with a new simulator.
Yeah, maybe I will just tell a small thing. I think like synthetic data set can also help like to find out where our sensors can fail in something, like which kind of particular occlusions or so can always be like very difficult to handle by the sensors, like camera angles and so, and how we can therefore learn from the synthetic data to understand the shortcomings of the existing sensors and to tackle them, because from the synthetic data we know the ground truth, which would be very difficult to know from the real world data. So that may be like one instance where we can learn from the synthetic data the failure cases, which can help in our further expanding like how to handle the real world conditions.
All right. So to summary, I think it's time. But to summary the discussion, like we have a long way to go, basically. So both AICTE Challenger organization and all the researchers, we have a lot of room to improve, a lot of territory to explore, and I think eventually we can achieve our ambitious goal, like to detect the naturalistic driver behavior of bicyclists from fisheye cameras in Woven City.
Yes, that's it. That's the future challenge.
All right. Thank you very much.
Yeah, thank you.
recognize.
All right.
let's waste no time. Let's directly dive into the final section of AICT Challenge workshop this year. We are announcing the final results in this section. So just to emphasize that we do take the decision on who's the winning team, who's the runner-up very seriously. So we have a amazing evaluation system developed by David, but we cannot fully rely on the automatically rely on the results from the evaluation system because no system are perfect. We do manual check to make sure all the submitted results are trustworthy, so that all the researchers can carry on the work and leverage the submitted code in their own work in the future. Also because we forgot to share the screen. Yeah, I will do it. Oh, it's sharing. Okay, perfect. Okay, perfect. It's sharing. I was about to say also because we need to send out real GPUs. Yes. One more second. Okay. So here are the results from track 1. So on the left is the final ranking by the due date. We have presented this table in our summary paper. And the right-hand side is the latest public leaderboard. So you can see the top 2 teams remain the same. But this year we are promoting the online tracking algorithms. So actually here team 79, they are using an online algorithm, while team 221 are using an offline method. So 79 qualify for a 10% bonus. That's adding up to the 10%, it got 77% in score, overcoming the 71.9 score from team 221. So the winner for track 1 obviously challenge this year is team 79 from Shanghai Jiao Tong University and Lenovo. And the runner-up goes to team 221. Congratulations. So for the winner, we're gonna grant a brand new NVIDIA RTX 4080 Super GPU. And for the runner-up, we're gonna grant a super edge computing device as a Nano Orange Jetson. Yeah, the team, the winner team and runner-up team can go up to the stage and take a picture if you want. Start from the winner. So just want to clarify, initially in the very first version of AICT, we do bring the awards with us on site, but that time we only have 2 tracks, right? And this time we have 5 tracks, and we are awarding a super large GPU, and the GPU there, the packaging box have become bigger and bigger, fancier and fancier. Good for your winning teams, but we cannot carry all the devices here on site. So as what we have done previous years, we're gonna ship out those GPUs through corporate shipping. Okay, let's continue on to track 2. So again, on the left, the final ranking by the due date we published in the summary paper. On the right-hand side is the up-to-date leaderboard, and we see some of the teams have improved their records. Still, team 208 and team 28 come up in top. So here we announce the winner of track 2 from AICT Challenge 2024 is team 208, and the runner-up is team 28. Congratulations. Yeah. Winner can come up stage and take a picture.
And the runner-up. The runner-up. Team 28.
Team 28. All right. So track 3. Track 3, this year we receive a lot of participation and also a lot of submission to the evaluation system, but end up only 3 teams submit papers. So the winner and runner-ups gonna be generated from those 3 teams. Unfortunately, so this track is a special because the submission format is kind of simpler than others. So in other words, it's slightly easier to trick the submission results. So for track 3, we are receiving a dataset B so that we have to reproduce all the codes and running on our device on a new dataset B to determine the final ranking of the 3 teams. So due to some resource limitation, we are still working on that. So we're gonna publish the results on our webpage as soon as possible. And don't worry, your awards gonna be saved and shipped in the same time with other teams, with other tracks. So let's go to track 4. On the left, final ranking by due date. On the right-hand side, the latest public leaderboard. So the top 3 teams is kind of leading with a certain margin, but team ranked number 2 and number 3, they have a very close run. So for this case, we are actually taking this very seriously. And Dr. Gochu's team have spent a lot of efforts like reproducing the results. Since this track, a lot of teams using ensemble models. The models are hard to train, and Gochu's team actually go retrain the models and inference them on their devices. And we reproduce the results for the top 3 teams, and ends up the ranking is the same. So here we announce the winner for track 4 is team number 9. The runner-up is team 40. And we do want to give team 5 an honorable mention. They are ranked 3rd place, but they are very, very close to the 2nd place. Yeah, honorable mentions. Where's the picture as well? Congratulations. And eventually track 5 on the left, final ranking by due date, team 99 and 76. On right hand side, same team. And we verify the code and everything. They are the winner and the runners. So here, I should have changed that it's not co-winner, right? So the margin is noticeable. So for track 5, the winner is team 99 and the runner-up is team 76. Do we want to change the slides before taking a picture? Yeah. All right, just give me a second. All right, congratulations to team 99 and team 76 for winning those beautiful GPUs. Please come up to the stage and take a picture if you are here. All right, then this concludes our award ceremony, right? So this is the summary table of all the winning teams and runner-ups and the honorable mentions for all the tracks. Thanks a lot for participating in this 2024 version of AICD Challenge. Congratulations to all. And I will contact those winning teams separately afterwards and get your awards shipped.
Yeah, there is something to add on. Actually, the CVPR workshop this year we have something new. So they prepared some social media graphics for the workshop challenge winners. So for all the challenge winners, we will send these graphics to you tonight, so you can use them to create your own certificate and post to your social media. That's actually encouraged by CVPR. And also there will be a press release of all the workshop challenge winners by the official by the official blog or something by CVPR. So we will make sure that all of you are well recognized. And thank you again for all the participation. And now we will be moved towards the poster session. So the poster will be held at the exhibition hall of the building ARC, which is another building. So you will be a 5-minute walk from the building summit. So we can all go there. And please remember that our poster space have a assigned number. So we are number 68 to 96. Again, number 68 to 96. So please put your poster at that specific session. And we look forward to see you at the poster session. Thank you all again. We can do it up there. Yeah. Are you going there? So we have one. Oh, we can do it here as well. Do you have any questions? For all the organizers, let's come up here. We can take a group picture. I know some of you already left, but the rest of us, we can take a group picture together. Yeah, Professor Xie. Yeah, come. Yeah, come. Okay. Professor Xie, okay. 1, 2, 3, 18. Thank you. Thank you. Yes. Nice to see you. Thank you. Thank you very much for organizing everything. Thank you. Thank you. Yeah, no. Thank you for all the contribution. Are you going to the poster session or you need to take some rest?
This time one cannot join, but
maybe we
contribution.
No problem.